in the boundless void of space, where stars flicker like distant candles and galaxies drift silently through the cosmic sea, extraordinary enigmas lie waiting to be unraveled. From the savage storms raging on distant worlds to the unfathomable depths of black holes, the universe brims with mysteries that challenge the very limits of human understanding. Embark with us on a riveting expedition as we delve into the most astonishing secrets woven into the fabric of our cosmos. But first, let us turn our gaze to Jupiter, the colossal gas giant whose swirling atmosphere harbors the legendary Great Red Spot. This immense tempest, a storm larger than our entire planet Earth, has baffled astronomers and scientists ever since its first sighting in the 17th century. How could such a colossal vortex endure for centuries in an environment as turbulent and volatile as Jupiter's atmosphere? For over 300 years, this storm has persisted, defying early scientific predictions that such a phenomenon would quickly dissipate amid the relentless turbulent winds encircling it. Researchers now theorize that the Great Red Spot's extraordinary longevity owes itself to its sheer scale and depth. Extending possibly up to 100 miles into Jupiter's dense atmosphere, the storm's vastness acts as a barrier, absorbing and withstanding the energy of smaller surrounding storms that might otherwise erode it. This immense size creates a self-sustaining system, a colossal whirlpool in the planet's thick gaseous envelope that maintains its dominance with a power difficult to fathom. Yet, there is another enigma wrapped within this immense tempest: its striking crimson coloration. Despite its prominence, the precise cause of the Great Red Spot's deep red hue remains elusive. Scientists speculate that complex chemical reactions involving trace elements such as sulfur and phosphorus within Jupiter's atmosphere, altered by the relentless bombardment of ultraviolet sunlight, might be responsible for the storm's ruddy tint. This chromatic mystery opens a window into the chemical processes and environmental conditions high in Jupiter's atmosphere, a realm still largely veiled in secrecy and wonder. Meanwhile, turning our eyes toward another giant, Saturn reveals its own celestial spectacle, the mesmerizing rings that encircle it. These rings stretch across hundreds of thousands of miles, yet are astonishingly thin, some sections measuring no more than about 30 feet thick. Their elegant structure and enduring beauty have captivated astronomers for centuries. But how do these delicate rings maintain their intricate form without scattering into the void? The secret lies in the gravitational dance orchestrated by Saturn's myriad moons, often poetically dubbed shepherd moons. These smaller celestial bodies exert gravitational forces that shepherd the countless icy and rocky particles within the rings, corralling them into well-defined bands. Moons like Pan and Atlas play pivotal roles, stabilizing specific ring segments such as the broad A ring and the slender F ring, respectively. Their gravitational grip prevents the particles from dispersing, ensuring the rings remain intact. Adding yet more complexity, the ring's stability is further enhanced by a phenomenon known as orbital resonance. Here, certain moons and ring particles orbit Saturn in synchronized ratios, integer multiples of each other's orbital periods. This resonance reinforces gravitational pulls that continually sculpt and organize the ring's structure. The result is a stunning array of patterns that evolve dynamically, endlessly reshaping and reforming under the invisible hand of gravity. Primarily composed of gleaming water ice mixed with dust and trace chemicals, these particles reflect sunlight brilliantly, creating the ring's dazzling luminosity. Despite their ancient origins, estimated to be over 100 million years old, Saturn's rings are far from static relics. They are living, evolving testaments to celestial mechanics and the delicate balance maintained by gravitational forces in our solar system. Yet another atmospheric marvel lies on Saturn's northern pole: the enigmatic hexagonal storm. Discovered by the Voyager spacecraft in the early 1980s, this geometric weather phenomenon defies ordinary expectations. Stretching across a vast expanse, the hexagon's 6 perfectly straight sides each surpass Earth's diameter. What natural force could craft such a precise, enduring polygon in the chaotic tempest of a planetary atmosphere? Scientists attribute this hexagonal pattern to the complex interplay of atmospheric dynamics and fluid mechanics. At the core of this phenomenon lies the interaction of powerful jets of air flowing at varying speeds around Saturn's pole. The planet's rapid rotation, completing a full spin in just about 10 Earth hours, drives these jets to form shear zones where differences in velocity carve the air into a stable wave pattern, one that astonishingly takes the shape of a hexagon. Laboratory experiments and computer models have replicated these conditions, revealing how fluids moving at differing rotational speeds can naturally give rise to polygonal patterns. In Saturn's atmosphere, this wave remains remarkably stable, locked into place by deeper currents beneath the cloud tops. The hexagon is not merely a surface feature, it is embedded within the planet's atmospheric layers, sustained by powerful and persistent forces operating far below what we can directly observe. Adding another layer of fascination, the hexagon's colors shift over time, reflecting seasonal changes that alter the chemical makeup and sunlight exposure in Saturn's upper atmosphere. These evolving hues provide clues about the underlying processes that govern not only this extraordinary storm, but also Saturn's broader meteorological dynamics. As we unravel these mysteries, the great red spot's enduring fury, the delicate dance of Saturn's rings, and the strange geometry of the hexagonal storm, we gain deeper insights into the complex forces that shape our solar system. Each phenomenon is a chapter in the grand cosmic narrative, a testament to nature's power to create wonders that challenge our understanding and ignite our curiosity. The universe beckons us forward, promising countless other secrets beyond these giants. What lies beyond the reach of our telescopes and probes? How do the wild storms on alien planets compare to those in our own neighborhood? What strange phenomena lurk in the shadowy regions of black holes and distant galaxies? Our journey into the unknown has only just begun, and the mysteries of the cosmos await those bold enough to seek them out, but also offers broader implications for the study of fluid dynamics and atmospheric sciences. Uranus's rotation remains one of the solar system's most puzzling enigmas. Unlike the other planets, Uranus spins almost entirely on its side, with an axial tilt of approximately 98 degrees. This extraordinary tilt is not just a quirky fact, it fundamentally changes the way the planet experiences seasons, casting an intense and bizarre dance of sunlight and shadow across its surface as it orbits the Sun. Imagine a world that doesn't simply spin upright like Earth or Jupiter, but instead rolls along its orbital path, turning summers and winters into extremes that last decades. Scientists have long sought to understand how Uranus acquired this unique posture, and the dominant theory points to a cataclysmic event during the planet's infancy more than 4 billion years ago. In the chaotic early solar system, immense collisions were not uncommon. The hypothesis that one or several titanic impacts struck Uranus, knocking it askew, paints a dramatic picture of planetary formation fraught with violence. A colossal protoplanet, possibly as large as Earth itself, may have collided with Uranus at an oblique angle, forever altering its rotation and internal makeup. Such a force would not only tip the planet on its side, but also violently disrupt the internal layers, stirring its deep interiors and influencing the flow of heat from its core to its atmosphere. This collision hypothesis is strengthened by the peculiarities observed in Uranus's internal heat profile and magnetic field, which deviate markedly from those of its fellow gas giants. Unlike Jupiter and Saturn, which emit more heat than they receive from the Sun, Uranus stands out for radiating remarkably little excess heat. This suggests that whatever turmoil shaped Uranus's tilt also suppressed the internal convection currents responsible for transporting heat outward. Moreover, Uranus's magnetic field is a bizarre outlier. Instead of aligning closely with the planet's rotational axis as seen in Earth or Jupiter, Uranus's magnetic field is tilted about 60 degrees away and offset from the planet's center. This asymmetry hints at a complex and turbulent interior, possibly churned and distorted by the ancient collision, resulting in an irregular dynamo process that generates the magnetic field. The study of Uranus, therefore, is not just about understanding a single planet's peculiar tilt, but unlocking clues about planetary evolution, interior physics, and magnetic field generation in worlds beyond Earth. Meanwhile, far across the solar system, Neptune presents its own atmospheric mysteries. The dark spots discovered by Voyager 2 in 1989 captivated astronomers with their ephemeral and enigmatic nature. Unlike Jupiter's Great Red Spot, a storm that has persisted for centuries, Neptune's dark spots are transient phenomena. They appear and vanish over several years, dynamic and unpredictable. These spots are understood to be massive, high-pressure storms comparable to anticyclones on Earth, but they manifest far higher in Neptune's atmosphere. Their dark appearance is explained by the absence of the bright, ammonia-rich clouds that blanket much of the planet, exposing instead the deeper methane and hydrogen sulfide-rich layers below. This contrast in atmospheric chemistry creates the striking visual signature of these storms. Neptune's dark spots are shaped by a combination of factors unique to the planet's environment. The planet experiences some of the fastest winds in the solar system, with speeds reaching 1,200 miles per hour or more. Such fierce winds create immense turbulence, stirring the atmosphere and fostering the conditions necessary for storm formation. Additionally, Neptune's internal heat, though not as well understood as that of Jupiter or Saturn, drives convection currents that energize the atmosphere from within. The extremely low temperatures at Neptune's upper atmosphere, around minus 373 degrees Fahrenheit, also play a crucial role. These frigid conditions facilitate unusual chemical reactions and cloud dynamics, allowing methane and hydrogen sulfide to condense and produce the dark, stormy features we observe. The fleeting lifespan of Neptune's dark spots reveals much about the planet's volatile atmospheric conditions. The transient nature, because Mars lacks the kind of plate tectonics that shape Earth's surface, this hotspot remained fixed, allowing volcanic activity to concentrate in one location and build the mountain higher and wider over time. The sheer scale of Olympus Mons is a testament to this geological stasis, providing critical clues about Mars's internal structure and thermal evolution. Moreover, the presence of Olympus Mons hints at a more active and warmer past on Mars, a time when the planet was potentially capable of sustaining liquid water and, conceivably, life. Beneath its summit lies a massive caldera complex, evidence of numerous volcanic eruptions and collapses. The flows that built Olympus Mons contain minerals that formed in the presence of water, suggesting Mars's climate was once quite different, capable of supporting hydrous alteration and chemical processes essential to habitability. In contrast to the dry and cold Martian surface today, Olympus Mons reminds us that planetary environments are dynamic, shifting dramatically over time. The mountain's formation and continued presence challenge scientists to piece together Mars's geologic timeline, understanding when and how the planet lost its atmosphere and water, transitioning from a potentially habitable world to the barren desert we see now. Meanwhile, beyond Mars lies the enigmatic outer solar system, where icy bodies like Europa and Enceladus harbor subsurface oceans beneath their frozen crusts. These moons, with their potential for liquid water environments sheltered from harsh surface radiation, have become prime candidates in the search for extraterrestrial life. The gravitational pull from their giant parent planets, Jupiter and Saturn respectively, generates tidal heating, a process that keeps their internal oceans from freezing solid. This tidal flexing causes the ice shells of Europa and Enceladus to crack and shift, enabling geysers and plumes of water vapor to erupt into space, as observed by spacecraft like NASA's Galileo and Cassini missions. Analyzing these plumes offers a unique opportunity to study the chemistry of subsurface oceans without drilling through kilometers of ice, raising hopes that future missions could detect signs of life or habitability markers. Scientists believe that these moons could possess the essential ingredients for life: liquid water, organic molecules, and a source of energy. Europa, in particular, with its relatively young and active icy surface, shows signs of salt-rich water interacting with the rocky seafloor below, possibly supporting chemical reactions similar to those on Earth's ocean floors, where life thrives around hydrothermal vents. Similarly, Enceladus's south polar region reveals a complex interaction between water, rock, and heat, making it a natural laboratory for astrobiology. The detection of organic compounds and molecular hydrogen in its plumes hints at ongoing geochemical processes capable of supporting microbial life. The exploration of these icy worlds represents a frontier in planetary science, broadening our understanding of the conditions under which life might arise and survive. Missions like NASA's Europa Clipper and ESA's Jupiter Icy Moons Explorer, JUICE, are designed to probe these moons in unprecedented detail, searching for clues that could revolutionize our knowledge about the prevalence of life beyond Earth. Shifting back toward the inner solar system, Mercury presents yet another fascinating case of planetary extremes. Despite its proximity to the Sun, Mercury's surface is marked by a surprisingly large iron core, making up about 85% of its radius, and a thin silicate mantle. This unusual composition raises questions about its formation and subsequent evolutionary history. Mercury's heavily cratered rocky terrain bears witness to intense bombardment during the early solar system, preserving a record of impacts that shaped not only this small planet, but the entire inner solar neighborhood. Its thin atmosphere, or exosphere, composed mainly of atoms blasted off its surface by solar wind and micrometeorite impacts, provides a window into space weathering processes under extreme solar conditions. Interestingly, despite its small size, Mercury has a magnetic field about 1% as strong as Earth's, generated by a partially molten outer core. This magnetic field, although weak, deflects some solar particles, influencing the planet's exosphere and surface chemistry. Mercury's extreme temperature fluctuations, ranging from roughly 9 to 330 degrees Fahrenheit at night to 800 degrees Fahrenheit during the day, pose challenges to understanding how volatile elements and compounds behave. Yet, recent missions like NASA's MESSENGER and ESA JAXA's BepiColombo continue to reveal surprises, such as the presence of water ice in permanently shadowed craters near its poles, challenging prior assumptions about this scorched world. Together, these planetary stories from the solar system's varied members reveal a rich tapestry of dynamic processes, from violent collisions in the asteroid belt to volcanic giants on Mars, from hellish greenhouse climates on Venus to icy ocean worlds orbiting distant gas giants. Each body, in its unique way, contributes essential pieces to the puzzle of planetary formation, evolution, and the potential for life beyond Earth. By studying these diverse worlds, scientists not only unravel the history of our cosmic neighborhood, but also gain perspective on Earth's own environment and future. The lessons learned from the runaway greenhouse effect on Venus warn us about the fragility of planetary climates. The volcanic might of Olympus Mons showcases the power of geological forces shaping planetary surfaces. The icy moons whisper of hidden oceans and the tantalizing possibility of life in the most unexpected places. In essence, the solar system is a vast natural laboratory where every planet, moon, asteroid, and comet tells a story of cosmic creation and transformation. These stories, written in rocks, ice, and atmospheres, invite us to explore, discover, and ultimately understand our place in the universe, fueling humanity's eternal quest to reach beyond and find answers among the stars. And their structure collapses under their own weight, a silent surrender to the immense forces they bear. Additionally, the absence of plate tectonics on Mars reveals a stark contrast with Earth's restless crust. On Earth, tectonic plates glide, collide, and reshape the surface, birthing new volcanic formations as they move across molten mantles. Yet on Mars, these colossal volcanoes are anchored, stationary over their magma sources, locked in place for eons. This immobility grants them the power to erupt continuously, feeding vast rivers of lava that pile endlessly, building mountains of unimaginable scale over millions of years. Olympus Mons stands as the titan among Martian volcanoes, a colossal shield rising above the desolate plains. Its grandeur, however, belies a number of mysteries that have perplexed scientists for decades. Despite its titanic size, Olympus Mons is surprisingly young in geological terms. Its last eruption, estimated at roughly 25 million years ago, is but a fleeting moment in Mars's deep history, a mere blink on a planetary timescale. This fact kindles profound questions. Is Mars still alive beneath its surface, quietly humming with geothermal energy? Could there be ongoing volcanic activity hidden beneath the dusty exterior waiting to reveal itself? These questions fuel missions and debates, driving researchers to probe deeper into the planet's fiery past. Compounding the intrigue is the volcano's complex caldera structure at its summit. Unlike a simple crater, Olympus Mons caldera is a sprawling mosaic of overlapping collapse pits, each one marking a violent episode of eruption and subsidence. This multi-layered caldera speaks of a dynamic, tumultuous history, one of cycles of eruption, collapse, and resurgence. By unraveling the chronology and magnitude of these eruptive phases, scientists can unlock vital clues about Mars' internal processes and volcanic evolution, shedding light on planetary behaviors far beyond our home. The colossal scale and peculiar shape of Olympus Mons also hint at volcanic phenomena not entirely analogous to those found on Earth. Its broad, shield-like form and the immense lava flows suggest a complex volcanic history that may have involved unique, poorly understood mechanisms. This enigmatic structure offers a window into comparative planetology, inviting us to explore how volcanic activity manifests differently in diverse planetary environments. Through Olympus Mons, we stand to deepen our understanding of how planets evolve, how their internal dynamics shape their surfaces, and how these processes may vary across the cosmos. Far beyond Mars lies another realm of cosmic fascination, the Kuiper Belt. Stretching beyond Neptune's orbit, this vast expanse teems with icy bodies and dwarf planets, relics from the solar system's earliest days. Objects like Pluto call this frigid region home, frozen remnants of the primordial solar nebula that never coalesced into full planets. During the solar system's infancy, a sprawling disk of gas and dust swirled around the young sun, gradually accreting into larger and larger bodies. Yet the Kuiper Belt's low density and the gravitational influence of giant neighbors, especially Neptune, interrupted this growth, scattering countless icy fragments into a distant, cold frontier. The intricate gravitational ballet between Neptune and many Kuiper Belt objects, including Pluto, adds a further layer of complexity. Pluto's orbit, locked in a 2-3 resonance with Neptune, means it completes 2 orbits around the Sun for every 3 of Neptune's. This cosmic dance prevents collisions, stabilizing their paths through the solar system's outskirts. Such resonances have sculpted the Kuiper Belt into a rich and dynamic structure, with populations of objects differentiated by their orbital rhythms and histories. Yet, the story of Kuiper Belt objects goes beyond orbits. Pluto, revealed in stunning detail by the New Horizons mission in 2015, shows a world alive with geological diversity. Its surface is a tapestry of towering mountains, vast plains, and strange formations hinting at cryovolcanism, the eruption of volatile substances like water, ammonia, or methane, rather than molten rock. This suggests internal heat sources that defy the frigid conditions, perhaps fueled by radioactive decay or tidal forces exerted by distant planetary companions. These processes imply that, despite the bitter cold and remote location, Kuiper Belt bodies may remain active over billions of years, their interiors simmering beneath icy shells. Studying these frozen sentinels unlocks stories of solar system formation and migration, weaving together the grand narrative of how our cosmic neighborhood came to be. Each Kuiper Belt object is a chapter, revealing the conditions of the early solar nebula, the forces that shaped planetary orbits, and the dynamic processes ongoing at the solar system's edge. In this way, the Kuiper Belt stands as a crucial key to understanding the full scope of planetary evolution. Closer to the Sun, Mercury, the smallest and most sunward planet, presents its own set of enigmas. Despite its proximity and size, Mercury boasts a surface marked by extraordinary features that defy easy explanation. Among the most mysterious are the hollows, shallow, irregular depressions with bright reflective halos unlike any typical impact craters. Their formation remains a puzzle, tantalizing scientists with the possibility of unknown geological or chemical processes at work. Some hypothesize that these hollows result from the sublimation of volatile materials under the intense solar heat, a process unique to Mercury's harsh environment. Others suggest a more complex interplay of solar wind erosion and internal geologic activity. Mercury's landscape, scarred and ancient, is a testament to the brutal forces it has endured, from massive impacts to relentless solar radiation. Its tenuous atmosphere, or exosphere, is a delicate veil of atoms stripped from its surface, dancing in the solar wind's constant gusts. This planet's extreme conditions make it a natural laboratory for understanding planetary resilience and surface evolution under intense space weathering. In each of these distant worlds, Mars with its towering Olympus Mons, the icy Kuiper Belt with its frozen remnants, and Mercury's enigmatic hollows, lies a profound story of planetary birth, change, and enduring mystery. These landscapes, forged by volcanic fury, gravitational choreography, and relentless solar forces, offer humanity a window into the forces that sculpt the cosmos. By probing their secrets, we not only uncover the history of our solar system, but also gain insight into the processes that shape planets across the galaxy. But they are hypothesized to result from the sublimation or direct transition from solid to gas of volatile elements. Such volatiles might have been brought to the surface by volcanic activity or outgassing from the planet's interior, resulting in the creation of these mysterious, ever-changing depressions as they evaporate under the sun's intense heat. Mercury's surface is a canvas painted by forces both ancient and active, revealing a narrative of transformation and enigma that challenges our understanding at every turn. Another anomaly on Mercury's surface is the existence of unusual, large, and unexplainable scarps or cliffs known as lobate scarps. These dramatic geological formations are believed to be thrust faults formed as Mercury's core cooled and contracted over billions of years, effectively squeezing the crust and creating these towering cliffs that sometimes stretch hundreds of kilometers. However, what perplexes scientists most is recent evidence suggesting that some of these tectonic features may still be geologically active today. Data from NASA's Messenger mission, which orbited Mercury between 2011 and 2015, revealed that these scarps might have experienced seismic activity in relatively recent geological timescales. This discovery disrupts the long-held assumption that Mercury, as a small rocky planet, should have been geologically dead for eons. Instead, it raises fascinating questions about the planet's current internal dynamics and thermal evolution. Could Mercury still harbor a slowly cooling core, maintaining tectonic activity that shapes its surface even now? The evidence suggests that the planet might not be as dormant as once believed. Adding to the complexity, Mercury experiences extreme temperature fluctuations, ranging from an intense 800 degrees Fahrenheit during the day to a bone-chilling minus 290 degrees Fahrenheit at night. These dramatic thermal swings exert enormous stress on the planet's crust, contributing to surface anomalies. The planet's surface is peppered with secondary craters and ejecta patterns that appear more chaotic and irregular than those seen on other bodies in the solar system. This chaotic distribution could be the result of intricate interactions between Mercury's thin regolith, the loose layer of dust and rock fragments, and its tenuous exosphere, which is influenced by relentless solar radiation and frequent micrometeorite impacts. These surface anomalies on Mercury are not just geological curiosities. They represent keys to deciphering the broader processes of planetary formation, thermal evolution, and the dynamic interplay between internal and external forces that sculpt rocky worlds. As humanity continues to study Mercury, especially through forthcoming missions like Bepi Colombo, a joint European-Japanese mission currently en route to the planet, our understanding of these enigmatic features will undoubtedly deepen, offering unprecedented insight into the smallest rocky planet in our solar system. Detecting exoplanets, those distant worlds orbiting stars beyond our solar system, is an equally challenging yet thrilling frontier of modern astronomy. The vast distances separating us from these planets, combined with their faint visibility compared to their host stars, require astronomers to employ ingenious and diverse methods to discover and study them. Each method reveals a fragment of the exoplanet's story, pieced together like a cosmic puzzle. One of the most successful and widely used techniques is the transit method. This method involves observing the periodic dimming of a star's light as an exoplanet passes, or transits, in front of it from our viewpoint on Earth. These tiny decreases in brightness, often less than 1%, are meticulously detected by space telescopes such as NASA's Kepler and the Transiting Exoplanet Survey Satellite, TESS. By analyzing these transit events, astronomers can deduce key planetary characteristics, including size, orbital period, and in some cases, atmospheric composition. When the exoplanet's atmosphere filters the starlight, subtle changes in the spectrum can reveal the presence of gases like water vapor, methane, or even more exotic compounds. Complementing the transit method is the radial velocity or Doppler technique. This approach measures shifts in the star's spectrum caused by the gravitational pull of an orbiting planet. As the planet orbits, it induces a slight wobble in the star's motion, shifting its light spectrum toward the red end when moving away and toward the blue end when moving closer. Highly precise spectrometers can detect these minute shifts, enabling scientists to infer the presence of an exoplanet and estimate its mass and orbital characteristics. Ground-based observatories equipped with instruments like HARPS, High-Accuracy Radial Velocity Planet Searcher, have been instrumental in refining this technique, revealing hundreds of exoplanets and enriching our knowledge of planetary systems beyond our own. Another fascinating avenue is direct imaging, which involves capturing pictures of exoplanets themselves by blocking the overwhelming glare of their host stars. This method is particularly suited to young, massive exoplanets located far from their stars, where the light contrast is more manageable. Instruments such as coronagraphs and star shades are deployed to suppress the star's light, allowing the faint glow of the planet to emerge. Despite the immense challenges posed by the faintness and proximity of these distant worlds to their stars, advancements in adaptive optics and the advent of next-generation telescopes like the James Webb Space Telescope promise to enhance the feasibility and precision of direct imaging. In addition, the gravitational microlensing method exploits the gravitational field of a star and its planet to bend and magnify the light from a more distant background star. When such an alignment occurs, the resulting light curve can reveal the presence of the planet, even if it orbits far from its host star, or would be otherwise undetectable by other methods. This technique is especially powerful for discovering planets that reside in the cold outskirts of their systems, regions often elusive to other detection strategies. Each of these methods offers unique strengths and limitations, but together they paint a richer, multidimensional picture of exoplanetary systems. By combining transit, radial velocity, direct imaging, and microlensing data, astronomers can infer not just the existence of these distant planets, but also their physical properties, atmospheres, and potential habitability. As technology advances, the precision and breadth of these observations will only grow, opening new windows into the diversity and complexity of planets populating the universe. Among the myriad classes of exoplanets uncovered, hot Jupiters stand out as particularly intriguing. These colossal gas giants share similarities with our own Jupiter in terms of their massive size and gaseous composition, but orbit perilously close to their stars, often completing an orbit in mere days. The intense stellar radiation these planets endure creates exotic atmospheres and extreme weather patterns, turning them into cosmic laboratories for studying atmospheric physics under conditions unimaginable in our solar system. The discovery and characterization of hot Jupiters have transformed our understanding of planetary formation and migration, revealing that planetary systems can be dynamic and wildly different from our own. The exploration of Mercury's enigmatic surface features and the ongoing quest to discover and study exoplanets illustrate the incredible breadth and depth of planetary science today. These endeavors weave together observations from spacecraft hurtling through our solar system and telescopes peering deep into the galaxy, revealing the intricate and often surprising ways that planets live, evolve, and interact with their environments. Each discovery pushes the boundaries of human knowledge, reminding us of the complexity of the cosmos and our enduring quest to comprehend it fully. But orbiting extremely close to their host stars, these exoplanets defy what we once believed possible in planetary systems. Often hugging their stars at distances far closer than Mercury's blistering approach to our Sun, these so-called hot Jupiters complete their orbital journeys in mere days. Their proximity subjects them to searing temperatures, often soaring into the thousands of degrees Fahrenheit, a crucible of heat that shapes their very nature. The intense stellar radiation bombarding these planets transforms their atmospheres in dramatic ways, setting them apart from the cooler gas giants drifting serenely in the outer reaches of their systems. Winds of extraordinary strength whip across their skies, while atmospheric gases expand, ballooning under the relentless heat. Some of this atmosphere is even stripped away, escaping into space in a slow, fiery evaporation. This process is not just a curiosity. It is a window into the complex dance of forces at play where star and planet intertwine so closely. The origins of hot Jupiters remain a fascinating puzzle. Current research delves deep into the mysteries of their formation and migration, revealing a narrative of cosmic journeys far from straightforward. One prevailing theory suggests that these giants begin their existence in the cool, distant outskirts of their protoplanetary disks, vast clouds of gas and dust circling young stars, much like Jupiter in our solar system. But unlike Jupiter's settled orbit, these massive bodies embark on an inward migration, pulled and pushed by intricate gravitational interactions. These migrations might be driven by the planet's interactions with the gaseous disk itself. As the planet moves, it stirs waves within the disk, waves that carry away angular momentum, causing the planet to spiral inward ever closer to its star. Alternatively, dramatic gravitational encounters with other massive planets or companion stars could send a giant planet careening into an elongated elliptical orbit. Over time, tidal forces between planet and star work to round and shrink this orbit, eventually locking the planet into a tight, blisteringly close path, its hallmark as a hot Jupiter. The existence of these extreme worlds challenges our traditional models of planetary system evolution. They reveal the dynamism and diversity hidden beyond the familiar layout of our solar system, hinting at complex and often violent processes sculpting planetary architecture. Each discovery broadens our understanding of how planets interact with their stars and each other, painting a picture of planetary systems as living, evolving entities. Hot Jupiters serve as natural laboratories where astronomers can study atmospheric physics under conditions impossible to replicate on Earth. They teach us about the influence of intense stellar radiation, the mechanics of atmospheric escape, and the powerful winds driven by temperature extremes. These lessons ripple outwards, enriching our grasp of exoplanetary atmospheres and the myriad ways planets respond to their environments. Meanwhile, the quest to find potentially habitable exoplanets, the worlds that might cradle life, remains one of modern astronomy's most compelling challenges. The classical idea of a habitable zone, the Goldilocks zone, where conditions allow liquid water to persist on a planet's surface, has guided this search for decades. Yet recent findings push us to reconsider and expand this definition. Habitability depends on a complex interplay of factors beyond mere distance from a star. The planet's atmospheric composition, geological activity, and magnetic field all shape its potential to sustain life. Take, for example, the discovery of multiple Earth-sized planets orbiting red dwarf stars, such as those in the TRAPPIST-1 system. These stars, smaller and cooler than our Sun, emit intense stellar flares and exhibit fluctuating luminosity, creating a hostile environment that calls into question the survivability of life as we know it. Yet, these planets compel scientists to study how life might adapt or thrive under such conditions, broadening the horizons of what habitable truly means. Understanding the atmospheres of exoplanets, both habitable and hostile, is a frontier rich with mystery. Methods like the transit technique reveal a planet's size and orbit, while radial velocity measurements inform us about its mass. But decoding the chemical makeup of these distant atmospheres is far more complex. Advances in spectroscopy now allow astronomers to detect molecules such as water vapor, methane, and oxygen in exoplanetary atmospheres by analyzing the light filtered through them during transits. Yet interpreting these signals requires caution. Oxygen might indicate biological activity, but it could also be produced by non-biological chemical processes like the photodissociation of water. Beyond atmospheric composition, the true climate and geological state of these worlds remain elusive. An Earth-sized planet does not guarantee Earth-like conditions. Factors such as rotation speed, axial tilt, ocean circulation, and volcanic activity profoundly influence climate and, by extension, habitability. These complexities underscore the challenge of assessing a planet's capacity to host life based solely on size and orbital distance. Future instruments like the James Webb Space Telescope promise to revolutionize our understanding. With unprecedented sensitivity, this telescope aims to provide detailed analyses of exoplanetary atmospheres, potentially identifying biosignatures or other indicators of life. The forthcoming data will undoubtedly deepen our knowledge of the complex interactions shaping planetary environments and push the boundaries of our cosmic perspective. In these discoveries and inquiries, we stand at the threshold of understanding worlds vastly different from our own, each a testament to the intricate, awe-inspiring forces that govern the cosmos. The story of exoplanets is a story of extremes, migration, and survival, a story that continues to unfold as we gaze deeper into the universe, seeking answers to some of humanity's most profound questions about existence and the possibility of life beyond Earth. But for now, the questions surrounding these distant worlds linger like cosmic shadows, veiling their true essence in layers of mystery. The enigma extends far beyond mere composition or orbit. It reaches into the very heart of existence itself, the potential for life beyond our familiar cradle. What if the life that inhabits other planets defies the very biochemistry that underpins life on Earth? What if the molecules and processes that sustain organisms elsewhere follow rules completely alien to our understanding? This profound uncertainty demands that the search for biosignatures, the unmistakable indicators of life, must expand beyond the narrow confines of Earth-like conditions and chemistry. The discovery of extremophiles on our own planet has shattered long-held assumptions about where life can exist. These extraordinary organisms thrive in environments once deemed utterly inhospitable. Scalding hydrothermal vents deep beneath the ocean, crushing pressures miles underground, acidic hot springs, and the frozen deserts of Antarctica. Their resilience forces us to broaden our horizons, to imagine life not only on sun-washed surfaces, but also hidden beneath ice, rock, and clouds. This expanded view has led scientists to consider habitability in realms previously overlooked, such as the subsurface oceans locked beneath the icy crusts of moons like Europa and Enceladus. These concealed oceans may be mirrors of those that could exist on distant exoplanets, worlds bathed not in sunlight but in internal warmth and tidal forces, nurturing the faint flickers of life in darkness. Every new exoplanet discovered within the so-called habitable zone, the region around a star where liquid water might persist, propels humanity closer to answering an ancient and fundamental question: are we alone in the vast cosmos? Yet, each revelation also deepens the puzzle. Planetary systems reveal themselves as kaleidoscopes of complexity and diversity, expanding our definition of what makes a world truly habitable. In this expanding frontier, super-Earths emerge as particularly captivating enigmas, planets more massive than our own, but still far lighter than the gas giants Neptune or Uranus. Typically ranging from 1 to 10 Earth masses, these worlds challenge simplistic comparisons. The label super-Earth might imply similarity, but these planets often bear little resemblance to our terrestrial home. Super-Earths defy easy categorization through their striking variations in size, mass, and composition. The sheer increase in mass translates into stronger gravitational forces, which can profoundly alter atmospheric properties. Some may harbor dense, thick atmospheres rich in lightweight gases like hydrogen and helium, especially if they formed farther out in their star's protoplanetary disk before migrating inward. These thick gaseous envelopes might create crushing surface pressures and searing temperatures, forging environments wildly distinct from Earth's temperate embrace. Beneath their skies, the internal structure of super-Earths presents another spectrum of possibilities. Some might resemble gigantic rocky worlds with colossal iron cores, worlds forged in the crucible of heavy metals and rock. Others could be veritable water worlds, their surfaces blanketed by global oceans hundreds of miles deep, drowning continents beneath endless liquid. In such worlds, the immense pressure at the ocean's depths would reshape geochemical cycles and pose unique challenges for any life forms daring to exist in such alien seas. The geological heartbeat of super-Earths may also differ significantly from that of our planet. Larger planetary masses could retain internal heat longer, potentially driving vigorous tectonic activity. This tectonic dynamism could play a pivotal role in stabilizing climates, recycling essential minerals, and sustaining long-term habitability. However, without direct observations or a firm grasp of tectonics beyond Earth, these hypotheses remain speculative, woven from the threads of theory and imagination. Furthermore, the climate and weather on super-Earths could be alien in their intensity and character. Thick atmospheres combined with potent greenhouse effects may trap heat to such a degree that surface temperatures soar relentlessly. Rapid planetary rotation might fuel tempestuous storms, creating volatile and unpredictable weather systems. Yet, amidst this diversity, some super-Earths might possess atmospheres more forgiving, with compositions that moderate climate extremes, perhaps even allowing for conditions where life as we know it, or as we can imagine it, might thrive. The study of super-Earths is still emerging from the shadows of cosmic discovery, a field poised on the threshold of profound insight. These planets compel us to rethink planetary formation, atmospheric evolution, and the very essence of habitability. They span a vast spectrum, from hostile worlds with suffocating atmospheres and crushing pressures to temperate, ocean-covered planets with gentle climates and the tantalizing potential for life. The exploration of these distant worlds is a journey into the unknown, an unfolding story of cosmic diversity and the endless possibilities for life beyond Earth. Each new discovery enriches our understanding, challenges our preconceptions, and invites us to look deeper into the universe and ourselves. The mysteries of super-Earths beckon, a cosmic call to uncover the secrets written in the stars and oceans of distant planets as humanity reaches ever outward into the boundless tapestry of the cosmos. But with the relentless march of technology and the revolutionary advances in telescope design and observational methods, the enigmatic nature of these distant worlds continues to unravel before our eyes, revealing an astonishing complexity that deepens our comprehension of the countless ways in which planets form and evolve throughout the cosmos. When planetary scientists first embarked on the detailed scrutiny of exoplanet atmospheres, they were met with a series of jaw-dropping discoveries that forever expanded the horizons of planetary science. Among the most extraordinary findings was the detection of elements and chemical compounds in states rarely, if ever, witnessed within our own solar neighborhood. For example, on the exoplanet designated HD 18973b, researchers uncovered tantalizing traces of silicate particles suspended high in the upper atmosphere. These silicates coalesce into droplets of molten glass rain, cascading sideways, driven by ferocious winds that can reach speeds of several kilometers per second. This bizarre meteorological spectacle evokes a vision of an alien world far removed from Earth's comparatively gentle weather patterns, illustrating just how diverse planetary climates can become under different stellar influences and atmospheric compositions. Equally captivating are the photochemical processes at work in the atmospheres of the so-called hot Jupiters, gas giants locked in tight orbits around their blazing host stars. The searing heat from these stars breaks molecular hydrogen apart into atomic hydrogen, while the intense ultraviolet radiation energizes these atoms, generating a luminous cloud of hydrogen gas that escapes into space. This phenomenon was observed directly on the exoplanet HD 209458b, where astronomers witnessed a comet-like tail of hydrogen trailing the planet, an unmistakable sign of dynamic atmospheric escape. Such processes, occurring over millions or even billions of years, can drastically reshape a planet's atmosphere and influence its long-term evolutionary path, offering invaluable insight into the life cycles of planetary atmospheres and the delicate balances that sustain them. Rogue planets, sometimes called interstellar or orphan planets, add an even more mysterious chapter to the cosmic narrative. These celestial wanderers drift aimlessly through the vast void between stars, unbound by the gravitational embrace of any sun. Unlike planets that follow stable elliptical orbits within a solar system, rogue planets chart unpredictable courses, shaped by the violent gravitational upheavals that expelled them from their birthplaces. Their ejection may result from close encounters with other massive planets or passing stars during the chaotic early stages of planetary system formation, when gravitational forces can launch planets on a solitary journey across the galaxy. This lonely trek through interstellar space is a chilling one, as these planets receive no warmth from a nearby star. Instead, their faint heat signatures stem from residual formation heat and possibly internal radioactive decay, potentially enough to maintain subsurface oceans beneath icy crusts. Some scientists speculate that these hidden oceans might harbor environments capable of supporting life, raising profound questions about habitability in the most unexpected corners of the galaxy. Despite their cold, dark solitude, like rogue planets streak through the Milky Way at speeds often reaching tens of kilometers per second, their paths subtly shaped only by the gravity of distant stars and the overall galactic mass. Studying the weather and atmospheric conditions on such distant and disparate worlds presents a daunting array of challenges. Unlike Earth, where we deploy a complex network of satellites and ground-based instruments to monitor atmospheric phenomena in exquisite detail, astronomers must rely on indirect techniques to probe exoplanet atmospheres. Chief among these is spectroscopy, the analysis of the light that filters through or radiates from a planet's atmosphere. This method demands unprecedented precision because the faint glow or reflected light from an exoplanet is almost invariably overwhelmed by the intense brilliance of its parent star. Isolating the subtle signatures of atmospheric molecules requires sophisticated data processing and the use of advanced space-based observatories equipped with cutting-edge instruments. The Hubble Space Telescope pioneered these studies, peering at exoplanet atmospheres with unparalleled clarity. Now, the James Webb Space Telescope extends this capability to new heights, equipped with infrared detectors designed to reveal the fingerprints of molecules that shape the climate, chemistry, and potential habitability of distant worlds. The quest to understand exoplanetary weather is a thrilling frontier in astronomy, one that pushes the limits of technology and human curiosity. Each new discovery peels back layers of cosmic mystery to transforming once speculative science fiction ideas into empirical knowledge. From the glass rainstorms on scorched gas giants to the drifting, cold expanse inhabited by rogue planets, the universe continues to astonish, inviting us to explore and comprehend the extraordinary diversity of planetary environments that exist beyond our own celestial neighborhood. Moreover, the dynamic nature of weather systems introduces a remarkable layer of complexity when studying exoplanets, especially those residing in extreme environments. Take hot Jupiters, for instance, colossal gas giants orbiting perilously close to their stars, where the conditions are far beyond anything we witness on Earth. These planets exhibit weather patterns that can change with astonishing rapidity, driven by forces far more varied and intense than terrestrial meteorology. Their atmospheres are guarded by intense stellar radiation that heats their surfaces to scorching temperatures. This immense energy input fuels high-speed winds reaching thousands of miles per hour, creating atmospheric turbulence unlike anything encountered in our solar system. The atmospheric compositions themselves can be strange and exotic, composed of chemicals and elements unusual to our earthly eyes, further complicating the modeling efforts. The phenomenon of tidal locking adds yet another fascinating dimension to these weather patterns. Unlike Earth, where every region experiences day and night in a rhythmic cycle, tidally locked exoplanets keep one hemisphere perpetually facing their star, while the other side remains in eternal darkness. This extreme differential heating between the blistering day side and the freezing night side results in fierce storms and broad-scale atmospheric circulation patterns that defy easy prediction. Modeling these interactions challenges our current understanding of physics and atmospheric science, as the energy flow and fluid dynamics operate on scales and intensities previously unimagined. Compounding the difficulty is the reality of limited observational time on the most powerful telescopes humanity has ever built. Each observation window is precious and fleeting, often hampered by interference from Earth's own atmosphere. These constraints severely restrict the amount of data astronomers can collect to build long-term, accurate weather models for exoplanets. Despite these formidable obstacles, the study of exoplanetary weather remains a frontier ripe with promise, a domain where scientific ingenuity could unlock astonishing discoveries about distant worlds and the forces that shape them. Adding yet another layer to this cosmic puzzle is the formation of exoplanets within binary star systems, a phenomenon that adds extraordinary complexity to an already intricate process. Binary stars, pairs of stars locked in a gravitational dance around a common center of mass, exert profound influence on the protoplanetary disks, vast, rotating bands of gas and dust from which planets are born. The gravitational tug of these stellar companions shapes the disk structure in unique and often chaotic ways, setting the stage for planetary formation scenarios that challenge conventional understanding. Within these binary systems, two primary configurations govern the pathways of planet formation: circumbinary and circumstellar. In the circumbinary scenario, planets emerge from a disk that encircles both stars, a complex environment where the combined gravitational forces sculpt the protoplanetary material. This interplay can either stabilize or destabilize certain regions within the disk, affecting where and how planets can coalesce. Typically, the innermost portions of such circumvenary disks are cleared of solid matter due to dynamic perturbations, pushing planet formation zones farther out. Yet, despite these challenges, discoveries like Kepler-16b, a planet orbiting two stars, confirm that planet formation in these conditions not only happens, but produces worlds with distinctive and fascinating orbital behaviors molded by the twin star dynamics. In contrast, circumstellar planets form around a single star within the binary pair. Here, the gravitational influence of the companion star can induce eccentricities, elongations, and distortions in the protoplanetary disk. These distortions alter the disk's density and temperature profiles, factors critical to planet formation. Depending on the intensity of these gravitational perturbations, planet formation can be either hindered or fostered. Key factors influencing these outcomes include the distance between the two stars and their relative masses. Planets born in such environments often follow more eccentric orbits than those around single stars, continuously shaped by the companion star's gravitational pull. This results in planetary developmental pathways that are highly diverse, reflecting the astonishing variety of planetary systems our universe can produce. As astronomers delve deeper into these remote worlds, their quest to find signs of life becomes increasingly sophisticated. They search for a wide array of biosignatures, indicators that hint at biological activity on distant planets. One of the most compelling biosignatures is the presence of certain gases in an exoplanet's atmosphere, especially those closely linked to life as we understand it on Earth. Oxygen, for example, is a crucial marker because it is produced and continually replenished by biological processes like photosynthesis. Without such processes, free oxygen would react with other elements and gradually disappear from the atmosphere, making its persistent presence a strong clue of potential life. Methane is another intriguing biosignature, particularly when found together with oxygen. Methane tends to break down rapidly under atmospheric conditions, so its detection alongside oxygen suggests an ongoing source replenishing it, possibly biological in nature. Beyond individual gases, scientists analyze the broader atmospheric composition and the complex interactions between different chemical species. The simultaneous presence of gases such as ozone and nitrous oxide, or particular ratios of carbon dioxide and water vapor, can suggest biological processes at work beneath the planet's surface or within its atmosphere. Moreover, the search extends beyond gases to include organic molecules, complex carbon-based compounds central to life. The detection of these molecules requires highly sensitive instruments capable of performing detailed spectroscopic analyses. Telescopes like the James Webb Space Telescope are designed to peer through the light filtered by an exoplanet's atmosphere, identifying these subtle signatures with unprecedented precision. This capability allows scientists to probe the chemical makeup of distant worlds, uncovering hints that could reveal whether life exists elsewhere in the cosmos. In sum, the exploration of exoplanetary atmospheres, weather systems, and formation in diverse stellar environments is one of the most dynamic and challenging frontiers in contemporary astronomy. Each discovery pushes the boundaries of human knowledge, revealing a cosmos rich in variety and complexity. From the tempestuous skies of hot Jupiters bathed in fierce stellar winds to the intricate gravitational choreography in binary star systems, these investigations shed light on the myriad ways planets can form and evolve. The ongoing search for biosignatures holds the promise of answering one of humanity's most profound questions: are we alone in the universe? As technology advances and telescopes grow ever more powerful, the coming decades may bring revelations that transform our understanding of life and our place among the stars. Moreover, scientists tirelessly observe the intricate surface conditions of distant planets, seeking clues that could unveil the secrets of habitability across the cosmos. The search for life beyond Earth hinges significantly on identifying the presence of liquid water, whether it flows visibly on the surface or lies hidden beneath icy crusts. Water is not merely a substance, but the very foundation of biochemical reactions. a universal solvent nurturing the complex chemistry necessary for life to arise and flourish. This quest involves understanding a planet's placement within its star's habitable zone, the delicate orbital region where temperatures allow liquid water to persist. This zone is more than just a cosmic sweet spot. It is the cradle where life as we know it could potentially thrive. The endeavor to find life takes a comprehensive approach, weaving together clues from atmospheric composition, surface environments, and the long-term stability of these planetary systems. Scientists carefully piece together these indicators, constructing detailed portraits of alien worlds to estimate the likelihood of life taking hold. Among these fascinating celestial bodies, exoplanetary moons, or exomoons, emerge as compelling candidates in the cosmic narrative of habitability. These moons, often orbiting giant gas planets, are not mere satellites, but potential habitats themselves, capable of creating environments where life might emerge. Tidal heating is one of the remarkable processes that exomoons contribute to their host systems. The gravitational dance between a moon and its planet causes the moon's interior to flex and rub against itself, generating internal frictional heat. This subtle yet persistent source of warmth can keep subsurface oceans in a liquid state, defying the freezing cold of outer space. Our solar system's moons, Europa and Enceladus, serve as tantalizing examples, with evidence suggesting vast oceans beneath their icy shells that could harbor life. Similarly, exomoons around distant stars could possess these warm, hidden oceans, offering potential refuges for life far from starlight. In addition to heating, exomoons may exert influence over their planet's axial tilt, playing a vital role in stabilizing climatic conditions. A steady axial tilt leads to predictable seasons, which is crucial for fostering environments capable of supporting complex ecosystems. Without such stability, a planet's climate might oscillate wildly, posing challenges for life's persistence. Moreover, some exomoons could protect their host planets' atmospheres from the relentless onslaught of solar winds, especially if these moons have magnetic fields of their own. These magnetic shields act as cosmic umbrellas, preserving atmospheric integrity and helping maintain liquid water on the surface, an essential ingredient for life. The possibility that exomoons themselves could be independent harbors of life adds an extraordinary layer to the search. Should these moons reside within the habitable zone of their star systems, they might boast their own atmospheres, oceans, and perhaps even geological activity. Upcoming astronomical instruments aim to scrutinize these moons meticulously, detecting signs of water vapor, geological dynamics, and biosignatures, chemical hints of life that echo the efforts to study exoplanets. The discovery of exomoons enriches the complexity of astrobiological exploration, opening new frontiers in understanding where life might exist beyond Earth. Shifting from the realm of life-supporting worlds to the most enigmatic objects in the universe, black holes capture the imagination with their mysterious nature and staggering power. These cosmic entities come in diverse types, primarily distinguished by their size and mass, each category revealing unique stories of formation and existence. Stellar mass black holes arise from the death throes of massive stars. When a star over about 25 times the mass of our Sun runs out of nuclear fuel, it explodes in a cataclysmic supernova. The core left behind succumbs to gravity's relentless pull, collapsing into a singularity, a point of infinite density, shrouded by an event horizon, the boundary beyond which nothing, not even light, can escape. These black holes typically weigh several times the mass of our Sun and pepper galaxies, including our own Milky Way. Supermassive black holes found lurking at the centers of most galaxies represent a cosmic class of their own, boasting masses millions to billions of times that of the Sun. Their origins remain one of astrophysics' deepest puzzles, with theories ranging from the collapse of massive gas clouds in the early universe to the merger of smaller black holes over time. These giants influence their host galaxies profoundly, regulating star formation and galactic dynamics through their immense gravitational pull and energetic outflows. Between these extremes lie intermediate mass black holes, elusive and less understood, potentially bridging the gap in size and formation between stellar mass and supermassive black holes. Their detection remains challenging, but their existence could illuminate key processes in black hole growth and galactic evolution. Through continuous observation and theoretical breakthroughs, scientists piece together the life cycles of black holes, unraveling the interplay of gravity, matter, and energy in these cosmic titans. Their study not only deepens our understanding of fundamental physics, but also frames the grand tapestry of cosmic evolution, from the birth of stars to the fate of galaxies themselves. But several theories exist to explain the enigmatic origins and nature of black holes, weaving together a rich tapestry of cosmic evolution, astrophysical phenomena, and the mysteries lurking at the very fabric of space-time. One prominent hypothesis suggests that supermassive black holes, the colossal anchors at the hearts of galaxies, form from the merging of numerous smaller black holes and massive stars within the densely packed central regions of young galaxies. Picture these bustling galactic cores, teeming with stellar giants and compact remnants, where gravity relentlessly pulls them together, gradually building a monstrous entity with a mass millions or even billions of times that of our sun. Another compelling theory posits that supermassive black holes may have originated from the direct collapse of massive gas clouds in the early universe. In those primordial cosmic epochs, vast clouds of hydrogen and helium, untamed and enormous, could have contracted under their own gravity without fragmenting into stars, plunging straight into a gravitational abyss to give birth to black holes of staggering mass. These nascent giants, born from the raw material of the cosmos, would then grow by devouring surrounding matter, gas, dust, stars, and by merging with other black holes, gradually swelling into the supermassive titans that dominate galactic centers today. Yet the story does not end there. Intermediate mass black holes, occupying the enigmatic mass range between the relatively modest stellar mass black holes and their gargantuan supermassive cousins, remain elusive phantoms in astrophysical research. These objects, thought to span hundreds to thousands of solar masses, may form through the merging of stellar mass black holes in densely packed star clusters, or through the direct collapse of extraordinarily massive stars in environments poor in heavy elements, known as low metallicity regions. This middle ground in black hole sizes could represent a crucial evolutionary link, an intermediate step bridging the gap between the birth of black holes from dying stars and the titanic supermassive behemoths that sculpt galaxies. Despite their elusive nature and the scarcity of confirmed detections, intermediate mass black holes hold the key to understanding the complex scaling and growth processes that shape black hole populations across the universe. Each type of black hole, stellar, intermediate, or supermassive, serves as a unique lens into the fundamental workings of the cosmos. They reveal secrets about stellar evolution, the life cycles of galaxies, and the mysterious force of gravity itself, which governs the dance of matter and energy on every scale. Their formation mechanisms, varied and intricate, underscore the dynamic, ever-changing nature of the cosmos, a universe filled with violent collisions, gravitational dramas, and ceaseless transformation. Black holes, in all their forms, distort space-time with their immense gravitational fields, bending the very fabric of reality. This phenomenon finds its theoretical foundation in Albert Einstein's general theory of relativity, formulated in the early 20th century. Einstein's groundbreaking insight revealed that gravity is not merely a force acting at a distance, but rather the manifestation of mass curving the geometry of space-time itself. Imagine space-time as a vast, two-dimensional rubber sheet. When a massive star rests on this sheet, it creates a gentle dip, a curve around which smaller objects orbit. But a black hole acts like placing an unimaginably dense and heavy object onto that sheet, creating a funnel-like well so deep and steep that it warps space-time to an extreme degree. The closer you move to this gravitational abyss, the steeper the curvature becomes, ultimately culminating in a singularity at the center, a point where space-time curvature grows infinitely intense and the known laws of physics cease to apply. This warping of space-time has profound, observable consequences. Light passing near a black hole no longer travels in a straight line, but bends along curved paths due to the intense space-time distortion, producing a phenomenon known as gravitational lensing. This cosmic optical effect can distort, magnify, or multiply images of distant stars and galaxies, allowing astronomers to detect objects otherwise invisible and revealing the presence of black holes indirectly through their gravitational fingerprints. Near the event horizon, the defining boundary of a black hole beyond which no information or matter can escape, the warping of time itself becomes evident. For a distant observer, time appears to slow dramatically near this boundary, a phenomenon known as gravitational time dilation. The closer an object gets to the event horizon, the slower its clock ticks relative to someone far away, an effect predicted by Einstein's relativity and confirmed through various experimental observations. Inside the event horizon, the escape velocity surpasses the speed of light, rendering any attempt to flee impossible. Matter and signals become trapped in an inescapable gravitational grip, spiraling inward toward the singularity. However, this dramatic process is often preceded by the formation of an accretion disk, matter swirling around the black hole at tremendous speeds, heating up to millions of degrees due to friction and gravitational forces. This superheated material emits intense X-rays and other forms of radiation, creating some of the most energetic phenomena observed in the universe. The event horizon itself stands as one of the universe's most mysterious and enigmatic boundaries. It marks a limit beyond which our conventional understanding of space, time, and physics begins to falter. One of the deepest puzzles associated with it is the information paradox. According to general relativity, information about matter that crosses the event horizon is lost to the singularity, seemingly erased from the fabric of the cosmos. Yet quantum mechanics, the framework governing the microscopic world, demands that information be preserved. This contradiction has sparked decades of debate and theoretical exploration, with some of the most famous proposals coming from Stephen Hawking, who introduced the concept of Hawking radiation. This quantum effect suggests that black holes can emit faint radiation and gradually evaporate, potentially releasing encoded information back into the universe, albeit in a scrambled form. Beyond these questions lies the nature of the singularity itself. This infinitely dense point defies explanation by current physical laws. General relativity breaks down, and the quest for a theory of quantum gravity, such as string theory or loop quantum gravity, aims to unify quantum mechanics with gravitational theory, offering hope to unlock the secrets of what truly happens inside black holes. These efforts represent some of the most ambitious and profound pursuits in modern theoretical physics, seeking to reveal the fundamental architecture of reality. The experience of falling into a black hole varies dramatically depending on its size. For a stellar mass black hole, the intense gradient in gravitational pull between different parts of an object, or even a person, would cause spaghettification, stretching and compressing it into a long, thin strand as it is torn apart on its way to the singularity. Conversely, near a supermassive black hole, the tidal forces at the event horizon are much gentler, allowing an object to cross this boundary without immediate destruction, though the ultimate fate inside remains equally grim. Black holes remain some of the most captivating and profound phenomena in the cosmos. They challenge our understanding of physics, confront us with paradoxes that push the limits of scientific knowledge, and illuminate the darkest corners of the universe with their powerful gravitational influence. From their mysterious formation and growth to the extreme effects they have on space-time and matter, black holes continue to inspire exploration and awe, inviting us to delve deeper into the universe's most profound enigmas. But this relative calm is fleeting, disappearing almost as quickly as it appears when journeying deeper into the enigmatic heart of a black hole. At its core lies a singularity, a phenomenon so extreme that it defies the very fabric of our understanding, a point where density soars beyond all conceivable limits, and the curvature of space and time warps to an infinite degree. According to Einstein's theory of general relativity, this singularity is where all matter and information swallowed by the black hole ultimately collapse, crushed into an infinitesimally small, infinitely dense point. Here, gravitational forces become immeasurable, stretching and twisting the cosmos itself. However, this traditional depiction confronts the boundaries of classical physics, forcing scientists to grapple with its implications and inherent contradictions. General relativity alone cannot fully describe what unfolds inside this cosmic abyss, prompting the search for a deeper, more unifying framework. This pursuit leads to the realm of quantum mechanics, the physics governing the microscopic world, which resists melding smoothly with the gravitational laws that dominate black holes. The result is an unresolved tension in physics, a call for a theory of quantum gravity that can seamlessly unite these conflicting domains. Among the leading candidates to bridge this gap are competing frameworks like string theory and loop quantum gravity. These ambitious theories strive to reconceptualize the singularity, replacing it with a quantum-structured core that is more comprehensible and consistent with the laws of quantum mechanics. In string theory, for instance, the fabric of reality is woven from tiny, vibrating strings whose interactions might dissolve the infinite densities predicted by classical theory. Loop quantum gravity, on the other hand, suggests that space itself is quantized, composed of discrete units that prevent the formation of true singularities. Beyond the mysteries at the core lies a perplexing enigma that has captivated physicists for decades. The fate of information that crosses the black hole's event horizon, the boundary beyond which nothing escapes. According to the laws of quantum mechanics, information can never be destroyed. It is conserved even as physical systems evolve. Yet classical interpretations of black holes imply that any information entering is irrevocably lost, consumed by the singularity, and erased from existence. This paradox, known as the information paradox, challenges our deepest understanding of physics and reality. In a groundbreaking proposal to resolve this contradiction, physicist Stephen Hawking suggested that black holes are not entirely black. Through quantum effects near the event horizon, black holes emit a faint glow now known as Hawking radiation. This radiation, emitted over incomprehensibly long cosmic timescales, could cause black holes to gradually evaporate, releasing energy and perhaps information back into the universe, although likely in a transformed and highly scrambled form. This elegant idea, while widely influential, remains the subject of intense debate, ongoing research, and refinement as scientists work tirelessly to reconcile the divergent principles of quantum mechanics and general relativity. While the intricate processes within black holes remain largely theoretical and shrouded in mystery, contemporary models depict them as stages for extraordinary gravitational phenomena intertwined with subtle quantum effects. These cosmic enigmas are more than mere cosmic vacuums. They are crucibles where the known laws of physics are pushed to their extremes, perhaps even revealing entirely new realms of physical reality beyond our current scientific horizons. As observational technology improves and theoretical advances continue, humanity may edge closer to unraveling these profound mysteries, forever altering our understanding of space, time, and existence itself. Black holes do not merely lie in wait. They actively consume matter and energy from their surroundings through a process called accretion. This mechanism, driven by gravity, transforms seemingly empty regions of space into intense zones of activity and luminous phenomena. Accretion plays a vital role in the growth and evolution of black holes, enabling them to gather mass from nearby stars, gas clouds, dust, and even light. As matter ventures too close, it becomes ensnared by the black hole's overwhelming gravitational pull, caught in an inescapable dance around the abyss. Instead of plunging directly into the black hole, this infalling material often forms a spectacular accretion disk, a swirling, flattened ring of matter spiraling inward at breakneck speeds. Within this disk, matter collides and rubs against itself, creating friction and compressing gas to such extremes that temperatures soar to millions of degrees. These superheated conditions cause the accretion disk to emit a broad spectrum of radiation, especially in X-rays, which astronomers detect as telltale signatures revealing the presence and behavior of otherwise invisible black holes. The gravitational gradient near the black hole is so intense that matter within disks steadily loses angular momentum and energy, causing it to spiral ever closer to the event horizon. This gradual inward journey is marked by extreme conditions and violent interactions, making the region around the black hole a cosmic laboratory for some of the universe's most energetic and exotic phenomena. In this way, black holes shape and influence their cosmic neighborhoods, transforming the void around them into regions bustling with activity, light, and dramatic astrophysical processes. The dance of matter within the accretion disk is a story of destruction and creation, of chaos forged into luminous beauty under the relentless grip of gravity. It is a window into the hidden workings of black holes, providing astronomers with clues to their mass, spin, and influence on the cosmos. As we peer into these swirling maelstroms, we glimpse the immense power contained within these cosmic giants and the frontier of knowledge they represent. A frontier where the known laws of physics meet the unknown, and where the mysteries of the universe beckon humanity to explore further and deeper than ever before. As the matter approaches the event horizon, the realm where the very fabric of space-time bends into unimaginable extremes, relativistic effects surge in their significance, reshaping everything in their grasp. The radiation emitted from this boundary zone undergoes a profound transformation, subjected to the phenomenon known as gravitational redshift. This process stretches light waves to longer wavelengths, a direct manifestation of Einstein's revolutionary theory of general relativity. The gravitational redshift is not merely a theoretical curiosity. It stands as a powerful observational beacon, a cosmic clue that illuminates the behaviors and properties of matter trapped within these extreme gravitational crucibles. And yet, black holes do more than passively consume. In binary systems, they can actively siphon material directly from a neighboring companion star. When such a star expands and fills its Roche lobe, the region where its gravity competes with that of the black hole, matter begins to flow inexorably through the inner Lagrange point, forming an accretion stream that plunges toward the black hole. This flow creates a luminous accretion disk, a swirling vortex of gas and dust that heats to staggering temperatures under immense gravitational and frictional forces. This disk becomes a furnace of energetic radiation and dramatic outbursts, radiating energy detectable across the vast expanses of space. However, this process is far from perfectly efficient. A significant fraction of the material drawn toward the black hole is violently expelled back into space as powerful jets and winds. These jets, often observed in the supermassive black holes anchoring the centers of galaxies, propel matter at speeds approaching that of light, shooting out in narrow beams that extend thousands or even millions of light years. Known as relativistic jets, these streams demonstrate the staggering power black holes exert on their surroundings, sculpting the cosmic landscape. The interaction of these jets with the interstellar and intergalactic medium, the feedback mechanism, plays a crucial role in regulating star formation, gas distribution, and the overall evolution of galaxies. Because of these feedback processes, black holes transcend their reputation as mere cosmic vacuum cleaners. They become architects of their environments. Through the interplay of gravitationally driven accretion, high-energy radiation, and relativistic jets, black holes grow, influence, and transform the galaxies around them. This transformation is evident in the way jets can suppress or trigger bursts of star formation, alter the morphology of galactic structures, and even shape the large-scale distribution of matter in the cosmos. Despite their immense gravitational pull, black holes offer glimpses into their enigmatic nature through these energetic emissions, providing windows into the extreme physical conditions near their event horizons. The supermassive black holes that reside at the centers of most galaxies, including our own Milky Way, are among the most fascinating and mysterious objects in the universe. They challenge our understanding at every turn, from their origins to their profound roles in galactic evolution. How do these cosmic giants form and grow to sizes ranging from millions to billions of solar masses? Two dominant theories attempt to answer this question. One theory posits that supermassive black holes originated from the direct collapse of massive gas clouds in the primordial universe, circumventing the usual star formation phase and rapidly forming colossal black holes. The other suggests a more gradual growth from smaller seed black holes, which themselves formed from massive stars or early star clusters, slowly accumulating mass through the accretion of gas and dust and merging with other black holes. Yet, neither theory completely explains the presence of enormous black holes observed mere hundreds of millions of years after the Big Bang, leaving their early formation an open puzzle. The relationship between these supermassive black holes and their host galaxies deepens the mystery. Observations reveal a tight correlation between the mass of the black hole and the properties of the galaxy's central bulge, such as the velocity dispersion of stars, known as the M-sigma relation. This suggests a remarkable coevolution, where galaxies and their central black holes grow in tandem, influencing each other's development. Yet the underlying mechanisms driving this symbiotic growth remain elusive. Supermassive black holes profoundly impact their environments primarily through energetic feedback processes, jets and radiation emitted from their accretion disks. These emissions can regulate star formation by either suppressing the cooling and collapse of gas or triggering new bursts of stellar birth. They redistribute gas, sculpt galactic morphology, and drive large-scale galactic winds. Understanding these feedback mechanisms is key to unlocking the broader narrative of galaxy formation and evolution. Moreover, the accretion processes near supermassive black holes defy simple explanations. The physics of matter swirling in the cauldron of extreme gravity and intense electromagnetic fields remains one of astrophysics' most challenging frontiers. How some material escapes as relativistic jets, launched with near-light speeds, while other matter crosses the event horizon, still fascinates scientists and fuels ongoing theoretical and observational research. Breakthroughs such as the Event Horizon Telescope, EHT, have revolutionized our view, offering humanity its first direct image of a black hole's event horizon in 2019, the shadow cast by the supermassive black hole in galaxy M87. This landmark achievement came from a global network of radio telescopes working in harmony as a planet-sized observatory. Through such observations, scientists probed the bending of light and intense radiation at the edge of the event horizon, testing the predictions of general relativity in regimes once thought unreachable. Yet black holes remain invisible in the traditional sense. They emit no light themselves. To study them, scientists rely on ingenious indirect methods. Observing X-rays emitted by the hot accretion disks, detecting gravitational influences on nearby stars and gas clouds, measuring gravitational lensing effects that distort the light of background galaxies, and now detecting gravitational waves from merging black holes all piece together a picture of these cosmic enigmas. Gravitational waves, first predicted by Einstein and detected by the LIGO and Virgo observatories in 2015, opened a new window onto black hole dynamics. These ripples in spacetime generated by accelerating massive objects like merging black holes provide direct insight into their masses, spins, and the cataclysmic processes governing their mergers. The merging of black hole binaries is not only a spectacular cosmic event, but also a critical factor in understanding how supermassive black holes grow and influence their galaxies. The Event Horizon Telescope's groundbreaking imaging techniques and gravitational wave observatories have combined to transform the study of black holes from theoretical speculation into a rich empirical science. They reveal that black holes, though dark and elusive, are vibrant engines of cosmic change, shaping the evolution of galaxies and the large-scale structure of the universe. Hawking radiation, theorized by physicist Stephen Hawking in 1974, adds another layer of complexity. It bridges the domains of quantum mechanics and general relativity by suggesting that black holes are not completely black but emit faint radiation due to quantum effects near the event horizon. Though not yet observed directly, this phenomenon challenges traditional notions and hints at deep connections between gravity, quantum theory, and thermodynamics. In sum, black holes, once relegated to the realm of pure theory, have emerged as fundamental actors in the cosmic drama. From swallowing matter and warping space-time to launching jets that sculpt galaxies, they are not merely passive voids, but dynamic, energetic engines influencing everything from the smallest stellar neighborhoods to the grandest scales of the cosmos. The quest to understand them continues to push the boundaries of physics, astronomy, and technology, promising new discoveries that will reshape our understanding of the universe itself. But emit radiation, this groundbreaking concept reshapes everything we thought we knew about black holes and the fabric of reality itself. Hawking radiation, named after the legendary physicist Stephen Hawking, arises from the strange, often counterintuitive world of quantum field theory when it meets the warped space-time surrounding a black hole. Imagine, in the seemingly empty vacuum of space, Pairs of particles and antiparticles spontaneously flicker into existence, only to vanish moments later. This is not just idle quantum whimsy, it is a fundamental feature of the universe at the smallest scales. Near the event horizon of a black hole, the point of no return, the immense gravitational pull disrupts this delicate dance. Sometimes this gravitational force separates these particle pairs before they can annihilate each other. One member of the pair slips beyond the event horizon, swallowed forever by the black hole's insatiable maw, while its partner escapes, shooting out into space as what appears to be radiation emitted directly from the black hole itself. This escaping radiation, known as Hawking radiation, is a profound departure from the traditional view of black holes as objects that swallow everything and give nothing back. Instead, black holes are dynamic, slowly losing mass and energy over unimaginably long timescales. This evaporation process, though imperceptibly slow for massive black holes, is faster for smaller ones. It suggests a universe where black holes are not eternal prisons, but ephemeral entities that could eventually vanish entirely. Consider primordial black holes, relics from the fiery birth of the cosmos in the Big Bang, which might have already evaporated or be nearing their final demise, leaving behind faint yet detectable signatures for astronomers to uncover. The implications of Hawking radiation ripple through the deepest mysteries of physics, especially the infamous black hole information paradox. Classical physics dictates that any information about the matter falling into a black hole disappears forever, trapped in the singularity's abyss. However, quantum mechanics, a theory that governs the microscopic world, insists that information cannot simply vanish. Here, Hawking radiation offers a tantalizing solution. Over vast epochs, the radiation emitted might encode the lost information, preserving the universe's ledger of reality in an intricate quantum script. Though the precise mechanism remains elusive, this notion has fueled intense debate and research, bridging gaps between competing ideas and forcing a reevaluation of how we understand the flow of information through the cosmos. Moreover, Hawking radiation is a critical nexus between the two towering pillars of modern physics, quantum mechanics and general relativity. These frameworks govern vastly different realms, the incredibly small and the unimaginably massive, and have historically resisted unification. Hawking's insight reveals that quantum effects are not confined to the minuscule, but can manifest in the colossal gravitational fields of black holes, hinting at a unified theory of quantum gravity. Such a theory, the holy grail of physics, would weave together all fundamental forces and particles into a single coherent framework, unlocking secrets that have eluded scientists for decades. This phenomenon is not merely a theoretical curiosity, but a cornerstone that challenges and extends our understanding of black holes, cosmic entities often portrayed as the ultimate destroyers. Instead, they emerge as complex systems governed by deep and subtle principles. Hawking radiation reshapes these titans of gravity into transient phenomena that influence the evolution of the universe, possibly even contributing to the fundamental makeup of reality itself. Beyond pure theory, the strange properties of black holes ignite bold speculations about futuristic technologies and space exploration. The extreme gravitational and energetic environments of black holes might one day be harnessed to revolutionize energy production or provide unprecedented propulsion mechanisms for interstellar travel. One especially captivating idea involves rotating or Kerr black holes, which, according to Einstein's field equations, possess regions where space-time itself is dragged around at dizzying speeds. Within these ergospheres, space and time become malleable in ways that defy common intuition. Some theoretical constructs suggest that such black holes could act as cosmic shortcuts, wormholes, bridging vast distances in space and even time, potentially opening portals for rapid travel across the universe. Though these remain speculative and beyond our current technological reach, they inspire visions of a future where humanity might explore the cosmos not by slow journeys through conventional space, but by riding the ripples and tunnels shaped by the most extreme forces in existence. Hawking radiation's discovery and the principles it reveals continue to energize scientific inquiry, pushing the boundaries of knowledge and inviting humanity to reconsider the nature of existence, information, and the universe's ultimate fate. In the dance between quantum mechanics and gravity, between the infinitesimal and the infinite, we glimpse the contours of a deeper truth, one that may someday unlock the full mysteries of space, time, and reality itself. If traversable wormholes exist, then humanity's dream of instantaneous cosmic travel could transcend the boundaries of fiction and become a tangible reality. Imagine a spacecraft entering one mouth of a wormhole and emerging light years away at the other end, circumventing the colossal distances that ordinarily take years or centuries to cross. This concept, though deeply rooted in speculative physics and currently far beyond our technological grasp, fires the imagination and challenges us to rethink the very structure of space and time. At its core, the wormhole concept tantalizes us with the idea that space-time might be warped and connected in ways we do not yet fully understand. These hypothetical passages, predicted by solutions to Einstein's field equations in general relativity, would act as shortcuts through the cosmic web. Yet, the journey through a wormhole would not be simple or safe. The gravitational and tidal forces near the mouths of wormholes, often linked to black holes or exotic matter, pose tremendous engineering challenges. Developing technology capable of navigating these intense environments, protecting the delicate instruments, and ensuring the survival of any occupants remains a daunting, if not near impossible feat at present. Parallel to these fantastical visions of travel lie more grounded prospects centered on black holes, those enigmatic, compact regions of space-time with gravity so intense that nothing, not even light, can escape. Black holes, often perceived as cosmic vacuum cleaners or destructive monsters, might instead be harnessed as sources of immense energy. The Penrose process, theorized by physicist Roger Penrose in the late 1960s, illuminates one pathway. Within the ergosphere, a swirling region just outside a rotating black hole's event horizon, particles could theoretically be split apart, one swallowed by the black hole, the other escaping with more energy than it originally possessed. This process effectively taps into the black hole's rotational energy, opening up tantalizing possibilities for energy extraction on scales far beyond anything currently achievable by humanity. Meanwhile, Stephen Hawking's groundbreaking discovery of black hole radiation, now known as Hawking radiation, adds another dimension to these possibilities. Hawking radiation suggests that black holes are not entirely black. They emit particles as they slowly evaporate over incredibly long timescales. Harnessing this radiation could, in theory, provide a continuous and steady stream of energy, though the practical means of capturing such faint emissions remain elusive. More radical still are proposals involving microscopic or quantum black holes. These tiny black holes would evaporate much faster than their massive counterparts, releasing intense bursts of energy that could be exploited, perhaps generated within particle accelerators or other highly advanced devices. However, the technological and safety challenges associated with creating and controlling such exotic objects are immense, and the notion remains firmly in the realm of theory and speculation. Expanding beyond energy extraction, black holes might serve as the backbone of futuristic propulsion systems capable of interstellar journeys. One speculative concept is the black hole bomb, which involves encasing a black hole inside a massive reflective shell designed to amplify the energy extracted from its rotation. The amplified energy could be directed to generate propulsion, potentially producing an unprecedented thrust to accelerate spacecraft to relativistic speeds. Science fiction has long embraced these ideas, with black hole starships envisioned as vessels powered by the intense energies black holes offer, potentially enabling human travel to the farthest reaches of our galaxy and beyond. Despite their current theoretical status, ongoing advancements in physics, particularly in quantum mechanics, general relativity, and high-energy particle physics, may gradually transform these ideas from science fiction into science fact. Understanding and harnessing black holes' energies could revolutionize how we power civilization and propel humanity into an era of interstellar exploration. These mysterious cosmic phenomena, once solely objects of curiosity and fear, might become the keys to unlocking extraordinary new capabilities in energy production and space travel. The recent groundbreaking observations of black hole mergers have dramatically expanded our comprehension of the universe's dynamic and violent nature. The detection of gravitational waves by the Laser Interferometer Gravitational Wave Observatory, LIGO, and the Virgo collaboration marked a pivotal moment in astrophysics. These ripples in the fabric of space-time, generated by colliding black holes, offer direct evidence of phenomena that were once purely theoretical. Often involving black holes with masses several times that of our Sun, these mergers release stupendous amounts of energy, sometimes equivalent to converting several solar masses directly into gravitational waves in fractions of a second. These observations have not only confirmed the existence of intermediate mass black holes, filling a previously mysterious gap between stellar mass black holes and the supermassive giants anchoring galaxies, but also opened new avenues to test the limits of Einstein's theory of general relativity. The mergers act as natural laboratories, subjecting the laws of physics to extreme conditions otherwise impossible to replicate. Intriguingly, recent data suggests that the aftermath of some mergers may defy the expected ring-down phase, where the newly formed black hole settles into a stable state. These anomalies hint at the tantalizing possibility that exotic, unknown physics could be at play, challenging our current understanding and inviting deeper exploration. Through the lens of these discoveries, black holes reveal themselves not merely as destructive forces, but as pivotal actors in the cosmic drama, offering clues about the universe's origins, evolution, and ultimate fate. They beckon humanity to push the boundaries of knowledge and technology, inspiring bold ideas that could redefine our place in the cosmos. If traversable wormholes remain a dream for now, the relentless pursuit of knowledge about black holes and their astounding properties continues to fuel humanity's journey toward unlocking the deepest secrets of space and time. Whether through harnessing energy, advancing propulsion technology, or decoding the messages carried by gravitational waves, the universe's most mysterious objects challenge us to imagine a future where the cosmos is not a distant frontier, but an accessible domain awaiting exploration. Additionally, these extraordinary cosmic events hold the key to unraveling the enigmatic mystery of how the universe forges its heaviest elements. The extreme gravitational interactions unleashed in these cataclysmic phenomena ignite high-energy processes that are believed to be the crucibles where elements heavier than iron are born, an intricate puzzle that traditional stellar nucleosynthesis alone struggles to solve fully. Imagine colossal stellar collisions or neutron-star mergers where unimaginable forces collide, generating conditions so intense that new atomic nuclei are synthesized in bursts of neutron-rich material. Such events do not just hint but strongly suggest that the cosmos's heaviest building blocks, gold, platinum, uranium, originate from these violent, energetic crucibles. Continuous observation and meticulous analysis of these cosmic spectacles provide scientists with an unprecedented window into some of the universe's deepest secrets. Each detected gravitational wave or gamma-ray burst sends ripples through our understanding of the very fabric of reality, reshaping our grasp on how matter evolves and cycles through space and time. The very existence of these heavy elements scattered across the cosmos serves as a testament to the intricate, violent dance of gravity and nuclear physics playing out across the vastness of space. But alongside this tale of elemental genesis lies another profound cosmic enigma: dark matter. This elusive, mysterious substance remains invisible to our most sophisticated telescopes because it neither emits, nor reflects, nor absorbs light. It exists beyond the reach of electromagnetic radiation, hiding in the shadows of the cosmos. Yet its presence is undeniable. Dark matter exerts a powerful gravitational influence that governs the motions of galaxies and entire clusters of galaxies, bending the paths of stars and shaping the structure of the universe itself. In fact, approximately 85% of the universe's total mass is believed to consist of this invisible substance, dwarfing the ordinary matter, from glowing stars to rocky planets that forms the visible cosmos we know. This realization places humanity's familiar matter as a mere speck, a minor fraction amid the vast, dark ocean of the universe's true mass. The discovery of dark matter traces back nearly a century to the pioneering observations of Swiss astronomer Fritz Zwicky in the 1930s. Studying the Coma cluster of galaxies, Zwicky found that these galaxies moved with such speed that the visible matter alone could not hold them together by gravity. He proposed the existence of dunkle materie, or dark matter, a hidden mass exerting gravitational force without shining or glowing itself. This radical idea found further compelling support decades later, in the 1970s, when astronomer Vera Rubin meticulously measured the rotation curves of spiral galaxies. Rubin discovered that stars near the outer edges of galaxies spun around just as fast as those near the dense centers, a motion that visible matter alone could never explain. This baffling uniformity indicated a massive, unseen presence enveloping galaxies, binding them with gravity and hinting at the true dominance of dark matter. Modern science continues to peel back layers of this cosmic mystery through technological marvels, such as the Hubble Space Telescope. Though incapable of detecting dark matter directly, Hubble and other observatories reveal its influence via gravitational lensing, an extraordinary phenomenon where the light from distant galaxies bends and distorts as it passes through the invisible mass between us and those galaxies. These cosmic lenses map the dark matter's invisible scaffolding, revealing a vast web that shapes the universe on the grandest scales. Despite the absence of direct detection, a multitude of experiments are in progress worldwide, hunting for the fundamental particles that might compose dark matter. Theories abound, from WIMPs, weakly interacting massive particles that barely engage with normal matter, to axions, hypothetical particles that could permeate space unseen. Unlocking the nature of dark matter stands as one of the most tantalizing frontiers in cosmology, promising to revolutionize our understanding of the universe's structure, formation, and ultimate fate. Dark matter's pivotal role is undeniable. It sculpts the cosmos at every scale. From the earliest moments after the Big Bang, dark matter acted as an invisible scaffold, its gravity pulling ordinary matter into clumps that eventually formed stars, galaxies, and clusters. Without dark matter's gravitational anchor, the gas clouds needed to ignite stars would have remained too diffuse to collapse, leaving the universe a far emptier place. This cosmic architecture manifests today as the vast cosmic web, an immense, intricate network of filaments composed primarily of dark matter, stretching across millions of light years. These filaments connect galaxies and clusters, channeling gas and matter along their lengths, guiding the formation and distribution of the luminous structures we observe. On smaller scales, dark matter influences the orbits of stars within galaxies, the dynamics of galactic mergers, and the behavior of intergalactic gas, confirming its omnipresence and profound influence throughout the universe. Every discovery about dark matter and heavy element formation weaves into a larger narrative, one where invisible forces and rare cosmic events combine to shape the universe in ways both beautiful and bewildering. Our journey to understand these phenomena is not just a scientific quest. It is an exploration of the very essence of existence, a dive into the unknown realms where matter, gravity, and time converge to create the cosmos as we perceive it. And so, the enigma of dark matter begins with its profound influence on the very fabric and dynamics of galaxies. Observations of spiral galaxies have unveiled a cosmic mystery that defies expectations, rooted solely in the visible universe. When astronomers peer into the rotational behavior of stars nestled at the outer edges of these galaxies, they encounter an astonishing phenomenon. These distant stars whirl at speeds far greater than what the mass of luminous matter could possibly dictate. This striking discrepancy points toward an invisible, pervasive entity, dark matter, that extends far beyond the visible edges of galaxies, forming an unseen halo of gravitational influence. This hidden halo, a vast cloak of dark matter, acts as a cosmic stabilizer. Without it, the rapid rotational velocities of stars would fling galaxies apart, tearing them asunder under centrifugal forces. The presence of this unseen mass ensures the structural integrity and continued cohesion of these grand celestial systems. Dark matter is not merely a passive backdrop. It is a fundamental architect in the formation, structural evolution, and ultimate destiny of the universe itself. Its shadowy properties and interactions remain one of the most profound mysteries confronting cosmologists, a quest that drives much of modern astrophysical research. As we delve deeper into understanding dark matter, each revelation serves as a gateway to broader insights into cosmic structure evolution and the universe's fundamental makeup. The implications stretch far beyond mere astrophysics, potentially unlocking new realms of physics that transcend the boundaries of current scientific paradigms. Detecting this elusive matter, however, remains an extraordinary scientific challenge. By its very nature, dark matter neither emits nor absorbs electromagnetic radiation. No light, no heat, no radio waves. This invisibility forces scientists to rely on indirect evidence and sophisticated inference techniques. The gravitational fingerprint of dark matter is the primary clue astronomers follow. By observing how dark matter's gravity warps space-time and influences visible matter, researchers construct a detailed map of its presence. One of the most powerful tools in this endeavor is gravitational lensing. This phenomenon occurs when light from distant galaxies bends as it passes through the intense gravitational fields of massive galaxy clusters, which include substantial dark matter components. The bending of light distorts and magnifies the images of these background galaxies, creating arcs, rings, and multiple images. By meticulously analyzing these distortions, astronomers can deduce the distribution and quantity of dark matter within clusters. Time and again, lensing reveals mass far exceeding what is observable through luminous matter alone, a testament to dark matter's pervasive reach. The study of galactic rotation curves, pioneered by astronomers such as Vera Rubin, further solidifies the case for dark matter. Rubin's meticulous measurements revealed that stars in the outer reaches of spiral galaxies revolve at nearly constant speeds, defying the drop-off predicted by Newtonian dynamics applied to visible matter. This uniform rotational velocity implies a massive, invisible halo enveloping galaxies, exerting gravitational forces strong enough to maintain such rapid stellar orbits. On the experimental front, the hunt for dark matter particles has taken root deep underground in shielded laboratories designed to minimize interference from cosmic rays and other background noise. These detectors, often utilizing cryogenic technology or noble liquid targets such as xenon, aim to capture the faint whispers of dark matter interactions. When a dark matter particle hypothetically collides with an atomic nucleus inside these detectors, it may release a tiny burst of energy in the form of scintillation light or heat, detectable by highly sensitive instruments. Experiments like the Large Underground Xenon, LUX, and Xenon NT represent the cutting edge of this approach, pushing the boundaries of detection sensitivity to unprecedented levels. Particle accelerators such as the Large Hadron Collider, LHC, at CERN provide a complementary approach to the dark matter mystery. By accelerating and colliding protons at extraordinarily high energies, physicists hope to generate dark matter particles transiently. These particles would escape the detectors, leaving behind subtle signatures in the form of missing energy and momentum in particle collision events. While no conclusive detection has yet emerged from these efforts, the data narrows the parameter space where dark matter might reside. Despite the absence of direct observation, the cumulative evidence from astrophysical phenomena, gravitational lensing, rotation curves, and laboratory experiments forms a compelling mosaic that affirms dark matter's existence. The pursuit to detect it directly remains one of the most captivating and challenging frontiers in cosmology. Success would herald a new era of understanding, fundamentally altering our conception of the universe. The very composition of dark matter constitutes one of cosmology's most tantalizing puzzles. Several leading theoretical frameworks strive to explain its elusive nature. Among the most prominent is the hypothesis that dark matter consists of weakly interacting massive particles, or WIMPs. These hypothetical particles are believed to have been produced in the primordial fireball of the early universe in vast quantities. WIMPs are compelling candidates because their weak interactions with normal matter and electromagnetic radiation align with observed cosmic phenomena and fit neatly into extensions of the standard model of particle physics. Notably, theories involving supersymmetry predict the existence of such particles, lending theoretical support to this concept. Another prominent contender in the dark matter arena includes axions, ultralight hypothetical particles arising from quantum chromodynamics. Axions, if they exist, would possess properties that allow them to evade detection through traditional means, yet exert gravitational influence on cosmic scales. The search for axions involves innovative experimental setups like resonant cavities and magnetic fields designed to coax these elusive particles into detectable signals. Further speculative candidates include sterile neutrinos, hypothetical neutrinos that do not interact via the weak nuclear force, making them even more elusive than their known counterparts. These neutrinos could contribute to the dark matter halo and influence galaxy formation. As these theories proliferate and experiments advance, the scientific community remains poised at the brink of a profound discovery. Each new dataset, every refined measurement, and all theoretical advances bring us closer to unveiling the nature of dark matter. The pursuit is not merely academic, it touches on the very essence of existence, the unseen framework holding the universe together. The quest to understand dark matter is a journey to the heart of cosmic mystery, one that may redefine physics, reshape cosmology, and deepen humanity's grasp of the cosmos. This story of dark matter is a saga of curiosity, persistence, and the relentless human drive to illuminate the unknown. It is the saga of how we seek to comprehend a universe that is, in large part, invisible to us, yet fundamentally shapes everything we observe. The shadows cast by dark matter beckon us to explore deeper, to push beyond the limits of sight and knowledge, and to embrace the mysteries of the cosmos with open minds and unyielding resolve. And so it began, the quest to unravel one of the greatest mysteries haunting modern physics, the elusive nature of dark matter and dark energy, entities that shape the cosmos yet remain stubbornly invisible. In the late 1970s, a novel particle entered the theoretical arena, proposed as a solution to a deep problem in quantum chromodynamics known as the strong CP problem. This hypothetical particle was named the axion. Axions, if they exist, would be incredibly light, possessing masses so tiny that their presence would barely ripple the fabric of ordinary matter. Their interactions with the familiar particles that compose stars, planets, and people would be extraordinarily feeble, making them incredibly difficult to detect directly. Yet, despite their ghostly subtlety, axions might have been abundantly produced in the fiery crucible of the early universe, emerging in quantities sufficient to account for the mysterious missing mass we call dark matter. This invisible form of matter does not emit, absorb, or reflect light, yet its gravitational fingerprint is unmistakable, holding galaxies together and sculpting the vast cosmic web of structure. As scientists forged ahead to find signs of axions, experiments like the Axion Dark Matter Experiment, ADMX, began the painstaking search. ADMX employs ultra-sensitive microwave cavities, chilling environments near absolute zero, and powerful magnetic fields, all designed to detect the faint whispers axions might leave behind as they subtly transform into photons. But the axion is only one player in the cosmic mystery. Another contender in the dark matter saga is the sterile neutrino. Unlike the known active neutrinos, which engage in the weak nuclear force, the feeblest of the fundamental interactions that can still be detected, sterile neutrinos would be even more aloof, interacting only through gravity. Their hypothetical existence would introduce a new form of neutrino that slips through ordinary matter unnoticed. Their masses, potentially heavier than their active cousins, might illuminate perplexing aspects of dark matter, potentially influencing the formation and clustering of galaxies across cosmic time. Detecting sterile neutrinos would transform our understanding of particle physics and cosmology, opening doors to realms hitherto unexplored. Beyond particles, some theories delve into the realm of primordial black holes, an exotic possibility that dark matter might be composed not of particles, but of compact objects born in the early universe. These black holes, forged in the extreme density fluctuations mere moments after the Big Bang, could persist as dark matter, exerting gravitational influence across vast cosmic distances. Though challenging to spot, their presence could be inferred through gravitational lensing effects or subtle perturbations in the cosmic microwave background radiation. The primordial black hole hypothesis weaves together cosmology and general relativity, hinting at a universe where dark matter may be far more varied than simple particle candidates. Meanwhile, an entirely different line of thought proposes that dark matter may not exist as a substance at all. Instead, it suggests that our very understanding of gravity needs revision on cosmic scales. Modified Newtonian dynamics, or MOND, posits alterations to Newton's laws to account for the anomalous rotation curves of galaxies without invoking unseen matter. While elegant in its simplicity, Mons struggles to match the full range of cosmological observations as effectively as particle-based dark matter theories. Still, it remains a provocative alternative, a reminder that the laws we take for granted may yet conceal deeper truths. Dark matter's enigmatic partner in cosmic drama is dark energy, a force that exerts a profoundly different influence. Discovered in the late 1990s through meticulous observations of distant Type Ia supernova, dark energy appears to drive the accelerated expansion of the universe. While dark matter clusters and binds galaxies through gravity, dark energy pushes the cosmos apart, acting almost like an anti-gravity force. It permeates all of space uniformly, shaping the universe's geometry and governing its destiny. Its nature remains elusive, modeled variously as Einstein's cosmological constant, a vacuum energy intrinsic to space itself, or more dynamic phenomena like quintessence, fields that evolve over time. Together, dark matter and dark energy constitute approximately 95% of the total mass energy content of the universe. Dark energy around 70%, dark matter about 25%, leaving a mere 5% to the ordinary matter that makes up stars, planets, and life. This dominance makes their study essential for understanding the cosmos from its earliest moments to its far future. Dark matter's invisible mass binds galaxies and clusters, enabling them to resist the centrifugal forces generated by their rapid rotation. Without it, stars at the outer edges of galaxies would fly off into the void. Dark energy, by contrast, governs the ultimate fate of the cosmos, driving an expansion that accelerates relentlessly. This expansion stretches the fabric of space, increasing the distances between galaxies at an ever-growing pace, leading to a future universe that may be cold, dark, and diffuse, devoid of the clustered structures that mark its past. To probe these shadows of the universe, scientists harness a myriad of observational tools. Measurements of the cosmic microwave background, the afterglow of the Big Bang, reveal the early distribution of matter and energy. Large-scale galaxy surveys map the three-dimensional distribution of galaxies, unveiling the cosmic web's intricate patterns. Gravitational lensing studies exploit the bending of light around massive objects, offering indirect glimpses of dark matter's presence. Together, these methods stitch together a picture of a universe shaped by unseen forces. Yet, many questions remain. What precisely constitutes dark matter? Are axions or sterile neutrinos the true dark matter particles, or does the universe's dark sector defy all current particle physics? What is the fundamental nature of dark energy? Will the accelerated expansion continue indefinitely, or will new physics emerge to alter cosmic destiny? These questions drive an ongoing scientific odyssey, a quest as much about the future of cosmology as it is about the deepest workings of nature. Understanding these mysterious components promises to unlock new realms of physics, potentially revolutionizing our conception of reality itself. The story of dark matter and dark energy is still unfolding, inviting us to peer ever deeper into the cosmic abyss where the known meets the unknown, and where the universe reveals its profoundest secrets. But we're accelerating in their recession, implying that some unknown force was driving galaxies apart faster and faster, defying the natural expectation of a universe gradually slowing down due to gravitational attraction. This mysterious driver of cosmic acceleration has become known as dark energy, a term that encapsulates both our ignorance and our awe at the universe's unseen forces. Its role in the accelerated expansion of the cosmos is one of the most profound revelations of modern astrophysics, and it fundamentally reshapes our understanding of space-time itself. Unlike ordinary matter, which gravitates in clusters into galaxies and stars, and unlike dark matter, which, although invisible, also exerts gravitational pull and forms cosmic scaffolding, dark energy operates differently. It does not clump. It does not attract. It repels. It stretches the very fabric of the universe in all directions with a force that is subtle, silent, and relentless. Dark energy does not dilute as space grows. Instead, it maintains a constant energy density, woven uniformly into the structure of the cosmos. It is omnipresent, unchanging, and yet it drives change on the grandest scale imaginable. This behavior can be elegantly expressed through Einstein's general theory of relativity. Embedded in his field equations is a term known as the cosmological constant, symbolized by the Greek letter lel, lambda. Initially introduced by Einstein to maintain a static universe, a view we now know to be incorrect, lambda was later discarded by him, only to be revived decades later as the key to understanding the accelerating universe. Today, lambda represents a form of vacuum energy, a residual energy inherent in space itself. It is this vacuum energy, this dark energy, that appears to be fueling the expansion of the universe, not just sustaining it, but accelerating it. As the universe ages and its matter becomes more thinly spread, the repulsive influence of dark energy becomes more dominant. Matter, both visible and dark, used to control the dynamics of cosmic evolution. Gravity drew structures together, galaxies merged, clusters formed. But now the tide has turned. The expansion rate is no longer slowing, it is quickening. Space-time itself is being pulled apart, the distances between galaxies growing not just steadily, but exponentially. Today, cosmologists estimate that dark energy constitutes roughly 70% of the total energy budget of the universe. The rest is divided between dark matter, about 25%, and ordinary matter, a mere 5%, everything we can see, touch, and interact with. This overwhelming dominance of dark energy presents an unsettling picture of the universe's future, one that is increasingly cold, dark, and isolated. Over the coming billions of years, the accelerated expansion will continue to drive galaxies away from each other. Eventually, many of them will move beyond our cosmic event horizon, slipping into invisibility. Their light will never reach us again. In this big freeze scenario, star formation ceases as galaxies grow increasingly barren. Existing stars will burn out one by one, and the cosmos will cool toward absolute zero. Thermodynamic activity will grind to a halt. A universe once teeming with light and motion will fade into a silent, frigid darkness. But there is a darker prospect still, the Big Rip. In this theoretical model, dark energy does not remain constant but increases in strength over time. If its repulsive force intensifies beyond a certain threshold, it could overcome all other forces, even those binding atoms and subatomic particles. Galaxies would be torn apart, followed by stars, planets, and eventually matter itself. Molecules, atoms, and finally the fabric of space-time could be unraveled. The universe would not merely die, it would be ripped into non-existence. To comprehend these possible fates, scientists are undertaking monumental efforts to understand the nature of dark energy. They analyze the cosmic microwave background, CMB, the faint afterglow of the Big Bang, which offers a snapshot of the universe just 380,000 years after its birth. By studying the tiny temperature fluctuations in the CMB, recorded with extraordinary precision by missions like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite, cosmologists can infer the composition, geometry, and expansion history of the universe. Another powerful tool lies in the observation of distant Type Ia supernovae, stellar explosions that occur with remarkable consistency in luminosity. These supernovae serve as standard candles for measuring vast cosmic distances. In the late 1990s, two independent research teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, used these stellar beacons to measure how fast galaxies were moving away. What they found shocked the scientific world. The supernovae were dimmer than expected. The light had traveled farther through a universe that had expanded more rapidly than anticipated. This was the first direct evidence that the universe's expansion was accelerating, a discovery that earned the teams the 2011 Nobel Prize in Physics. Yet another crucial method for probing dark energy is gravitational lensing, where light from distant galaxies is bent by the gravity of massive structures between them and the observer. By analyzing these lensing effects, scientists can map the distribution of dark matter and measure how structures in the universe grow over time. Changes in structure formation offer indirect but compelling clues about the influence of dark energy on the cosmic web. Large-scale galaxy surveys, such as those conducted by the Franz Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey, DES, chart the positions and motions of millions of galaxies across billions of light years. These massive datasets enable astronomers to measure a phenomenon known as baryon acoustic oscillations, subtle, periodic fluctuations in the density of matter relics from the early universe that act as a cosmic yardstick for expansion. Despite all these methods and the growing mountain of observational evidence, the true nature of dark energy remains elusive. Is it truly a cosmological constant, an unchanging property of vacuum energy, or is it a dynamic field evolving over time, a so-called quintessence? Could it be a manifestation of new physics, perhaps hinting at extra dimensions, modifications to gravity, or connections to string theory? Or is dark energy a sign that we have fundamentally misunderstood the laws that govern the cosmos? These questions strike at the heart of cosmology and theoretical physics. If answered, they could revolutionize our understanding not only of the universe's fate, but of its very origin and structure. Scientists are now designing the next generation of telescopes and experiments to pierce deeper into the cosmic past and trace the fingerprints of dark energy across time and space. Among these efforts is Euclid, a European Space Agency mission launched to measure the geometry of the universe with unprecedented accuracy. Complementing it is NASA's Nancy Grace Roman Space Telescope, scheduled for launch in the coming years, which will use both supernovae and gravitational lensing to dissect the influence of dark energy on cosmic expansion. Meanwhile, ground-based observatories like the Vera C. Rubin Observatory will survey the entire sky repeatedly, like mapping how galaxies evolve and move over time in a universe under the sway of an invisible force. Together, these investigations represent the most ambitious attempt yet to unravel a cosmic mystery that defies our intuition. Dark energy is not merely a curiosity on the margins of physics. It is the dominant force shaping the evolution of the universe. It raises questions more profound than any we have faced before. What is the nature of nothingness? Can energy emerge from the void? Is our universe one among many, governed by parameters that differ across a multiverse? In seeking to understand dark energy, we are not just trying to explain why galaxies fly apart faster with each passing moment. We are probing the boundary between the known and the unknown, between science and philosophy, between what is and what might be. This is not simply a quest to measure more precisely. It is a journey to comprehend the deepest laws that govern existence itself. And yet, in the cold silence between the stars, as space stretches and time marches on, the universe offers no answers, only clues, scattered in the light of ancient explosions, in the patterns of galaxies, in the whispers of background radiation. We are left to interpret the evidence, to build our models, and to follow the data wherever it leads, even if it takes us to the edge of what we believe is possible. This is the story of dark energy, a force unseen, a mystery unresolved, a puzzle that may hold the key to the past, the future, and the fate of everything that ever was. And the data, like an ancient whisper carried through time, reveal tiny temperature fluctuations, delicate imprints etched onto the canvas of the cosmos. These primordial ripples embedded within the cosmic microwave background, CMB, offer a frozen snapshot of the universe's earliest moments, just 380,000 years after the Big Bang. It is within this cosmic fossil light, relic radiation stretched across the vastness of space, that scientists seek answers. These subtle fluctuations, mapped with astonishing precision, are not mere noise. They are a celestial code. Decoding it has allowed scientists to reconstruct a narrative of the universe's geometry, its origins, its energy content, and its destiny. By meticulously analyzing the pattern of these temperature variations, cosmologists have determined that the universe is remarkably flat, not curved like a sphere or a saddle, but flat like an endless sheet. This flatness has profound implications. It demands a very specific total energy density, a balance so fine that even minute deviations would lead to a dramatically different cosmos. But here lies the cosmic conundrum. The visible constituents of the universe, ordinary matter, the atoms that form stars, planets, and people, alongside dark matter and the lingering radiation, account for only about 30% of the required energy density. The remaining 70%? Invisible, elusive, and enigmatic. That missing portion, it turns out, is something entirely different. Something that repels rather than attracts. Something that drives space itself to stretch, grow, and accelerate. It is dark energy. This mysterious force is not a theoretical abstraction pulled from mathematical fancy. Its existence is etched into the universe on the grandest scales. Large-scale galaxy surveys, among them the groundbreaking Sloan Digital Sky Survey, SDSS, have meticulously mapped the three-dimensional distribution of galaxies across billions of light-years. These surveys paint a tapestry of structure: cosmic filaments, vast voids, clusters of galaxies, and superclusters. Embedded in this pattern is a story of motion, a story not just of expansion, but of acceleration. Galaxies are not merely retreating from one another, they are doing so at an ever-increasing pace. This accelerating expansion, first revealed by observations of distant Type 1a supernovae, aligns perfectly with the dark energy hypothesis. As space expands faster and faster, it pulls galaxies apart more rapidly than gravity can bind them. Yet another layer of evidence comes from a phenomenon seated in the fiery plasma of the infant cosmos: baryon acoustic oscillations, BAO. These pressure waves formed when photons and matter danced in rhythm during the first few 100,000 years after the Big Bang, left behind permanent marks. These acoustic signatures are fossilized into the large-scale structure of the universe, appearing as a preferred scale in the distribution of galaxies. The BAO peaks serve as a cosmic ruler. By measuring their scale across different epochs, astronomers can trace how the universe's expansion rate has changed over time. The results consistently point to a universe whose expansion has been accelerating, again implicating dark energy as the driving force behind this cosmic runaway. Gravitational lensing offers yet another window into this invisible realm. This phenomenon, predicted by Einstein's theory of general relativity, occurs when the gravity of a massive object, such as a galaxy cluster, bends the path of light from more distant sources. These distortions are not just visual curiosities, they encode valuable information. By examining the warping of light across millions of galaxies, scientists can map the unseen mass responsible for the bending. This includes not only dark matter, which clusters around galaxies and gives them their scaffolding, but also the indirect influence of dark energy, which affects the growth rate and distribution of cosmic structures. Taken together, the CMB, large-scale surveys, BAO, gravitational lensing, and supernova data form an overwhelming interlocking web of evidence. It points to a universe governed not just by gravity and matter, but by a powerful, pervasive dark energy that dominates the cosmic energy budget. This revelation has shaken the foundations of cosmology and forced a profound reevaluation of our models of the universe. And yet, the mystery deepens. Dark energy and dark matter, though fundamentally different in character and behavior, are the twin shadows that define our cosmos. Dark matter clumps under gravity, seeding the formation of galaxies and anchoring them with invisible hands. It neither emits nor absorbs light, yet it forms the skeleton of all large-scale structures. Dark energy, on the other hand, is the agent of cosmic acceleration. It smooths and stretches the fabric of space-time itself. In the widely accepted LILCDM, lambda cold dark matter model, these two components are treated as independent and non-interacting, two distinct actors with different roles in the cosmic play. But what if this division is an illusion? What if, in the deeper mechanics of the cosmos, dark matter and dark energy are not entirely separate? Some theorists have dared to speculate on such interactions, models where these two dark components speak to one another across time and space. One of the most intriguing ideas is that of coupled dark energy. In this framework, dark energy is not a static cosmological constant, but a dynamic entity whose density can change over time and interact with dark matter. These interactions might subtly alter how dark matter clumps and evolves. In turn, dark matter could influence the rate at which dark energy exerts its repulsive pressure. Some coupled models suggest that dark energy may slowly decay into dark matter particles, adding mass and gravitational influence over time. Others hypothesize the opposite. Dark matter might decay into dark energy, accelerating the universe's expansion at an even more dramatic pace. These exchanges would have consequences for the growth of structures, potentially modifying the formation of galaxies, clusters, and voids. Scalar field models of dark energy also offer tantalizing possibilities. In these scenarios, dark energy is described not as a constant force, but as a field, akin to the Higgs field that gives particles mass. This scalar field evolves over time and could interact with dark matter in non-trivial ways. Such interactions might leave signatures in the distribution of galaxies, in the gravitational lensing maps, or in the detailed structure of the CMB. If these models prove accurate, then the nature of the dark sector is not just a matter of composition, but of communication. The evolution of the universe would be governed not merely by the presence of dark matter and dark energy, but by their ongoing relationship, a cosmic dialogue shaping everything from the birth of stars to the ultimate fate of all space and time. For now, the interaction between dark matter and dark energy remains an open question, an edge of the map still shrouded in mist. Observations continue to tighten the constraints, narrowing the possibilities. Future missions, such as the Euclid satellite, the Nancy Grace Roman Space Telescope, and ground-based observatories like the Vera C. Rubin Observatory, promise to illuminate these mysteries with unprecedented clarity. They will chart the expansion history, trace the growth of structure, and perhaps detect the subtle fingerprints of interactions across the dark sector. As we stand at the edge of knowledge, one thing is clear. Dark energy is not an abstract concept confined to equations. It is a force that sculpts the cosmos, a vital actor in the grandest story ever told. Its interplay with dark matter could hold the key to a deeper theory, one that unites the physics of the large and the small, the visible and the invisible. In confronting this darkness, we do not retreat. We advance, armed with data, driven by curiosity, and compelled by the belief that understanding the dark will ultimately lead us to a fuller light. And this interaction might lead to observable signatures in the large-scale structure of the universe. In a cosmos where nothing is ever truly still, where galaxies drift apart in a silent ballet choreographed by forces barely understood, subtle signs may be waiting to be uncovered. Modifications in the clustering of galaxies, deviations in the cosmic microwave background. These are not mere curiosities, but potential fingerprints of a deep and hidden relationship, an elusive cosmic dance between dark matter and dark energy. Despite decades of research and the ingenuity of physicists and astronomers, experimental and observational campaigns have yet to deliver conclusive proof of these interactions. The telescopes peer deeper into the heavens. Satellites measure background radiation with staggering precision. Detectors buried deep underground or mounted in orbit stand sentinel, watching for the tiniest tremors in the cosmic fabric. And still, no definitive evidence. Still, silence. Yet the clues may already be out there, camouflaged in the chaos of cosmic evolution. Precision measurements of the cosmic microwave background, the afterglow of the Big Bang, whisper ancient truths. The clustering of galaxies across billions of light years hints at forces pulling, shaping, influencing. Baryon acoustic oscillations, those primordial sound waves frozen in the large-scale distribution of matter, offer yet another lens through which the invisible might be inferred. Deviations from expected statistical patterns in these phenomena might not be mere noise. They might be signs. They might be evidence. They might be the first fragile strands of a web that connects the unseen. In this grand quest, physicists are not confined to the observational realm alone. Another path winds its way through the vast machinery of particle accelerators and the delicate instruments of particle physics laboratories. High-energy collisions at the Large Hadron Collider may reveal particles that do not fit neatly into the standard model. Intermediaries. Messengers. Particles that speak the secret language of dark energy and dark matter. Detection experiments, often deep underground to shield from interference, listen for whispers of dark matter interacting in ways that defy current understanding. Anomalies in these experiments might not be errors. They might be echoes from a hidden sector of reality. And while the standard cosmological model remains committed to the notion that dark matter and dark energy are separate, independent entities, the reality may be more complex. Conceptual models and cutting-edge research continue to explore the possibility that these dark components of the universe are not solitary actors, but intertwined elements in a larger cosmic drama. Detecting any interaction between them would not simply be a scientific milestone. It would be a revolution. It would reshape the foundational principles of cosmology. It would alter our understanding of gravity, of space-time, of the universe's ultimate fate. It would crack open the door to a new era of physics, one in which dark matter and dark energy are not only observed, but understood. Understanding the true nature of dark energy remains one of the most formidable challenges in modern science. It is a task layered in complexity, obscured by both observational limitations and theoretical conundrums. The primary obstacle is, paradoxically, its ghost-like nature. Unlike dark matter, which betrays its presence through gravitational effects on galaxies and other cosmic structures, dark energy reveals itself in more subtle, indirect ways. Its fingerprints are not found in motion or mass, but in the very expansion of space itself. The acceleration of this expansion is inferred from phenomena such as the redshift of distant Type Ia supernovae. These cosmic explosions serve as standard candles, allowing astronomers to trace how quickly the universe has grown over billions of years. Complementing these are the intricate temperature fluctuations mapped in the cosmic microwave background, patterns that tell stories from a time when the universe was less than 400,000 years old. Together, these methods build a compelling case, but they do not tell the whole story. They measure effects, not causes. They hint at dark energy, but they do not reveal its essence. And this is where the enigma deepens. Dark energy, by current estimates, makes up roughly 70% of the total energy density of the universe. It is the dominant component of the cosmos, yet it is uniformly distributed, showing no tendency to clump or form structures like ordinary matter or dark matter. It is diffuse, pervasive, and invisible. This homogeneity makes it profoundly difficult to isolate. Unlike a galaxy or a cluster, there is no place where dark energy resides more than elsewhere. Its effects are everywhere and nowhere, constant and elusive. Designing experiments to study something so evenly spread and weakly interacting presents a formidable task. Every approach must reckon with the sheer subtlety of the phenomena. To see dark energy, one must look not at things, but at the spaces between them. One must measure not motion, but acceleration. One must seek patterns across unimaginable scales and through vast spans of cosmic time. From a theoretical perspective, the situation is no less daunting. The most widely accepted model for dark energy is the cosmological constant, Lel, a term introduced by Einstein and later resurrected to account for the universe's accelerating expansion. In this model, dark energy is a constant vacuum energy density, a kind of energy inherent to empty space. It fits the data. It explains the acceleration. It is mathematically elegant, and it is deeply unsatisfying, because the vacuum energy predicted by quantum field theory is monstrously larger than what is observed by a factor of 10 to 120. This is the cosmological constant problem. It is, without exaggeration, one of the most profound, unsolved problems in all of physics. How can theory and observation differ so wildly? What principle, what law, what overlooked aspect of nature might reconcile these two worlds? Alternative theories abound. Some suggest that dark energy is not constant, but dynamic, a scalar field quintessence permeating space and evolving over time. Unlike Lel, quintessence can vary in strength and even interact with other fields or particles, including dark matter. It opens the door to a richer and more complex cosmology, but it also demands new physics. It introduces additional parameters. It complicates the equations. It strains against the boundaries of current theory. To properly describe such fields, physicists may need to extend or even break the standard model of particle physics. They may need to modify general relativity itself. Each step forward risks conflict with principles that have stood for over a century. And yet, the allure of understanding is irresistible. Precision in cosmological measurements is a linchpin of this quest. Observing the universe with the fidelity required to constrain dark energy's properties demands an extraordinary fusion of engineering and imagination. Telescopes must be bigger, instruments must be more sensitive, data analysis must be more refined. Projects like the Dark Energy Survey, known as DES, and the European Space Agency's Euclid mission are spearheading this charge. They aim to map vast regions of the sky with exquisite precision, measuring the shapes, positions, and redshifts of hundreds of millions of galaxies. They track the bending of light through gravitational lensing. They measure cosmic expansion across time. They catalog the large-scale structure of the universe with unprecedented clarity. And yet, every new dataset brings with it new puzzles, anomalies, deviations, features that do not quite fit. Some will be statistical flukes. Others may be systematics, but perhaps buried within are the first definitive signatures of a deeper truth. The story of dark energy is far from complete. It is being written now, in laboratories and observatories, in the equations of theorists and the observations of astronomers. It is a story not just of a force or a field, but of the human hunger to understand the cosmos at its deepest level. What is dark energy? Is it a property of space itself? Is it a dynamic field? Is it a signal that our theories, though brilliant, are incomplete? As new instruments come online and new theories are tested, the answers may slowly begin to take shape. But until then, the universe continues to expand, carrying with it the greatest mystery of all: why? But interpreting the data from these massive surveys requires sophisticated statistical tools and deep theoretical understanding. The complexity is not merely in processing terabytes of observational data collected from the furthest reaches of the cosmos. It lies deeper in the challenge of decoding the fabric of space and time itself. These efforts demand the interplay of advanced mathematics, machine learning algorithms, and high-performance computing systems to extract patterns invisible to the unaided human eye. Data from instruments like the Euclid Space Telescope, the Vera C. Rubin Observatory, and the James Webb Space Telescope are inundated with signatures of dark energy and dark matter. But separating signal from noise requires a level of precision and finesse that sit the frontier of contemporary science. Lastly, reconciling dark energy with other fundamental forces and particles might necessitate new physics beyond the current paradigms. This is not a minor refinement of existing theory. It may call for a conceptual overhaul of the very architecture of reality. Physicists are exploring frameworks that venture far beyond the Standard Model and Einstein's general relativity. Some propose extra dimensions curled up in the fabric of spacetime, imperceptible to our senses, but mathematically consistent with string theory. Others investigate modified theories of gravity, such as star FR gravity or scalar tensor models that could explain the accelerated expansion without invoking a cosmological constant. Or perhaps the answer lies in the discovery of entirely new particle species, new fields, or exotic interactions that defy our current expectations. These theories might be waiting in the gaps between quarks and leptons, between the curvature of spacetime and the vacuum energy of quantum fields. Developing and testing such revolutionary ideas remains a formidable task, one that requires simultaneous breakthroughs in theoretical frameworks and experimental technology. Next-generation particle accelerators, quantum sensors, and gravitational wave detectors may be the instruments that finally offer a glimpse into the invisible mechanisms shaping our universe. The quest to understand dark energy is hampered by its indirect detectability. It neither emits nor absorbs light. It does not clump into stars or galaxies. Instead, it exerts its presence subtly through the large-scale behavior of spacetime, accelerating the expansion of the universe with an inscrutable push. Theoretical challenges abound. How to incorporate dark energy into a framework that includes quantum field theory and general relativity, both of which falter at cosmological scales. Even its name, dark energy, is a placeholder, a linguistic admission of our ignorance. The need for precise cosmological measurements grows more urgent with every advance. Instruments that can measure the redshift of distant galaxies to pinpoint the rate of cosmic expansion, detectors that can map minute fluctuations in the cosmic microwave background, and telescopes that track the clustering of galaxies across epochs, all are required to refine our understanding. Only by charting the influence of dark energy across time and scale can we hope to constrain the theories that seek to explain it. Yet even with the difficulties of detection, the potential requirement for new physics, and the enormous theoretical uncertainties, ongoing research holds the promise of unraveling this profound mystery. With each new observation, each new experiment, we are drawn closer to the horizon of comprehension. It is a journey marked by persistent curiosity and evolving understanding, where each data point is a clue and each anomaly a potential breakthrough. The influence of dark matter and dark energy extends far beyond their roles in shaping the cosmos' large-scale structure. These mysterious components are more than silent architects, they are custodians of cosmic fate. Understanding how they interact, how they pull and push against the fabric of the universe, is essential for predicting what the universe will become. Dark matter, which comprises approximately 25% of the universe's energy density, acts as the gravitational skeleton upon which all visible matter is suspended. It is the unseen hand that molded the earliest galaxies, that shepherded gas and dust into stars, and that binds galaxy clusters into gravitationally coherent wholes. Without dark matter, the structures we observe, spiral galaxies, galactic superclusters, the web-like filaments spanning billions of light years, could never have formed. Its gravitational embrace holds galaxies together, resisting the tendency of cosmic expansion to pull them apart. Over billions of years, this scaffolding has allowed galaxies to coalesce and persist. The rotation curves of spiral galaxies, gravitational lensing patterns, and temperature anisotropies in the cosmic microwave background all bear the fingerprints of dark matter. Its presence is irrefutable, yet its identity remains elusive. It may consist of weakly interacting massive particles, WIMPs, axions, or perhaps some other unknown constituent. The search for dark matter continues both underground, in deep mines shielded from cosmic rays, and in the high-energy collisions of particle accelerators. In contrast, dark energy, accounting for roughly 70% of the universe's energy density, operates as a repulsive force. Its nature first emerged from the dim glow of distant Type Ia supernovae observed in the late 1990s. These stellar explosions served as standard candles, revealing that the universe's expansion was not decelerating, as once expected, but accelerating. This finding overturned centuries of cosmological assumptions and introduced a fundamental puzzle. What force could cause space itself to stretch faster over time? The balance between dark matter and dark energy is a cosmic tug-of-war, the outcome of which will decide the universe's ultimate destiny. If dark energy continues to dominate, as current observations suggest, the expansion will accelerate indefinitely. Galaxies will drift apart beyond the reach of any light signal. Stars will exhaust their nuclear fuel and die, leaving behind white dwarfs, neutron stars, and black holes. Eventually, even black holes will evaporate through Hawking radiation. The universe will become a vast, cold, dark expanse where no meaningful interactions occur. This is the Big Freeze, also called heat death, a future in which entropy rules and the cosmos lapses into eternal stillness. But an even more dramatic fate might await. Some models suggest the possibility of a big rip. If dark energy is not constant but instead grows stronger over time, imagine a scenario in which its repulsive force increases with the expansion. It could tear apart the fabric of the universe itself. First, galaxy clusters would be sundered, then galaxies, then solar systems. Eventually, the very atoms making up matter could be ripped apart by the overwhelming expansion. This apocalyptic finale would obliterate all known structures and dissolve space-time into discontinuity. Conversely, if future research uncovers a stabilizing mechanism, if, for instance, dark matter plays a larger role than currently assumed, or if a new understanding of dark energy arises, the universe might stabilize. In one such scenario, the expansion could slow, halt, and reverse. Gravity would reassert dominance, pulling galaxies together. The universe would contract, leading to a big crunch, a return to singularity. Some speculative theories go further, proposing that such a collapse could precede another Big Bang in a cyclic model of the universe: creation, expansion, contraction, rebirth. Theoretical models exploring dynamic forms of dark energy, such as quintessence, introduce additional possibilities. Unlike the cosmological constant, which remains uniform, quintessence changes over time. Its strength may wax and wane, leading to universes that oscillate between expansion and contraction. These models hint at a cosmos not destined for eternal uniformity, but engaged in an infinite rhythm, a cosmic breath of expansion and collapse. Presently, the best available evidence from the cosmic microwave background, from the distribution of galaxies in large-scale structure surveys, from the light of ancient supernovae, supports a universe fated for continued acceleration. Yet science thrives on its provisional nature. With every refinement in observation, with every leap in theoretical insight, our models evolve. Tomorrow's data could overturn today's consensus, replacing certainty with deeper questions. While dark matter binds the cosmos together through its gravitational influence, dark energy drives its accelerated expansion. This tension, this cosmic dialectic between attraction and repulsion, is not just a phenomenon of astrophysics. It is the very engine of cosmic evolution. Their balance shapes the galaxies, the voids, the web of cosmic filaments, and ultimately, the future of everything that exists. The mystery remains, but in the search for answers, humanity inches ever closer to a fuller understanding of the universe's greatest enigmas, but also dictates its future trajectory, anchoring our understanding in a cosmos that stretches endlessly outward, laced with possibility, uncertainty, and grandeur. The formation and evolution of the Milky Way, like the rhythmic unfolding of an ancient epic, tells a story both deeply personal and universally profound. A story that begins not in the heart of our galaxy, but in the primeval fires of the Big Bang itself. In the earliest fractions of cosmic time, just a few 100 million years after the birth of the universe, tiny irregularities in the near-uniform sea of matter began to collapse under gravity's silent direction. These were no ordinary regions. They were overdensities, fluctuations that would seed structure in the otherwise smooth fabric of space-time. Here, dark matter, the elusive and invisible scaffolding of the cosmos, began to clump and gather. In these dark matter halos, like pearls forming in unseen shells, gas cooled, condensed, and ignited into the very first stars. These earliest stars, the enigmatic and massive population 3 stars, blazed briefly and fiercely. Forged in hydrogen and helium, devoid of heavier elements, they lived fast and died young, collapsing in violent supernovae that spewed carbon, oxygen, and other building blocks into the void. Each explosion was both an end and a beginning, a cosmological alchemy enriching the interstellar medium, preparing the raw material for later generations of stars, and initiating the gradual metal enrichment of the universe. Galactic assembly was not a peaceful affair. The early universe was a maelstrom of motion, where small galaxies collided, merged, and cannibalized one another in a hierarchical dance described by the lambda cold dark matter, CDM model, the prevailing theory of cosmic structure formation. The Milky Way's formation was a product of this cosmic turbulence. It was not born in isolation, but accreted over billions of years through the gravitational amalgamation of smaller protogalaxies and star clusters. In this relentless process of galactic consumption, the Milky Way grew, first assembling its diffuse halo, a sprawling sphere of ancient stars and globular clusters, many of which remain as fossil records of long-devoured dwarf galaxies. We can still trace these ancient feasts in the sky today. Stellar streams, remnants of shredded satellite galaxies, arc across the sky like ghostly rivers, echoing the violent gravitational interactions that shaped our galaxy's skeleton. Roughly 8 to 10 billion years ago, the Milky Way began to settle into a more recognizable form. As gas cooled and collapsed under gravity, it flattened into a spinning disk, setting the stage for the galaxy's iconic spiral structure. Within this disk, star formation accelerated, giving rise to population 1 stars rich in heavy elements, gold, iron, uranium, each atom a legacy of earlier generations of stellar death. This era birthed the spiral arms, those sweeping, luminous structures where pressure waves known as density waves compressed gas and triggered the collapse of molecular clouds, giving birth to stars in immense stellar nurseries. The Milky Way's disk remains a bustling metropolis of stars, planetary systems, nebulae, and gas clouds. Here, in a modest arm known as the Orion Spur, our own solar system orbits the galactic center, a tiny speck in a grand architecture. But even in this apparent stability, change is constant. Gas continues to flow into the disk from the intergalactic medium and infalling satellite galaxies, fueling ongoing star formation and reshaping the galactic canvas. Beneath the grandeur of the spiral arms lies the galactic bulge, a dense central concentration of older stars wrapped around a singular object of profound mystery and power, Sagittarius A star, the supermassive black hole at the Milky Way's heart. This gravitational colossus, weighing in at approximately 4 million solar masses, lurks invisible yet omnipresent, veiled by veils of dust and gas, commanding the motion of stars that dance around it in dizzying orbits. Sagittarius A was discovered through radio observations in the 1970s, but it has only become a major focus of astrophysical inquiry in recent decades. Unlike its more flamboyant cousins in distant galaxies, quasars and active galactic nuclei that blaze with energy as they consume matter at furious rates, Sagittarius A is subdued. It flickers occasionally, emitting bursts of X-rays and radio waves, but remains largely dormant. Why it is so quiet remains one of the galaxy's greatest puzzles. Is it starved of fuel? Is its accretion process governed by unusual physics? Or are we merely witnessing a temporary lull in a longer cycle of activity? The quiescence of Sagittarius A is contrasted sharply by the frenetic activity in its immediate environment. The galactic center is a crucible of extreme physics, where stars orbit at relativistic speeds and magnetic fields twist and snap like cosmic whips. The S stars, a population of young, hot stars orbiting dangerously close to the black hole, are being studied intensively. Their tight, fast orbits provide an unprecedented laboratory for testing Einstein's general theory of relativity under extreme conditions, probing the nature of gravity itself. But beneath the observable lies the unknowable. The event horizon, the point of no return surrounding Sagittarius A, marks the limit where space and time fold inward. Beyond it, our laws of physics collapse into singularity, and light itself cannot escape. Efforts to glimpse the shadow of this event horizon are underway through the Event Horizon Telescope, EHT, a global network of radio observatories that, in 2019, revealed the first image of a black hole in galaxy M87. Capturing a similar image of Sagittarius A is even more difficult. Unlike M87's black hole, Sagittarius A varies rapidly and is obscured by interstellar gas. But progress continues, driven by technological innovation and international collaboration. This supermassive black hole may also play a much larger role in the galaxy than its silence implies. Though Sagittarius A Hleirstad is currently dormant, it is thought that supermassive black holes in general regulate the evolution of their host galaxies through feedback mechanisms, outflows of energy and material that suppress or trigger star formation across vast distances. How exactly Sagittarius A influences the dynamics and evolution of the Milky Way remains an area of intense research. Does it shape the bulge? Does it moderate star formation? Or is its influence far more subtle, woven into the cosmic architecture in ways we do not yet understand? Beyond the astrophysical lies the quantum, where even greater mysteries await. Theoretical physicist Stephen Hawking once proposed that black holes are not entirely black. Due to quantum effects near the event horizon, black holes may emit what is now called Hawking radiation, a faint glow that could ultimately cause them to evaporate over eons. But detecting such radiation from a supermassive black hole like Sagittarius A is far beyond our current technological reach. Still, the mere possibility opens profound questions about the nature of space-time, the unification of quantum mechanics and gravity, and the ultimate fate of black holes. Sagittarius A is not alone in its quiet dominion. The Milky Way itself is changing, evolving, and marching toward an inevitable rendezvous with another giant, the Andromeda Galaxy. In approximately 4 billion years, the two galaxies will collide and merge, reshaping the local cosmos into a new, larger elliptical galaxy. The stars themselves will rarely collide, but the gravitational ballet will trigger massive starbursts, distort galactic structures, and likely alter the position and behavior of the central black holes, perhaps even leading to their own merger. Until that time, the Milky Way remains a dynamic, restless system, a cauldron of creation, destruction, and transformation. From its birth in the murky depths of cosmic dawn to its current grandeur as a spiral galaxy hosting hundreds of billions of stars and onward into an unknowable future, the Milky Way is both our home and our history. Each photon we observe, each star we chart, and each signal we decipher tells a piece of its story. In the shadows of Sagittarius A, at the edges of the spiral arms, in the ancient globular clusters that drift like stellar fossils in the halo, the history of our galaxy is etched. It is a history of fire and dust, gravity and collision, birth and death, and in telling its story, we tell something of our own, a species born of star stuff, reaching back with light and theory into a past too vast to imagine and forward into a destiny yet unwritten, but also the fundamental properties and behaviors of black holes throughout the cosmos, but also the immense, often violent ballet of galaxy collisions that unfold across the fabric of the universe. These titanic interactions serve as pivotal engines of galactic metamorphosis, driving a sweeping transformation in structure, star-forming activity, and the dynamical evolution of galaxies. It is within these immense encounters that the architecture of the universe, is constantly reshaped. The story of galaxies is not a static one, but rather a saga of continual motion, merging, and reformation. Galaxy collisions are not rare anomalies. They are common and essential processes that perpetually recycle matter and energy, fostering new life within the vast, ancient voids of space. Among the most breathtaking consequences of galactic collisions is the radical transformation of morphology. When two galaxies approach one another, their mutual gravitational pull acts like a sculptor's chisel, distorting their shapes in surreal and sometimes majestic forms. Long, sinuous tidal tails stretch into the void, star streams arc like cosmic brushstrokes across the black canvas of space, and brilliant bridges of gas and dust link the colliding galaxies together in luminous umbilical cords. These features emerge from gravitational forces so powerful that they draw stars and gas out of the galactic disks, flinging them into vast, curling structures. The antennae galaxies, an iconic visual symbol of galactic collision, offer a vivid glimpse of this process in action. Their outstretched tails and glowing knots of star formation speak to an ancient and ongoing interstellar dance, a cosmic choreography unfolding over millions of years. As these galaxies continue to interact, their individual identities begin to dissolve. Over time, they will coalesce into a single galactic remnant, one whose form may bear little resemblance to the elegant spirals that once were. Spiral galaxies, rich in gas and rotating with stately grace, can emerge from collisions as entirely different entities. The randomization of stellar orbits and the redistribution of angular momentum often give birth to elliptical galaxies, more massive, more rounded, and with much less gas for star formation. Indeed, in massive galaxy clusters teeming with interactions, elliptical galaxies dominate, their presence testament to ancient collisions and mergers now written into the cluster structure like geological strata. But these encounters do not simply tear and reshape, they ignite. As galaxies collide, massive clouds of gas are compressed, shocked, and forced together. This compression triggers torrents of star formation in what astronomers call starbursts. These events are breathtaking in scale. New stars flare into being at rates hundreds of times greater than in tranquil galaxies. Regions of furious brightness blaze in ultraviolet and infrared, bathing the merging system in light. In these bursts, tens of thousands of stars can be born in the space of a single cosmic heartbeat. The Milky Way itself is not immune to this destiny. Hurtling through the void at breakneck speed, the Andromeda Galaxy, our nearest spiral neighbor, is on a collision course with us. In approximately 4.5 billion years, the two galaxies will begin their slow, majestic merger. While the collision will not likely result in many direct stellar crashes due to the vast spaces between stars, the gravitational and gas dynamic chaos will fuel a new epoch of star formation. This future galactic remnant, sometimes dubbed Milkomeda, will likely resemble a giant elliptical galaxy, glowing faintly as its star-forming gas dwindles. Yet perhaps the most enigmatic and consequential impact of galactic collisions lies at the very hearts of galaxies, where supermassive black holes reside. These behemoths, weighing millions to billions of times the mass of our Sun, often slumber in quiet galaxies. But when galaxies merge, torrents of gas and dust are driven inward, funneled by gravitational torques toward the central regions. There, the material begins to spiral into the waiting maw of the black hole, feeding it, awakening it. As the black hole consumes this matter, it erupts with unimaginable energy. The galaxy's core becomes an active galactic nucleus, or AGN, sometimes outshining the rest of the galaxy combined. In some cases, the energy output is so intense that the galaxy becomes a quasar, visible across the universe. These periods of intense AGN activity can unleash powerful jets and outflows capable of reshaping the galaxy's internal structure. These outflows can sweep away gas, quenching star formation and regulating the future evolutionary path of the galaxy. But the influence of galactic collisions does not stop at the edge of visible light. Beneath the glowing stars and swirling gas lies an invisible skeleton of dark matter. Every galaxy is embedded in a vast halo of dark matter, mysterious, non-luminous mass that exerts gravitational influence but does not interact with light. When galaxies collide, so too do their dark matter halos. These halos merge, stretch, and ultimately relax into a new equilibrium, defining the gravitational potential of the resulting galactic remnant. This dark matter coalescence plays a critical role in binding the post-merger galaxy together, anchoring the stars, gas, and black holes in a stable gravitational framework. Without this dark scaffolding, galaxies would disintegrate into chaos. On even larger scales, the impact of galactic collisions extends into the dynamics of galaxy clusters, vast conglomerates containing hundreds or thousands of galaxies. Within these clusters, interactions and mergers are ongoing. Galaxies fall into clusters from surrounding filaments of the cosmic web, collide with resident members, and are stripped of their gas in a process known as ram pressure stripping. Over time, these interactions build ever more massive and complex clusters surrounded by halos of hot X-ray emitting gas and dominated by the giant ellipticals born of ancient collisions. Simulations powered by the most advanced supercomputers have become essential to understanding these epic events. By modeling billions of particles representing stars, gas, and dark matter, astronomers can reconstruct the slow dance of merging galaxies, predicting their future evolution and comparing simulated structures with telescopic observations. These digital laboratories allow researchers to test hypotheses, explore the effects of varying masses and orbits, and decode the intricacies of tidal forces, starburst triggers, and black hole feeding patterns. Through these simulations, we understand not just the final stages of mergers, but the long, slow prelude, the drawn-out gravitational courtship, the tidal harassment, the induced spiral arm warps, and the early gas inflows that preface the explosive changes to come. Each simulated collision becomes a kind of living documentary, a dynamic film revealing the processes that have shaped every galaxy in the universe, including our own. Ultimately, galactic collisions are the engine rooms of cosmic transformation. They reshape the structure of galaxies, ignite new stars in explosive fury, awaken sleeping black holes into brilliant quasar beacons, and sculpt the dark matter skeleton that holds it all together. Every shining elliptical galaxy, every dormant supermassive black hole, every burst of newborn stars owes its existence to the violence and beauty of these intergalactic encounters. To understand the universe, we must understand the stories told in these collisions. We must read the twisted shapes of merging galaxies like ancient runes. We must trace the stellar streams back to their violent origins. We must listen to the silent testimony of X-rays and radio waves, whispering of gas stripped and black holes fed. And in that search, the Andromeda Galaxy stands as both a subject and a warning. Known to astronomers as M31, it is the nearest large spiral galaxy to our own and one of the most studied objects in the night sky. Yet despite its proximity and centuries of observation, it remains shrouded in mysteries. Perhaps the most perplexing of these is its double nucleus, a strange dual-lobed structure at the galaxy's core. At first glance, it appears as though Andromeda possesses two central bulges, two hearts. This bizarre formation, first revealed through high-resolution imaging, has spurred intense study and speculation. One interpretation suggests that we are seeing a single central black hole encircled by a lopsided disk of old stars, their distribution creating the illusion of two distinct nuclei. Others suggest a more tumultuous history involving a smaller galaxy swallowed by Andromeda in a long-ago merger, its stellar core still orbiting within the larger galaxy's center like a fossilized heart. Whatever the truth, the double nucleus is a symbol of Andromeda's turbulent past and an omen of the Milky Way's future. We are watching a giant approach. We are drifting, year by year, toward a future shaped by gravitational inevitability. When the collision comes, it will be slow and spectacular, beautiful and violent. In the cold, vast theater of space, galaxy collisions are not the exception, they are the rule. They are the ancient forge in which the universe has been shaped, and they are the promise of the future, where stars will be born anew in the glowing wreckage of what once was. But two closely spaced bright cores shimmer at the heart of the Andromeda Galaxy, an enduring enigma that has fascinated astronomers for decades. One prevailing hypothesis suggests that this unusual duality arises from a supermassive black hole displaced from the true galactic center, a consequence of ancient gravitational turmoil following a merger with a smaller galaxy. The collision, slow and silent across millions of years, may have nudged the black hole into an orbit just off-center, leaving behind the illusion of a double nucleus. However, other astronomers argue that this phenomenon could instead be a byproduct of stellar dynamics, an illusion created by stars executing elongated orbits around a single, massive central object. The apparent duplication is not a physical pairing, but a clever trick played by orbital paths and the observer's perspective. Andromeda's mysteries do not end at its glowing heart. High above and far beyond the galactic core, the ancient inhabitants of its stellar halo offer more puzzles than answers. The galaxy's collection of globular clusters, dense spherical groupings of ancient stars, far exceeds that of our own Milky Way. This overabundance raises pressing questions. How did Andromeda accumulate such a large population of these aged stellar relics? Some researchers believe that Andromeda's violent past may hold the key. The galaxy could have cannibalized smaller satellite galaxies, stripping them of their clusters like cosmic souvenirs. Others suggest that Andromeda's unique environment might have triggered the formation of new globular clusters in the outer halo, far from the calming influence of the galactic core. The halo of Andromeda itself is a monument to cosmic violence and ancient encounters. Stretching tens of thousands of light years from the galactic center, it contains faint stars, ghostly star streams, and remnants of galaxies long consumed. These stellar streams act as the galaxy's fossil record. Like the veins in an ancient leaf, they trace the trajectories of smaller systems that once orbited freely, but were ultimately shredded and absorbed by Andromeda's immense gravitational field. Each stream is a scar, a memory of a cosmic conquest. Yet many remain partially charted, their origins uncertain. With the advent of deep sky surveys and ultra-sensitive imaging instruments, astronomers continue to piece together these broken arcs, decoding Andromeda's turbulent evolutionary history. Another spectral structure emerges when astronomers view Andromeda in ultraviolet, a vast ring-like feature etched into its galactic disk. This ultraviolet ring, unseen in visible wavelengths, may be the residue of a cosmic collision, an ancient impact with a smaller galaxy that sent ripples through Andromeda's disk, like a stone tossed into a serene pond. These ripples may have condensed gas and dust into concentrated star-forming regions, igniting newborn stars in a loop around the galaxy's core. Others postulate that the ring may still be forming, fueled by ongoing gravitational interactions with nearby satellite galaxies. This dynamic process, frozen in light, offers a rare window into the hidden choreography of galaxies in motion. Beneath these visible structures lies an invisible force shaping every motion and holding together the galactic whole. The dark matter halo of Andromeda is an unseen titan, enveloping the galaxy in a cocoon of gravity. Though it cannot be seen, its influence is undeniable, revealed in the way stars orbit at unexpected velocities, far beyond what visible mass alone would dictate. Despite decades of study, the precise shape and density of this dark matter envelope remain elusive. Theoretical models and high-resolution simulations race to match observed data, aiming to uncover the hidden architecture that dark matter imposes on the galaxy. The nature of this shadowy substance, what it is, how it behaves, and how it came to be so dominant, remains one of the deepest riddles in astrophysics. And then there is the future, written in the stars but yet to unfold. In approximately 4.5 billion years, Andromeda and the Milky Way will collide in a slow, majestic cataclysm. The two galaxies are on an inevitable course, pulled toward one another by mutual gravity. Their halos have already begun to interact. Simulations predict that their spiraling dance will lead not to annihilation, but to rebirth, a new, larger elliptical galaxy born from the remnants of both. The collision will trigger waves of star formation, warp galactic structures, and scatter planetary systems into chaotic new orbits. Although the event lies far in the future, studying its precursors allows astronomers to anticipate the structural evolution of galaxies and the long-term fate of our cosmic neighborhood. At the very core of Andromeda, deeper still than the double nucleus, lies a dark and massive mystery, a supermassive black hole, estimated to be nearly 100 million times the mass of our Sun. Though quieter than its quasar counterparts in the distant universe, it still commands immense gravitational influence. Its subdued activity leaves astronomers with an important question. Why is this black hole dormant, and under what conditions might it awaken? Researchers examine the surrounding stellar populations, gas distributions, and historical data to understand how this leviathan has shaped the evolution of its host galaxy. The black hole's quietude contrasts starkly with its incredible mass, offering a paradox that draws continued scientific scrutiny. These interwoven mysteries, Andromeda's core, its halo, its ancient clusters, its stellar streams, its ghostly ring, its dark matter, and its eventual merger, form a galactic biography written in gravitational forces and luminous echoes. Each structure tells a chapter of cosmic evolution, each interaction another step in the ballet of galaxies. Meanwhile, on the largest scales of the universe, astronomers step back even farther. They map the cosmic web itself, the vast scaffolding of galaxies and voids that stretches across cosmos like a three-dimensional spider's web. Astronomical surveys, such as the Sloan Digital Sky Survey, scan immense swaths of the sky to catalog millions of galaxies. These surveys reveal the underlying geometry of the universe, filaments of matter where galaxies cluster together, and voids where space lies eerily empty. The light from these galaxies is ancient, carrying the imprint of epochs long past. Looking at them is looking back in time, witnessing the emergence of structure from the near-uniform glow of the Big Bang. In addition to visible light, scientists also use radio telescopes to probe the structure of the cosmic web. These instruments detect the faint emission of neutral hydrogen, an element that permeates intergalactic space and outlines the filamentary highways of matter that connect galaxies. Even in regions devoid of starlight, hydrogen marks the path of gravitational collapse and formation. By following the trail of this elusive gas, astronomers can trace the hidden structure of the universe with remarkable precision. To complement these observations, physicists turn to computer simulations, wielding supercomputers like virtual universes. These models incorporate the known laws of physics to recreate the growth of cosmic structures over billions of years. By adjusting parameters such as the distribution of dark matter, the influence of dark energy, and the impact of feedback from stars and black holes, these simulations test and refine our understanding of how the universe has evolved. Comparing these digital universes with actual observational data enables scientists to validate their theories and pinpoint the invisible influences that shape everything we see. Among the most enigmatic cosmic objects revealed by these observations are quasars, or quasi-stellar objects. Quasars are the luminous beacons of the early universe, burning with an intensity that defies comprehension. At their heart lies a supermassive black hole surrounded by an accretion disk of gas and dust. As this material spirals inward, it accelerates and heats up to astonishing temperatures, emitting energy across the entire electromagnetic spectrum. The result is an object so bright it can outshine an entire galaxy of stars, yet it occupies a space no larger than our solar system. Quasars are more than just bright objects. They are cosmological laboratories. Their intense energy output challenges our understanding of how matter behaves under extreme gravity and pressure. Some quasars exhibit variability in their brightness over days, weeks, or months, suggesting turbulent and dynamic conditions near the event horizon. These fluctuations open a window into the heart of the black hole's feeding frenzy, revealing clues about the mechanics of accretion, jet formation, and energy dissipation. The sheer scale and power of quasars offer a window into the early universe. They are among the first structures to form after the Big Bang, serving as markers of the first galaxies and their central black holes. Their light has traveled billions of years to reach Earth, bringing with it a message from a time when the universe was still young. By studying quasars, astronomers can understand the growth of supermassive black holes, the enrichment of intergalactic space with heavy elements, and the transformation of primordial gas into stars and galaxies. The quest to understand objects like Andromeda, the cosmic web, and quasars is ultimately a quest to understand ourselves. These immense systems and their histories inform the story of our own galaxy, our own star, and the fragile blue planet we call home. Through their light, their gravity, and their silence, they teach us that the universe is not a static backdrop, but a living, evolving entity, a grand and ceaseless drama playing out across unfathomable distances and unthinkable timescales. but also provides clues about galaxy formation and the evolution of the cosmos itself. Galaxy clusters, vast, sprawling systems that are the largest gravitationally bound structures in the known universe, reveal a cosmic narrative that spans nearly the entirety of space and time. These immense clusters, composed of hundreds to thousands of galaxies, trace their origins back to the earliest moments following the Big Bang. Initially, the universe was a nearly homogeneous expanse of primordial matter and radiation, but subtle variations in density, imperceptible fluctuations caused by quantum perturbations magnified during the inflationary epoch, sowed the seeds of all subsequent structure. In those first fractions of a second, the universe expanded faster than the speed of light, stretching these quantum fluctuations across cosmic distances. As the universe cooled and matter began to dominate, these tiny irregularities grew under the inexorable force of gravity. Regions slightly denser than their surroundings began to attract more matter, snowballing into vast wells of gravitational potential. Over billions of years, through countless mergers and the continuous accretion of matter, these nascent overdensities evolved into the massive galaxy clusters we observe today. Galaxy clusters do not form quietly. The merging of smaller galaxy groups and clusters is a violent, energetic process. As these titanic bodies collide, they unleash shockwaves that ripple through the intergalactic medium, heating the sparse gas that permeates the cluster environment to temperatures exceeding tens of millions of degrees Kelvin. This superheated plasma, known as the intracluster medium, emits strongly in the X-ray part of the electromagnetic spectrum. Observations from space-based telescopes like Chandra and XMM Newton allow astronomers to study this searing hot gas, which holds more mass than all the stars in the galaxies combined. These X-ray observations provide critical clues to the dynamics and composition of clusters, revealing intricate details of cluster formation, interaction, and history. The secrets contained within galaxy clusters extend far beyond their sheer mass or the violence of their formation. They are key probes into the very nature of the universe itself. One of the most profound mysteries these structures help unravel is the elusive nature of dark matter and dark energy. Despite making up over 95% of the total mass energy content of the universe, these components remain invisible and enigmatic. Galaxy clusters act as cosmic laboratories where the fingerprints of dark matter can be studied through its gravitational influence on visible matter. One of the most compelling lines of evidence for dark matter in galaxy clusters comes from the phenomenon of gravitational lensing. According to Einstein's general theory of relativity, massive objects warp the fabric of space-time, bending the paths of light that pass near them. When light from distant galaxies travels through a cluster, the cluster's massive gravitational field distorts and magnifies the background light, creating arcs, rings, and multiple images. These lensing effects allow scientists to map the mass distribution of clusters, including the unseen dark matter that far outweighs the observable stars and gas. The distribution of dark matter, inferred through such gravitational lensing studies, often reveals clumps and halos that do not align with visible components, confirming its invisible yet dominant presence. In addition to dark matter, galaxy clusters provide a window into the properties and effects of dark energy, the mysterious force driving the accelerated expansion of the universe. By measuring the abundance and distribution of galaxy clusters over cosmic time, astronomers can trace the growth of large-scale structure and test models of cosmic evolution. Changes in cluster number density and spatial distribution reflect the influence of dark energy on the rate at which matter clumps together under gravity. Observations from surveys like the Sloan Digital Sky Survey, SDSS, and the Dark Energy Survey, DES, help constrain the parameters of dark energy, including its equation of state. The hot, X-ray emitting gas in clusters is also a rich source of information about the chemical evolution of the universe. This gas is enriched with elements heavier than hydrogen and helium, elements forged in the hearts of stars and released through supernovae. By analyzing the spectral lines of this intracluster medium, astronomers can determine the abundances of elements like iron, oxygen, and silicon, offering a glimpse into the star formation and feedback processes that have shaped galaxies across billions of years. The presence of these metals in such vast quantities suggests that galactic winds and outflows have transported material far beyond the confines of individual galaxies, distributing it throughout the cluster environment. Through all these lenses, gravitational, electromagnetic, and theoretical, galaxy clusters emerge as powerful tools for unraveling the grand architecture of the cosmos. They illuminate the interconnected threads of the cosmic web, a vast network of filaments composed of galaxies, dark matter, and gas that stretches across the universe. These clusters lie at the nodes of this web, where filaments intersect and gravitational potential wells are deepest. Studying their properties helps scientists piece together the cosmic puzzle, tracing the evolution of matter from the smooth early universe to the richly structured tapestry we see today. The cosmic microwave background, or CMB, is another critical piece of this cosmic story. Discovered by Arno Penzias and Robert Wilson in 1965, the CMB is the faint afterglow of the Big Bang, a nearly uniform bath of microwave radiation that fills the universe. This relic radiation originates from a time approximately 380,000 years after the Big Bang, when the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms, allowing photons to travel freely for the first time. Before this era, known as recombination, the universe was opaque, a seething plasma of particles and radiation. The CMB is not entirely uniform. It contains tiny fluctuations in temperature and polarization, imprinted with the fingerprints of the early universe's density variations. These fluctuations at the level of 1 part in 100,000 are the direct precursors of all later cosmic structure. Detailed maps of the CMB made by missions such as COBE, MAVI-P, and Planck have revolutionized cosmology. They provide a snapshot of the universe in its infancy and a wealth of data that informs virtually every aspect of modern cosmological theory. From these maps, scientists have extracted the universe's fundamental parameters with remarkable precision. The age of the universe, approximately 13.8 billion years, the proportions of its constituents, about 5% ordinary matter, 27% dark matter, and 68% dark energy, and the Hubble constant, which quantifies the rate of cosmic expansion. Moreover, the CMB confirms that the universe is flat, meaning that its geometry conforms to the rules of Euclidean space on large scales. The significance of the CMB does not end there. By comparing the predicted and observed power spectra of its temperature fluctuations, cosmologists test theories of inflation, dark energy, and the overall evolution of the universe. Polarization measurements, in particular, offer insight into the epoch of reionization, the period when the first stars and galaxies formed and began to reionize the neutral hydrogen, re-illuminating the universe after the cosmic dark ages. The expansion of the universe itself was dramatically confirmed through the observation of redshifted light from distant galaxies. In 1929, Edwin Hubble published his seminal discovery that the farther a galaxy is from Earth, the faster it appears to be receding. This observation, based on the redshift of spectral lines, where the wavelength of light stretches toward the red end of the spectrum, established that the universe is not static. Instead, it is expanding in all directions, with space itself stretching over time. This cosmic expansion, initially met with skepticism, became a cornerstone of modern cosmology. It was soon realized that if the universe is expanding now, then it must have been denser and hotter in the past, leading inevitably to a beginning, the Big Bang. The redshift-distance relationship, now encapsulated in Hubble's law, provided the first direct evidence for this explosive origin. Subsequent observations, including those of supernovae in distant galaxies, revealed that the expansion is not slowing down as once thought, but accelerating, an astonishing discovery that earned the 2011 Nobel Prize in Physics. Taken together, the study of galaxy clusters, the cosmic microwave background, and the redshift of galaxies paints a cohesive, awe-inspiring portrait of the universe. From the minute ripples of energy in the infant cosmos to the colossal clusters of galaxies threading the vast emptiness of space, every scale of structure is a testament to the laws of physics playing out across billions of years. The universe is not merely a backdrop for celestial events. It is a dynamic, evolving entity, governed by principles that scientists continue to explore with ever-increasing precision and wonder. Galaxy clusters, the CMB, and cosmic expansion are not isolated phenomena. They are interwoven chapters in the grand narrative of existence, each echoing the same fundamental questions. Where did we come from? What is the universe made of? How will it end? The pursuit of these answers fuels the deepest inquiries of modern science, inspiring a ceaseless quest to understand not only the cosmos around us, but the profound nature of reality itself. But expanding uniformly in all directions, the universe unveils a cosmic ballet of immense proportions, a grand and relentless unfolding that challenges not only our scientific paradigms, but the very framework through which we grasp existence itself. The implications of this perpetual expansion are vast, reorienting every facet of cosmology and redefining the way humanity perceives its place in the cosmos. One of the most immediate and profound revelations brought forth by the expanding universe is the robust affirmation of the Big Bang theory. This foundational cosmological model suggests that everything, the galaxies, stars, planets, light, and even the laws of physics themselves, originated from an incredibly hot, dense singularity. From that primordial state, space itself began to stretch, creating a universe not expanding into something, but rather expanding space itself. Every galaxy, like raisins in rising dough, has been carried along by this universal inflation. As space stretches, so too does time. So too do the boundaries of what we can observe and theorize. This expansion provides us with more than a dramatic origin story. It gives us a cosmic clock. A finite age of the universe means we can trace a timeline billions of years long through which everything evolved. From the subtle, stochastic tremors of quantum fluctuations shortly after the Big Bang to the majestic birth of stars, the clustering of galaxies, and the rise of complex cosmic web structures, the universe's expansion offers a structured chronology of everything that has ever existed. The expansion, however, is not simply a historic footnote. It is also a harbinger of future mysteries and ultimate destinies. Will this expansion go on indefinitely, casting galaxies so far apart that their light will no longer reach one another? Will it one day slow, stop, and reverse, collapsing back into a singularity in a cosmic death spiral known as the Big Crunch? Or will it continue to accelerate, stretching the very threads of reality until nothing remains cohesive? These questions once belonged solely to the realm of philosophical speculation. Now they are deeply embedded in the pursuit of observational cosmology, particularly with the discovery of a baffling phenomenon known as dark energy. In the late 1990s, observations of distant supernovae revealed something astonishing. Not only is the universe expanding, but that expansion is accelerating. Galaxies are moving away from each other faster than ever before, driven by a repulsive force that permeates the vacuum of space. This dark energy, whose nature remains one of the most tantalizing mysteries in all of physics, is believed to constitute nearly 68% of the universe's total energy content. Alongside it is dark matter, an invisible scaffolding that shapes the formation and movement of galaxies, making up around 27%. That leaves a mere 5, an almost insignificant fraction, as baryonic matter, the ordinary, atoms that compose everything we see: stars, planets, dust, oceans, trees, machines, and human beings. Thus, our universe, which seems so filled with light and matter, is actually governed by unseen forces. The expansion of the universe, once a simple observational fact, has become a philosophical touchstone, a keystone in our attempt to unravel not just what the universe is, but why it is the way it is and what it may become. The future of the cosmos lies shrouded in theoretical frameworks, each offering a divergent vision of the eventual fate that awaits all that exists. One of the leading models is the Big Freeze, also known as the heat death of the universe. According to this scenario, the relentless expansion will never cease. Over trillions of years, galaxies will drift so far apart that their light will no longer traverse the yawning voids between them. Star formation will halt as the raw materials necessary for fusion become exhausted. Existing stars will slowly die, one by one, leaving behind remnants, white dwarfs, neutron stars, and black holes drifting in the cold darkness. The cosmos will become a desolate and inert wasteland, a silent crypt of extinguished suns and collapsed cores, where time stretches endlessly and entropy reigns supreme. But there is another path the universe might take. The Big Crunch is a scenario in which the expansion one day halts and reverses. The gravitational pull of all the mass in the universe, if sufficient, could overcome the thrust of expansion. Space would begin to contract. Galaxies would collide and merge. Temperatures would rise. Eventually, all matter and energy would be drawn inward, collapsing into a singular state of infinite density, a mirror of the Big Bang. This cyclical model proposes a universe born and destroyed in an endless loop, each death birthing a new cosmos in a grand oscillation of expansion and collapse. Yet this idea has fallen out of favor in recent decades. The observed acceleration of cosmic expansion suggests that a big crunch is unlikely, at least under current conditions. Instead, new and more exotic possibilities have emerged, such as the Big Rip. In this radical theory, the repulsive force of dark energy grows stronger over time. Not content to merely push galaxies apart, it begins to tear them apart. Then solar systems, then planets, then molecules, then atoms themselves. As the influence of dark energy intensifies, it could shred the very fabric of space-time. In the final moments before the Big Rip, the scale of destruction would move from cosmic to quantum, culminating in a final singular annihilation of all structure. Yet, even this may not be the end. Some theorists propose a universe without a beginning or end, a cosmic Ouroboros, eternally cycling through phases of birth, growth, decay, and rebirth. The cyclic universe model, or oscillatory universe theory, posits that the Big Bang was not the absolute beginning, but simply the latest in an infinite series of cosmic expansions. After each expansion reaches its limit, a contraction follows, ending in a big crunch that resets the universe, possibly under slightly altered conditions. This sequence might recur endlessly, a divine rhythm echoing across infinite time. Such models remain speculative, their mechanics unproven. They raise profound questions. Can information from one cycle pass to the next? Is there a memory embedded in the fabric of the universe itself? What mechanism could reset entropy, allowing each new universe to start fresh? Regardless of which theory ultimately proves correct, each offers not just a possible future, but a powerful lens through which to contemplate the present. These cosmological models function as more than predictions. They are tools for understanding the profound laws that shape reality, guiding both theoretical inquiry and experimental design. Our journey into the cosmos also owes an incalculable debt to one of the greatest revolutions in human thought, Albert Einstein's theory of relativity. Comprising both special relativity, 1905, and general relativity, 1915, Einstein's insights forever altered the landscape of physics and cosmology. Together, these theories redefined our conception of time, space, mass, and gravity itself. Special relativity began with a simple yet world-shattering realization. The speed of light in a vacuum is constant for all observers, regardless of their motion. From this seemingly innocuous postulate followed a cascade of radical implications. Space and time, once thought to be fixed, absolute dimensions, were instead revealed to be malleable and interdependent. They form a unified continuum, space-time, that bends, stretches, and warps in response to motion and mass. Time dilation occurs when a clock moving at high velocity ticks more slowly compared to a stationary one. Length contraction means that objects shrink along their direction of motion as their speed approaches the speed of light. But special relativity was just the beginning. General relativity took Einstein's genius a step further by incorporating acceleration and gravity. In this framework, gravity is not a force pulling objects together, as Newton had imagined, but a warping of spacetime itself. Massive objects like planets, stars, and galaxies create indentations in the fabric of spacetime, and these distortions dictate the motion of other objects. The Earth orbits the Sun not because of an invisible tether, but because it is following a curved path through a warped geometry created by the Sun's mass. This elegant geometric view of the universe has been validated countless times, from the bending of starlight during eclipses to the precise functioning of GPS satellites, which must correct for relativistic time shifts to maintain accuracy. General relativity predicted phenomena once thought to be science fiction: black holes, gravitational waves, the expansion of the universe itself. Einstein's equations laid the groundwork for the modern cosmological model, influencing everything from the behavior of high-energy particles to the structure of space-time on the largest scales. Without general relativity, we would have no mathematical framework to describe cosmic inflation, no tools to model gravitational lensing, no predictions for the behavior of matter near event horizons. It is the theoretical scaffold upon which modern cosmology is built. Together, the concepts of universal expansion, dark energy, and relativistic physics form a grand tapestry, a narrative both humbling and empowering. They tell us that we are part of a universe in motion, a universe filled with unseen forces and governed by laws that challenge our senses but reward our curiosity. They invite us to ask not only where we are and how we got here, but what it means to exist at all within such a strange and wondrous reality. And so the story continues. Each observation, each equation, each photon captured by our telescopes adds another thread to the cosmic fabric. The questions we ask of the universe echo back at us, reshaping our understanding not just of the heavens, but of ourselves. In the vast silence of space, the expansion goes on. But as the warping of space-time by mass and energy, massive objects like stars and planets distort the cosmic fabric, sculpting invisible curvatures that command the motion of everything that passes nearby. These unseen contours influence how objects move and even how time itself flows. The idea, bold and elegant, was vindicated dramatically in 1919 during a total solar eclipse. That day, light from distant stars, which should have appeared in fixed positions, was seen to bend around the sun. The arc of their altered positions precisely mirrored the predictions of Albert Einstein's equations. In that fleeting moment, a photograph captured not only the sun, but the dawning of a revolution in human thought. The universe was not what Newton imagined, but something more fluid, dynamic, and deeply connected through the geometry of existence. The implications of general relativity echoed far beyond that singular celestial event. Black holes, the enigmatic endpoints of gravitational collapse, emerged as cosmic laboratories where Einstein's equations predicted the ultimate extremity, regions of space-time so intensely warped that not even light, the universe's swiftest traveler, could escape their grip. These mysterious titans were once considered mathematical curiosities, but in the years that followed, they would come to define our understanding of high-energy astrophysics and galactic evolution. Then, almost like whispers from the universe itself, came the ripples. Gravitational waves, faint tremors in space-time generated by the violent motion of massive bodies, had been predicted in Einstein's theory, but remained undetected for nearly a century. That silence was broken in 2015 when LIGO, the Laser Interferometer Gravitational Wave Observatory, recorded the infinitesimal stretching and squeezing of space caused by two merging black holes over 1 billion light-years away. It was a soundless event, but it echoed across the scientific world like a thunderclap. It meant we could now listen to the universe, not just look at it. The silence of space-time had been breached. Beyond the frontiers of black holes and gravitational waves, general relativity reshaped cosmology itself. It became the scaffolding upon which our modern models of the universe were built. From the accelerating expansion driven by dark energy to the fine curvature of space on cosmic scales, Einstein's equations guide our understanding of the universe's evolution, from the fireball of the Big Bang to the slow cooling of the cosmos today. It has turned physics into a poetic exploration of curvature and time, energy and geometry. The universe is no longer simply a stage for the play of matter and energy. It is a dynamic participant. Einstein's theoretical edifice reached beyond academic boundaries and quietly embedded itself into the circuitry of everyday life. Without general relativity, the GPS systems that guide our cars, map our streets, and coordinate our digital lives would quickly fall out of sync. The satellites that orbit Earth experience time differently than we do, subtly but significantly. Their clocks, hundreds of kilometers above Earth, run faster due to the weaker gravitational field, while also slowing down slightly due to their high velocity. Engineers armed with relativity correct for both effects, aligning the flow of time between Earth and space to within billionths of a second. The price of ignoring relativity in GPS? You would miss your turn by miles. And then there is time itself, the beating heart of Einstein's legacy. Time dilation, the uncanny revelation that time does not tick at the same rate for everyone, is perhaps the most philosophically disorienting of all the theory's predictions. This effect arises when either velocity or gravity, or both, distort the passage of time for different observers. Near a massive object or at extreme speeds, time slows down relative to someone farther from gravity or moving slower. What once seemed constant and universal is now contingent and relative. Nowhere does this insight resonate more powerfully than in the context of space travel. Imagine an astronaut accelerating toward a distant star at near light speed. For the crew aboard the spacecraft, the journey may last a few subjective years. But on Earth, decades or even centuries may have passed. This is not science fiction. It is a direct consequence of special relativity, and it raises astonishing possibilities and dilemmas for humanity's expansion into the cosmos. The so-called twin paradox, where one twin travels on a relativistic journey and returns younger than their sibling who remained on Earth, underscores the personal, almost tragic poignancy of relativistic physics. The future of deep space missions must wrestle with these effects. Missions of prolonged duration must account not only for propulsion and life support, but also for the psychological and emotional burden of relativistic time. A journey to the stars may require leaving behind everything and everyone a traveler knows, with no hope of reunion in a shared temporal frame. What does it mean to live in a separate slice of time? How will we mourn and remember when even memory is stretched and folded by the fabric of the cosmos? Time dilation has already influenced practical aspects of spaceflight planning. For missions to Mars or other planetary bodies, engineers must calculate the effects of gravity on time. Although the time dilation at interplanetary velocities is modest, the precision required for communication, navigation, and data synchronization demands careful attention to relativistic principles. A mission that ignores these effects could experience delayed signals, unsynchronized operations, or inaccurate landings. Even a few microseconds, discrepancy can compound over months of travel into navigational errors with catastrophic consequences. Looking further ahead toward voyages beyond the solar system, these relativistic effects intensify. Achieving velocities that approach a significant fraction of light speed will necessitate breakthroughs in propulsion technology, perhaps nuclear pulse drives, antimatter engines, or the speculative Alcubierre warp drive. But whatever the method, the consequences for time will be profound. Entire civilizations could rise and fall during a single interstellar voyage. Time will cease to be a shared experience and become a personal journey. The universe will speak to each traveler in their own clock's tongue. To plan these missions, scientists and engineers must marry the elegant predictions of Einstein's equations with the brutal reality of physics. Every gram of mass must be accounted for, every second of time predicted. Communication lags of years or decades must be accepted. Colonists on a distant exoplanet may live in the future of Earth's past or the past of Earth's future. The relativistic horizon becomes a boundary not just of light, but of memory and belonging. Yet time dilation is not only a challenge, it is also a potential asset. If harnessed strategically, relativistic effects could allow future explorers to extend their subjective lifespans, to travel vast distances while experiencing only brief intervals. In this way, relativity becomes a tool not just of comprehension, but of survival. It may be that our best hope of reaching other worlds lies in surrendering to time's pliability rather than resisting it. In the final calculus, Einstein's vision of the universe has not only reshaped our equations and instruments, it has altered our very conception of reality. We live in a cosmos where the stage bends, the script evolves, and time itself is a player. The journey into this new understanding began with a theory and an eclipse, with a light bent by gravity and a man who dared to imagine a different universe. And from that moment, we have been following the curves of space-time. One ripple, one dilation, one paradox at a time. But a fundamental aspect of practical space travel lies in the profound influence gravitational waves exert on how humanity plans, executes, and imagines its ventures into the cosmos. These ripples in the very fabric of space-time, predicted long ago by Albert Einstein's groundbreaking general theory of relativity, have unlocked a breathtaking new window onto the universe. Unlike any other cosmic messenger, gravitational waves carry with them the signatures of the most violent and cataclysmic events ever to unfold across the vast cosmic expanse. Imagine colossal black holes spiraling towards each other in a deadly cosmic dance, or neutron stars colliding with a fury that forges the heaviest elements in existence. These titanic collisions send out ripples, undulating through space-time at the speed of light, distorting reality itself. When these waves wash over Earth, they bring invaluable insights, illuminating the unseen structure of the universe and revealing the fundamental forces at work. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, made history in 2015 by detecting these elusive waves for the very first time, capturing the echoes of two black holes merging in a cataclysmic embrace billions of years ago. This landmark discovery not only confirmed Einstein's century-old prediction, but opened a revolutionary field of astronomy that goes beyond light and traditional observation. Through the patterns encoded in these waves, scientists can decipher the masses, spins, and distances of these mysterious black holes, mapping out their collisions and building a cosmic catalog that reveals how black holes are born, evolve, and influence their surroundings. Moreover, gravitational waves extend their reach beyond black holes, unveiling the extraordinary physics at play when neutron stars, ultra-dense remnants of massive stars, crash into one another. These violent mergers produce bursts of heavy elements such as gold and platinum, elements that are key to understanding the nuclear processes that govern matter at its most extreme. By combining gravitational wave detections with electromagnetic signals, astronomers have crafted a powerful multi-messenger approach, painting a rich and detailed picture of neutron stars' inner workings, their composition, and their dynamic behavior. This synergy of observations is rewriting textbooks and pushing the boundaries of physics in regimes previously thought inaccessible. But the potential of gravitational waves goes even deeper, reaching back to the earliest moments of the cosmos. Just after the Big Bang, the infant universe underwent rapid inflation, a violent and mysterious expansion that would have generated primordial gravitational waves. If scientists can detect these primordial signals, they will unlock empirical evidence of the universe's birth pangs, shedding light on the fundamental particles and forces that shaped everything we know. Such discoveries promise to illuminate the conditions of the cosmos at its very inception, providing an unparalleled glimpse into the origins of space, time, and matter itself. Gravitational waves have become a transformative tool in the quest to understand the universe, revealing phenomena that were once completely hidden or unknowable. They expand our knowledge of cosmic structure, origins, and the fundamental laws that govern reality. This blossoming field melds observation with theory in novel and breathtaking ways, answering some of the deepest questions in astronomy and cosmology, and opening doors to new realms of knowledge. Wormholes, often called Einstein-Rosen bridges, emerge from the same fabric of general relativity that describes gravitational waves. These hypothetical tunnels through spacetime could provide shortcuts between distant parts of the universe, folding spacetime like a sheet of paper so that two far-flung points touch, creating a pathway that defies the vast cosmic distances that confound conventional space travel. The concept captures the imagination with the tantalizing possibility of faster-than-light travel, potentially revolutionizing human exploration of the stars. Yet, wormholes remain speculative, as they face immense theoretical and practical challenges. To remain stable and traversable, a wormhole would require exotic matter, a mysterious form of matter with negative energy density that has never been observed or created. The scientific and engineering obstacles to producing or harnessing such exotic matter are formidable. Even if stable wormholes could be created, the intense gravitational forces near their entrances could spell doom for any travelers daring to pass through. Thus, gravitational waves and wormholes represent twin frontiers of modern physics. One already reshaping our understanding of the cosmos through observation and insight, the other a tantalizing theoretical doorway that may one day redefine the limits of exploration. Together, they inspire humanity's journey into the unknown, pushing the boundaries of knowledge and daring us to dream beyond the stars. Moreover, maintaining the delicate stability of a wormhole against the relentless perturbations caused by particles and radiation passing through it presents a monumental scientific challenge. Calculations, rooted in the principles of theoretical physics, suggest that if traversable wormholes do indeed exist, their natural state might be one of extreme instability, prone to rapid collapse under the influence of everyday cosmic conditions. This fragility implies that the vast energies and precise conditions required to stabilize such phenomena are beyond anything humanity can currently achieve. Practical considerations extend beyond mere stability. The enormous energy requirements, the advanced technological capabilities necessary to even locate such cosmic anomalies, let alone create them artificially, are staggering in scale. These requirements push the boundaries of our current scientific understanding and engineering prowess, making wormholes a tantalizing yet elusive concept. Despite these formidable obstacles, the study of wormholes continues to captivate physicists and cosmologists, driving theoretical research that probes the very foundations of the universe. Drawing upon the counterintuitive realms of quantum mechanics and the still mysterious field of quantum gravity, scientists hope to uncover new insights or even innovative technological pathways that could one day make the manipulation or utilization of wormholes feasible. Presently, wormholes inhabit the imaginative domain of science fiction, yet their theoretical existence sparks profound discussions about the fabric of space-time itself, the potential limits of human travel across cosmic distances, and the fundamental laws that govern reality. In some ways, wormholes embody the ultimate scientific paradox. Their potential to revolutionize space travel is as immense as the scientific and practical barriers that currently keep them out of reach. Future breakthroughs in physics, whether through novel experiments or refined theoretical frameworks, might bring the concept closer to tangible reality, or alternatively reveal entirely new mechanisms for achieving rapid interstellar travel. Until then, the dream of using wormholes to traverse the cosmos remains a powerful inspiration, fueling humanity's enduring quest to explore the universe beyond our planetary neighborhood. Parallel to the study of wormholes, scientists have made remarkable progress in understanding the curvature of spacetime around massive objects, a cornerstone concept predicted by Einstein's general relativity. By combining precise astronomical observations with sophisticated theoretical models, researchers have developed a multifaceted approach to mapping how gravity bends and warps the cosmic fabric. One of the most powerful observational tools is gravitational lensing, an effect that occurs when light from distant stars or galaxies passes near a massive object, such as a black hole or galaxy cluster. The gravity of the massive body bends the light's path, often producing multiple images of the same celestial object, magnifying it, or creating striking arcs and rings of light known as Einstein rings. By carefully analyzing these distortions, scientists can infer the distribution and strength of gravitational fields, effectively mapping the curvature of spacetime in those regions. Another critical method involves monitoring the orbits of stars and planets around massive objects. For instance, the study of stars orbiting the supermassive black hole at the center of our own Milky Way galaxy has provided direct evidence of spacetime curvature. The star known as S2, in particular, follows a rapid, highly curved trajectory around Sagittarius A Stri, the galaxy's central black hole. Observing S2's path has allowed scientists to calculate the black hole's mass and verify the predictions of general relativity. More recently, the detection of the star's relativistic redshift, as it neared its closest approach to the black hole, offered even more direct confirmation of the warping of spacetime by intense gravitational fields. Further groundbreaking discoveries have come from the detection of gravitational waves, ripples in spacetime generated by the violent acceleration of massive objects such as merging black holes or neutron stars. Instruments like LIGO and Virgo have captured these waves, providing unprecedented insights into the dynamics of spacetime under extreme conditions. The detailed waveforms carry information about the masses, spins, and collision mechanics of the celestial bodies involved, revealing characteristics of spacetime that were previously inaccessible. These detections represent a new window into the universe, confirming and expanding upon Einstein's century-old theories. In addition, highly precise measurements within our own solar system contribute to our understanding of spacetime curvature. Missions such as Gravity Probe B have measured subtle effects predicted by general relativity, including frame dragging and geodetic precession, small shifts in the orientation of gyroscopes caused by Earth's mass and rotation. These experiments validate the complex predictions of Einstein's theory with remarkable precision, deepening our grasp of how massive bodies influence space-time. In all these endeavors, the interplay between rigorous observational data and theoretical frameworks allows scientists to build an increasingly detailed picture of how space-time behaves around massive objects. This synergy not only reaffirms Einstein's groundbreaking insights, but also lays the foundation for future explorations into the mysteries of gravity, quantum mechanics, and the ultimate structure of the cosmos. The pursuit continues, driven by humanity's insatiable curiosity to understand the universe in its most fundamental form. But also it profoundly deepens our understanding of the universe's fundamental properties, extending from the enigmatic behaviors of black holes to the complex dynamics within sprawling galaxy clusters, and offering tantalizing glimpses into new physics that may lie beyond the limits of our current scientific models. Space-time singularities, those mysterious and extreme points where gravitational forces stretch into infinity and the familiar laws of physics abruptly fail, stand as some of the most profound riddles confronting our grasp of the cosmos. Singularities exist at the heart of black holes and mark the origin of our universe itself, famously represented by the Big Bang. These extraordinary regions are characterized by densities and curvatures so immense that conventional notions of space and time disintegrate. One of the most confounding elements of singularities is their very prediction by Einstein's equations of general relativity. Under particular conditions, such as the catastrophic collapse of massive stars, these equations suggest that the gravitational field intensifies to an infinite curvature of space-time. Yet, this prediction creates a paradox: determinism, the principle that the future and past states of physical processes can be precisely predicted, breaks down. Such a scenario introduces the concept of naked singularities, singularities exposed without an event horizon to shield the outside universe from their influence. This contradicts the cosmic censorship conjecture, proposed by physicist Roger Penrose, which hypothesizes that singularities must always be hidden within event horizons, cloaking them from external observers. The interface where general relativity meets quantum mechanics is another profound mystery at the heart of singularities. While general relativity elegantly describes large-scale cosmic phenomena, stars, galaxies, the expansion of the universe, quantum mechanics governs the microscopic world of particles and their interactions. However, these two pillars of modern physics are fundamentally incompatible when faced with environments of extreme gravitational intensity and infinitesimal scales, such as those present in singularities. The quest for a comprehensive theory of quantum gravity, one that reconciles the vast cosmic scales with the quantum realm, remains one of the foremost challenges in physics. Frameworks such as string theory and loop quantum gravity offer promising but still incomplete attempts to unify these conflicting models. Layered onto this puzzle is the infamous black hole information paradox. According to classical general relativity, any information swallowed by a black hole is irretrievably lost, locked away behind the event horizon, and presumably destroyed at the singularity. Yet quantum mechanics insists that information cannot be destroyed, leading to a fundamental conflict. This paradox has stimulated a range of speculative theories, among them the holographic principle, which posits that all information contained within a volume of space can be represented as encoded on its boundary, reshaping our concepts of dimensionality and information storage in the cosmos. Turning our gaze back to the Big Bang singularity, it too poses profound questions. As we approach this initial singularity, the universe's conditions grow unimaginably hot and dense, where classical physics fails to offer adequate explanations. The mystery of what preceded the Big Bang or what mechanisms triggered it remains shrouded in scientific uncertainty, resting at the edge of current observational capability and deeply intertwined with the pursuit of a unified physical theory. Singularities, then, occupy a frontier in physics where our existing theories reach their limits, but also where the possibility of revolutionary understanding beckons. These cosmic enigmas urge scientists to extend the boundaries of knowledge, motivating ongoing research to forge a more unified and complete description of reality. Particle accelerators emerge as critical instruments in this grand scientific endeavor. By propelling particles to velocities approaching the speed of light and orchestrating their high-energy collisions, These machines simulate conditions akin to those moments just after the Big Bang. Such experimental environments allow physicists to probe the fundamental forces and constituents of matter, peeling back layers of cosmic history and structure. The Large Hadron Collider, LHC, operated by CERN, stands as the most prominent example of these accelerators. It hurls protons and heavy ions at tremendous energies, orchestrating collisions that momentarily generate an array of exotic particles, many of which exist only under such extreme conditions. By meticulously studying these ephemeral particles and their interactions, scientists rigorously test and refine the standard model of particle physics, a framework describing electromagnetic, weak, and strong nuclear forces. A landmark achievement came in 2012 with the LHC's discovery of the Higgs boson, a particle pivotal to explaining how other particles acquire mass via the Higgs mechanism. This discovery not only solidified a key element of the standard model, but also deepened our understanding of space-time itself, revealing how pervasive fields underpin the very structure of the universe. Particle accelerator experiments also delve into phenomena that might unveil new physics beyond current theories. By pushing the energy frontier, physicists search for evidence of supersymmetry, hypothetical partner particles that could resolve various theoretical challenges, or signs of extra-spatial dimensions beyond the familiar three dimensions of space and one of time. String theory, a leading candidate for a quantum theory of gravity, suggests such additional dimensions exist, potentially detectable through the byproducts of high-energy collisions. Furthermore, these experiments recreate and analyze quark-gluon plasma, a state of matter believed to have permeated the universe microseconds after the Big Bang. By smashing heavy ions together, researchers generate conditions that allow them to study how strong nuclear forces behave under extraordinary temperature and density. Understanding these forces in such environments offers crucial insights into the early evolution of the universe, painting a more detailed picture of how space-time and fundamental forces emerged and transformed. Particle accelerators also serve as testing grounds for the interplay between quantum field theory and general relativity. Predictions about particle behavior in intense gravitational fields can be indirectly tested by examining the outcomes of high-energy collisions. Such experiments advance the quest for a quantum gravity theory by assessing the mutual consistency of existing frameworks. In essence, particle accelerators function both as microscopes and time machines, delving into the deepest layers of reality and the earliest cosmic moments. Through their operation, scientists do not merely confirm established theories, but challenge them, push them beyond their limits, and open pathways toward discovering new principles that will ultimately redefine our comprehension of the universe. But this journey is far from over. Each collision, each fleeting particle traced and studied, unfolds new chapters in the grand narrative of existence, urging humanity to continuously seek answers to the profound mysteries embedded within the fabric of space-time itself, but also unravel mysteries that reach far beyond the horizon of our current understanding of space-time and the intricate unseen forces that weave the fabric of the cosmos. The theoretical implications of faster-than-light travel, often abbreviated as FTL, plunge us into a realm of profound possibilities and daunting paradoxes, touching the very bedrock of physics and challenging the way humanity has long perceived the universe. According to Einstein's special theory of relativity, as any object accelerates towards the speed of light, its mass inflates to an infinity, demanding an impossible amount of energy for further acceleration. This principle seems to erect an impenetrable barrier against the notion of traveling faster than light, at least by conventional means. Yet, the human imagination and theoretical physics both persist in pushing this boundary, conjuring speculative frameworks that might, in principle, bend the rules rather than break them outright. One of the most captivating of these speculative constructs is the warp drive, a concept thrust into scientific discourse by the Mexican physicist Miguel Alcubierre in 1994. Alcubierre's bold proposition imagines the possibility of contracting the very fabric of space-time ahead of a spacecraft, while simultaneously expanding it behind. This cosmic contortion would enable the craft to effectively surf a wave of space-time itself, achieving effective speeds beyond light without the spacecraft locally exceeding light speed within its own bubble of spacetime. This idea elegantly skirts the relativistic speed limit by shifting spacetime around the craft, rather than accelerating the craft through spacetime. Yet this vision demands the existence of exotic matter with negative energy density, a form of matter that defies the characteristics of everything observed in the known universe. To date, no experimental evidence supports the feasibility of such matter, making Alcubierre's warp drive a beautiful yet speculative solution that sits at the interface between physics and imagination. Parallel to the warp drive concept are the enigmatic structures known as wormholes or Einstein-Rosen bridges, theoretical tunnels connecting distant points in spacetime. These cosmic shortcuts, if stable and traversable, could revolutionize our understanding of distance and travel. They would offer instantaneous passage across vast cosmic expanses, potentially collapsing interstellar journeys that would normally take millennia into moments. However, like the warp drive, maintaining a stable wormhole seems to require exotic matter and energy configurations far beyond our current technological and theoretical grasp. The challenge of engineering or even detecting such phenomena remains one of the most tantalizing puzzles in modern physics. The theoretical implications of FTL travel ripple outward with staggering consequences. One of the most unsettling is the potential violation of causality, the fundamental principle that cause precedes effect. Under the framework of relativity, FTL travel could enable scenarios where effects precede their causes, opening the door to paradoxes, such as traveling backward in time. This shatters our linear understanding of time and forces physicists to confront deep questions about the nature of reality, potentially demanding new physics or novel interpretations of time itself. Beyond the philosophical quandaries, the practical consequences of FTL mechanisms, should they exist, are transformative. They would redefine the scale and connectivity of the universe, turning distant galaxies into reachable destinations and interstellar travel into a reality. This would open vast new frontiers for the search for extraterrestrial life, the colonization of distant worlds, and the evolution of humanity's future as a cosmic species. The mere possibility of transcending the speed of light rekindles age-old dreams of exploration and connection across the cosmos. Intriguingly, recent advancements in quantum mechanics hint at phenomena that seem to echo certain aspects of FTL communication. Quantum entanglement, Einstein's spooky action at a distance, demonstrates how particles can instantaneously influence each other over vast separations. However, these quantum correlations do not transmit usable information faster than light, thus preserving the core tenet of relativity and sidestepping causal paradoxes. Still, these effects challenge classical intuition and invite deeper exploration of the quantum fabric underlying reality. While the notion of FTL travel firmly resides within the domain of theoretical speculation and science fiction, its implications are inextricably linked to the foundations of physics. The exploration of warp drives, wormholes, and quantum phenomena forces us to reconsider the very essence of space-time and the universe's structure. Such intellectual ventures push the limits of scientific knowledge and may someday spark revolutionary breakthroughs or fundamental paradigm shifts. Among the most ambitious attempts to unify our understanding of the universe is string theory, a framework seeking to reconcile quantum mechanics with general relativity. At its core, string theory replaces the idea of point-like particles with tiny vibrating strings as the fundamental building blocks of reality. This reimagining of matter and forces hints at a radically different conception of space-time, one that could encompass multiple dimensions beyond the familiar four and possibly accommodate phenomena currently beyond the reach of conventional physics. String theory's multidimensional landscape suggests that space-time itself might be more malleable and complex than previously imagined, opening avenues where faster-than-light travel or similar effects could find theoretical grounding. While still unproven, this elegant yet mathematically intricate theory fuels ongoing research and debate, embodying humanity's relentless quest to decipher the cosmos. In this grand narrative, the quest to transcend light speed is not merely about transportation. It is a journey into the deepest mysteries of existence, where physics meets philosophy and the boundaries between science and imagination blur. The very fabric of space-time invites us to explore beyond what we know, to question our assumptions, and to dream boldly of a universe where the impossible may one day become reality. But rather, one-dimensional strings that oscillate in a symphony of modes, each vibration resonating as a distinct particle in the cosmic orchestra. These strings do not merely exist, they vibrate with purpose, embodying the very essence of matter and energy. The fundamental shift from point particles to these dynamic strings has revolutionized our understanding of space-time itself, casting open the doors to dimensions beyond the familiar. String theory demands a radical reimagining of the universe's structure, insisting that the fabric of reality stretches far beyond the three spatial dimensions and one temporal dimension we navigate daily. Instead, it paints a grander, more complex canvas, a universe woven from 10, sometimes 11 dimensions. Yet these additional dimensions evade direct observation, hidden away in minuscule scales, curled tightly like cosmic origami, so minute that our instruments and experiments cannot yet reveal them. This concept of compactified dimensions is not mere mathematical curiosity. It offers profound implications that ripple through every corner of physics. Within this expanded dimensional framework lies the promise of unification. String theory offers a cohesive stage where all fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces play harmoniously. Traditional physics treats gravity as a geometric curvature of four-dimensional spacetime, a legacy of Einstein's groundbreaking insight. But string theory elevates this concept, embedding gravity within a multidimensional geometric structure, suggesting that gravity's subtlety and uniqueness stem from its interaction with these hidden dimensions. The dance of strings within this broader arena may reveal why gravity is so weak compared to the electromagnetic force, perhaps because it leaks into dimensions beyond our perception. Furthermore, the theory confronts the paradoxes that haunt the union of general relativity and quantum mechanics. Singularities, such as those inside black holes or at the inception of the Big Bang, stand as insurmountable walls within classical physics, zones where calculations dissolve into infinite values and known laws crumble. Here, string theory's extended entities and extra dimensions act as a buffer, smoothing these infinities and stitching together a consistent quantum theory of gravity. The microscopic structure of strings, their vibrations and interactions, may provide the mathematical glue that binds the macroscopic curvature of spacetime to the probabilistic nature of the quantum world. Among the most captivating features of string theory are D-branes, multidimensional membranes, where strings anchor their ends. These branes are more than mathematical constructs. They could represent entire universes, suggesting that our four-dimensional cosmos might be a mere brain floating in a higher dimensional expanse. This brain world perspective ignites new possibilities. Gravity, unlike other forces, may seep into the higher dimensional bulk, explaining its relative weakness and potentially offering observable consequences through subtle deviations in gravitational behavior. The theory's richness deepens further with the notion of dualities, astonishing equivalences between seemingly disparate physical theories. These dualities blur the boundaries between different string theories and between theories operating in different dimensions. They imply that space and time, traditionally viewed as fundamental backdrops, may instead emerge from deeper, more abstract structures. Reality through this lens is not a fixed stage, but a dynamic, emergent phenomenon shaped by underlying symmetries and connections. String theory does not merely propose extra dimensions or novel entities. It revolutionizes the very foundation of physics by merging the geometric elegance of relativity with the quantum's probabilistic dance. This revolutionary framework offers not just theoretical coherence, but also fertile ground to tackle physics' deepest enigmas, from the unification of forces and the nature of black holes to the origins of the universe itself. Einstein's general relativity majestically describes gravity as the warping of space-time by mass and energy, bending the trajectories of planets, stars, and light. Quantum mechanics, by contrast, governs the microscopic realm with extraordinary precision, explaining the erratic yet rule-bound behaviors of electrons, photons, and quarks. Reconciling these two pillars into a single harmonious theory remains one of physics' grandest quests. String theory strides into this arena, providing a promising scaffold upon which a quantum theory of gravity may be constructed, reshaping our understanding of reality at the most fundamental level. However, these two monumental frameworks of physics, standing as titans on the frontier of human knowledge, function on principles so fundamentally divergent that their unification remains one of the greatest scientific enigmas of the modern age. The quest to forge a coherent theory of quantum gravity, an elegant marriage of the quantum mechanics governing the microscopic and the general relativity dictating the cosmos, has vexed physicists for generations. It is a pursuit not merely of academic interest, but one that promises to peel back the veils of reality itself, revealing truths about the birth of the universe, the enigmatic nature of black holes, and the very fabric of space-time woven at the Planck scale, a realm so unimaginably minuscule that classical intuition dissolves, replaced by a confluence where quantum phenomena and gravity entwine. This struggle to synthesize these divergent conceptual giants extends beyond theoretical elegance. It touches on profound mysteries that underpin our existence. Among these is the elusive nature of dark energy and dark matter, two components that overshadow the familiar matter composing stars, planets, and life itself. Observations from the most sophisticated telescopes and cosmic surveys have consistently demonstrated that ordinary, visible matter accounts for a mere 5% of the universe's total energy content. In stark contrast, approximately 70% is attributed to dark energy, a mysterious force accelerating the expansion of the universe, while dark matter, invisible yet gravitationally influential, constitutes about 25%, shaping the structure and evolution of galaxies. Despite their overwhelming presence and critical role in cosmic architecture, the true essence of dark energy and dark matter remains shrouded in mystery. Scientists grapple with these invisible components, striving to understand what they are made of, how they interact, and what their existence implies for the laws of physics. Unlocking their secrets could revolutionize our understanding of relativity, gravity, and the cosmos as a whole, reshaping the narrative of the universe's past, its current expansion, and its ultimate destiny. Turning our gaze from the cosmic scale to the possibility of life beyond Earth, scientists deploy an astonishing arsenal of tools and methodologies, blending cutting-edge technology with humanity's insatiable curiosity. The search for extraterrestrial life is a multifaceted endeavor that explores distant stars and their planetary companions, probes the harsh environments of our own solar system, and listens for whispers from civilizations far beyond our reach. One cornerstone of this search is the study of exoplanets, worlds orbiting stars other than our Sun. With the advent of telescopes like Kepler and its successor, the Transiting Exoplanet Survey Satellite, TESS, astronomers have transformed the night sky into a treasure trove of potential habitats. These instruments identify exoplanets by detecting minute dips in a star's brightness when a planet crosses its face, a method known as transit photometry. Once these distant worlds are cataloged, their potential for habitability is assessed, primarily by calculating their position relative to their star's habitable zone, the Goldilocks zone, where conditions might permit liquid water, an essential ingredient for life as we understand it. Yet, determining habitability goes beyond mere orbital parameters. Upcoming instruments, notably the James Webb Space Telescope, promise to revolutionize our capacity to analyze exoplanet atmospheres. By detecting chemical signatures, oxygen, methane, water vapor, and other biosignatures, these observatories will search for the subtle fingerprints of life, molecules that might hint at biological processes billions of miles away. Complementing this cosmic perspective is the study of extremophiles on Earth, organisms that thrive in environments once thought utterly inhospitable. These remarkable life forms endure extremes of temperature, acidity, radiation, and pressure that would obliterate most known species. From the scalding hydrothermal vents deep in the ocean, to the acidic pools of sulfur springs, to the frozen expanses of Antarctica's icy deserts, extremophiles challenge our assumptions about where life can persist. These insights profoundly inform astrobiology, the study of life beyond Earth. If organisms can flourish in Earth's harshest niches, might life find sanctuary in the subsurface oceans of icy moons like Europa or Enceladus, warmed by tidal forces beneath their frozen crusts? Could microbial life endure beneath the harsh radiation and thin atmosphere of Mars, hidden safely underground? The answers could redefine our understanding of the limits of life. Within our solar system, robotic explorers, Mars rovers such as Perseverance, carry sophisticated instruments designed to detect signs of past or present life. These rovers analyze soil, rocks, and the atmosphere for biosignatures and chemical markers indicative of biological activity. Mars, with its evidence of ancient riverbeds and periodic methane spikes, tantalizes scientists with the possibility that it once hosted microbial ecosystems. Simultaneously, missions to the icy moons aim to penetrate their frozen surfaces and analyze the oceans beneath. Plumes of water vapor erupting from Enceladus and complex organic molecules detected on Titan, Saturn's largest moon, suggest active chemical environments where life could potentially take root. Beyond physical exploration, radio telescopes sweep the skies, listening intently for signals from intelligent extraterrestrial civilizations. This endeavor, known as SETI, Search for Extraterrestrial Intelligence, represents humanity's attempt to find company in the vast cosmic ocean through the detection of deliberate communications or anomalous radio emissions. The study of extremophiles further expands the possible habitability map, highlighting how life adapts to survive extremes once considered prohibitive. Organisms known as thermophiles thrive near boiling hydrothermal vents, acidophiles in highly acidic conditions, alkaliphiles in strongly basic environments, and radio-resistant microbes withstand intense radiation. These adaptations illuminate potential habitats on other worlds, such as the sulfuric acid clouds of Venus or the alkaline hydrothermal vents hypothesized on Mars. On Earth, environments such as the dry valleys of Antarctica serve as analogs for extraterrestrial terrains, offering clues to how life might endure on frozen moons or the frigid polar regions of Mars. The resilience of extremophiles inspires scientists to think expansively, breaking free from traditional models and embracing a broader view of life's tenacity. This burgeoning understanding has fueled optimism that life, whether microbial or complex, may exist beyond our pale blue dot. The discovery of thousands of exoplanets in habitable zones bolsters the possibility of Earth-like environments elsewhere. Among these, planets such as Kepler 452b and Proxima Centauri b present tantalizing prospects due to their size, composition, and position relative to their stars. Furthermore, the presence of organic molecules, the essential building blocks of life throughout the galaxy detected in meteorites, comets, and interstellar clouds, hints that the seeds of life might be widespread. On Titan and Enceladus, these compounds suggest chemical pathways that could give rise to life or prebiotic chemistry, adding local intrigue to the broader cosmic search. Mars continues to intrigue with its methane fluctuations and sedimentary deposits, pointing toward a wetter, warmer past where life might have once flourished. The presence of methane, particularly its seasonal variation, provokes debate about its origin, whether biological or geological, but it remains one of the most compelling clues to the planet's potential habitability. Collectively, these discoveries weave a rich tapestry of possibility. Though no definitive evidence of extraterrestrial life has yet been found, the accumulation of knowledge, from quantum gravity's mysteries to the tenacity of life on Earth and the hunt for distant biosignatures, pushes the boundaries of human understanding. It challenges our imagination to envision life not merely as an earthbound phenomenon, but as a cosmic principle that might manifest in myriad forms across the universe. This expanding horizon invites us to keep looking, keep exploring, and keep questioning, for within these pursuits lies the profound hope of discovering our place in the vast, mysterious cosmos. But the principles of biology and evolution offer a remarkable foundation from which to imagine the birth and growth of life on planets vastly different from our own. Picture a world where gravity is relentless and unyielding, tugging at every molecule with a force far greater than Earth's familiar pull. In such a realm, evolutionary pressures would sculpt organisms of extraordinary resilience and strength, their bodies forged to defy the constant weight pressing down upon them. These beings might possess muscles dense as steel, limbs forged for power and endurance, and bodies compacted into squat forms designed to resist collapse. Imagine creatures whose very skeletons have evolved to be a latticework of strength, minimizing strain and maximizing support beneath a sky heavy with gravity's pull. And yet, the adaptations would not end at mere strength. The relentless gravity would demand that the cardiovascular systems of these life forms become masterpieces of efficiency and resilience. The heart, veins, and arteries would face a daunting challenge, pumping life-sustaining blood against an unceasing downward pull that could otherwise starve tissues of oxygen and nutrients. Evolution could craft hearts capable of extraordinary force and precision, vessels lined with reinforced cells that prevent collapse or leakage under immense pressure, and regulatory systems finely tuned to maintain equilibrium in this demanding environment. Every heartbeat would be a testament to biological ingenuity, a rhythm designed not only for survival, but for thriving under conditions that would crush lesser life. Meanwhile, consider a planet bathed not in gentle sunlight, but in a harsh glare of radiation, orbiting a star that bathes its surface in intense ultraviolet rays or deadly X-rays. Here, the narrative of life would be one of relentless defense and repair. Life forms on such a world would evolve astonishing mechanisms for DNA repair, capable of reversing damage that, on Earth, would spell cellular death. Microbial organisms might develop enzyme complexes so efficient that they mend genetic material faster than it is broken, maintaining the integrity of life's blueprint in a hostile environment. Multicellular beings might cloak themselves in protective armor, thick layers of pigment that absorb and neutralize harmful radiation, or exoskeletons that shield vital organs from damage. These adaptations would not be mere fantasies, but echoes of extremophiles on Earth, such as Deinococcus radiodurans, a bacterium renowned for its near-miraculous ability to survive doses of radiation that would obliterate most other life. It is a living testament to nature's capacity to conquer extremes, hinting at the possibilities that await beyond our planet. Delve deeper still into the realms of possibility where chemical foundations of life differ radically from our own. On a distant moon like Titan, with its lakes of liquid methane and ethane under a frozen alien sky, life might have evolved not with water, but with these hydrocarbons as solvents. In such frigid conditions, the very chemistry of life would shift. Membranes encasing cells might be composed of exotic molecules stable at ultra-low temperatures, while metabolic pathways would operate with exquisite efficiency to harness the scant energy available. The notion of silicon-based life replacing carbon as the structural backbone adds another layer of speculation. Silicon's chemistry allows for stable, complex molecules in environments inhospitable to carbon life, offering a theoretical pathway for life forms profoundly alien, yet governed by the same fundamental laws of chemistry and physics. The interaction between life and its stellar environment could also drive revolutionary shifts in biological processes like photosynthesis. On a world orbiting a dim red dwarf star where visible light is scarce but infrared radiation abounds, photosynthetic organisms might evolve pigments finely tuned to capture this longer wavelength energy. These pigments would harness the abundant infrared light to fuel life's essential processes, creating ecosystems based on a spectrum of light unfamiliar to Earth's greenery. Conversely, on planets around hotter, more energetic stars, organisms could develop sophisticated pigments and protective systems to not only survive but thrive under intense ultraviolet radiation, using it to their advantage while minimizing cellular damage. This dynamic interplay between biology and star type highlights evolution's versatility and the endless potential for life's adaptation across the cosmos. Such hypothetical scenarios illuminate the vast adaptability and creative power inherent in evolution by natural selection. While the precise forms extraterrestrial life might take remain shrouded in mystery, the study of Earth's extremophiles, organisms flourishing in the harshest, most unlikely conditions on our own planet, offers invaluable clues. These organisms demonstrate that life's resilience and diversity far exceed our initial expectations, that thriving in acidic hot springs, deep ocean vents, and radioactive waste. Each discovery expands the boundaries of what we consider possible, pushing the horizons of astrobiology and the search for life beyond Earth. The potential discovery of microbial life on Mars, for example, would represent a watershed moment in human history and science. It would confirm that life is not a terrestrial anomaly, but a cosmic phenomenon, arising independently or spreading through the solar system. Such a finding would redefine our understanding of life's ubiquity and its origins, suggesting that the universe may teem with life in myriad forms and environments. This revelation would ignite scientific exploration with unprecedented vigor, focusing attention on habitable zones within countless star systems, refining our models of planetary habitability, and inspiring missions designed to detect life's subtle signatures. Moreover, microbial life on Mars would be a living record of the planet's geological and climatic past. It would reveal how life adapts over eons to shifting conditions, surviving cold deserts, radiation bombardment, and scarce resources. These tiny organisms would tell stories of endurance, adaptation, and evolution in a world once thought barren. Their study would illuminate not only Mars's history, but the processes that shape life itself, providing insights that could apply to Earth and beyond. In sum, the principles of biology and evolution serve as a powerful lens to envision the astonishing diversity of life that could emerge under the universe's countless variations of environment. They remind us that life, driven by natural selection and shaped by environmental pressures, can manifest in forms and functions far removed from terrestrial norms. The quest to understand these possibilities fuels humanity's relentless curiosity, driving exploration and discovery that expand our place in the cosmos and deepen our appreciation of life's boundless potential. But understanding the origins of life on Mars could unlock a trove of vital information about the planet's ancient environments, offering a glimpse into a world that may once have been capable of nurturing life. If life truly emerged independently on Mars, it would revolutionize our understanding of biology by suggesting that life can arise under a far broader range of conditions than those previously thought possible, conditions that may differ radically from the wet, warm cradle of early Earth. Alternatively, should Martian microbes bear striking genetic or biochemical similarities to terrestrial life, this could lend compelling support to panspermia theories. These hypotheses propose that life might not be confined to one planet, but can hitch rides across the cosmos on meteoroids, comets, or other celestial bodies, effectively seeding multiple worlds with the raw ingredients for biology. The ramifications of such a discovery are profound and multifaceted. In the realm of astrobiology, it would galvanize the scientific community to develop advanced methodologies and cutting-edge technologies designed to detect life, especially in extreme environments that challenge our Earth-centric understanding of habitability. The search for life would no longer be an isolated quest confined to Mars alone, but would extend with renewed vigor to other promising celestial bodies in our solar system, moons like Europa, Enceladus, and Titan. These icy worlds, cloaked beneath their frozen surfaces, are suspected to harbor subsurface oceans where microbial life might thrive, concealed from direct observation, yet detectable with refined instruments and carefully designed exploratory missions. This would ignite a new era of space exploration, marked by ambitious, sophisticated missions aimed at probing these distant moons and planets with unparalleled precision. The goal would be to detect microbial communities without disrupting their fragile ecosystems. Ethically and philosophically, the discovery of Martian microbes would shake the foundations of humanity's self-perception, compelling us to reconsider our place in the universe. It would challenge long-held beliefs about the uniqueness of human life and raise provocative questions about the likelihood of intelligent civilizations scattered across the cosmos. Furthermore, the implications would ripple through debates surrounding the colonization of Mars and beyond. The presence of indigenous extraterrestrial life would necessitate stringent protections to preserve these alien ecosystems, transforming legal and ethical frameworks governing space exploration. Discussions about planetary stewardship would become central, shifting priorities toward conservation and respectful coexistence with extraterrestrial life forms rather than unfettered exploitation. From a practical standpoint, the discovery would revolutionize planetary protection protocols, which are currently designed to minimize contamination risks between Earth and other worlds. If Mars hosts native life, preventing the cross-contamination of Earth microbes with Martian organisms would become paramount, necessitating the development of far more rigorous sterilization methods for spacecraft and advanced quarantine procedures for any samples returned to Earth. This heightened caution would safeguard not only Mars's pristine environments, but also Earth's biosphere from potential biological hazards. In the grand tapestry of science, uncovering microbial life on Mars would be a watershed moment. It would reshape our understanding of biology, drive technological innovations, spur new exploratory missions, and provoke profound ethical and philosophical reflections. Humanity would take a transformative step toward grasping the diversity and pervasiveness of life in the universe, forever altering our cosmic perspective. Parallel to the search on Mars, the search for extraterrestrial intelligence, SETI, remains a critical frontier. Dedicated researchers deploy sophisticated technologies to scan the cosmos for signals from intelligent civilizations beyond Earth. At the heart of these efforts are powerful radio telescopes capable of sweeping the skies for faint radio waves that might bear the unmistakable imprint of artificial origin. Among the vast spectrum of frequencies monitored, special attention is given to a narrow band around 1,420 megahertz, a frequency known as the water hole. This band is naturally emitted by neutral hydrogen, the universe's most abundant element, and is thought to be a logical choice for an intelligent civilization attempting interstellar communication, given its cosmic significance and minimal background noise. The quest for intelligent signals is far from haphazard. It involves meticulously organized strategies for data collection and analysis, employing advanced algorithms and powerful software to process enormous data sets. These tools filter out terrestrial radio interference and natural celestial noise, seeking narrowband signals that stand apart from the random hiss of cosmic background radiation. Such signals, typically characterized by their distinct, concentrated frequencies, are widely regarded as potential hallmarks of technologically produced transmissions. Projects like SETI at Home have expanded the search by enlisting the help of millions of volunteers worldwide. By tapping into the collective processing power of personal computers, these initiatives democratize the search for extraterrestrial intelligence, massively boosting computational resources available to researchers. Beyond radio waves, optical SETI presents another promising frontier, using optical telescopes to detect brief, powerful flashes of laser light that could be deliberate attempts at interstellar signaling. These ephemeral bursts, if identified, would mark an entirely new mode of communication, expanding our search parameters far beyond the traditional radio frequency domain. In both the biological search on Mars and the technological quest of SETI, humanity is engaged in a profound journey. It is a journey driven not merely by curiosity, but by the deep, innate desire to connect with life beyond our home planet, to uncover the mysteries of our origins, and to comprehend our place in the vast cosmic expanse. This endeavor challenges us to push the limits of technology, philosophy, and ethics, promising to reshape the narrative of life and intelligence in the universe for generations to come. But powerful laser pulses sent from distant civilizations might be the cosmic whispers we have been yearning to hear, piercing the vast ocean of space with signals that travel unimaginable distances. These pulses, brief yet unmistakably artificial, could illuminate the dark void as unmistakable signatures of intelligent technology far beyond our world. State-of-the-art photo detectors attached meticulously to the most advanced telescopes vigilantly scan the sky with unwavering focus, hunting for these fleeting bursts of light that stand apart from the continuous glow of stars. Unlike the steady shimmer of celestial bodies, these pulses flash momentarily, like cosmic Morse code, drawing the attention of those who seek to unravel the mysteries of the universe. And as the quest deepens, a sophisticated layer of targeting has transformed the search, concentrating efforts on specific star systems that cradle potentially habitable exoplanets. Our knowledge of these distant worlds, once speculative and vague, has flourished thanks to groundbreaking missions like Kepler and TESS, which have revealed countless planets orbiting distant suns, some with environments that could nurture life. Armed with this treasure map of promising candidates, SETI researchers now focus their instruments with precision, narrowing their gaze toward the most likely abodes of extraterrestrial intelligence. This focused approach not only optimizes precious observation time, but also magnifies the possibility of detecting something truly extraordinary. Moreover, the search for extraterrestrial signals does not exist in isolation. It is a grand global symphony of collaboration where astronomical surveys and observatories across the planet share data and insights in real time. This networked vigilance enhances the ability to rapidly confirm or disprove potential signals, distinguishing genuine cosmic communications from mundane terrestrial interference, those all too common false alarms caused by earthly technology. By viewing a candidate's signal from multiple angles and instruments, the global scientific community ensures that any potential discovery is subjected to rigorous scrutiny before it is embraced as the herald of extraterrestrial contact. The implications of such a discovery would be staggering, a profound shift that would forever alter humanity's understanding of its place in the cosmos. To detect an intelligent signal from beyond our solar system would be to bridge the cosmic divide, affirming that we are not alone in this vast universe. Therefore, SETI researchers approach their work with both passionate curiosity and meticulous care, documenting every observation with exacting detail and subjecting findings to robust peer review. This painstaking rigor is essential to validate claims that could redefine our species' story, ensuring that any announcement of contact is both credible and compelling. Until that epochal moment arrives, the ongoing search stands as a testament to humanity's enduring curiosity and relentless pursuit of one of the universe's most profound questions: are we alone? The journey is not without its tantalizing mysteries, chief among them the enigmatic "wow" signal detected in 1977, a singular, extraordinary blip in the cosmic static that continues to haunt the imaginations of scientists and enthusiasts alike. On August 15th of that year, Jerry R. Eman, a volunteer astronomer working with the Ohio State University's Big Ear radio telescope, noticed an anomaly unlike anything recorded before. The signal he detected was a narrowband radio burst, astonishingly strong, about 22 times greater than the usual cosmic background noise. Lasting a mere 72 seconds, this signal was so striking that Eamon circled it in red ink on the computer printout and wrote the now famous exclamation, "Wow," beside it, immortalizing the event. This brief flash has since become a cornerstone of the search for extraterrestrial intelligence, a beacon of hope and mystery. But the origin of the WOW signal remains elusive, shrouded in cosmic ambiguity. The source appeared to emanate from a patch of sky within the constellation Sagittarius, near the star group Chi Sagittarii, roughly 120 light-years from Earth. Despite numerous intensive follow-up observations over the decades, neither Eamon nor other astronomers have been able to detect the signal again. This singularity, a signal heard once and never again, has fueled endless speculation. Was it a genuine message from an alien civilization, a fleeting cosmic transmission sent across the void? Or was it a rare, poorly understood natural phenomenon masquerading as intelligence? The characteristics of the WOW signal add to its enduring allure. Its narrow bandwidth, approximately 10 kilohertz, starkly contrasts with the broad frequency ranges typical of natural cosmic radio sources, which usually produce a diffuse spectrum of emissions. Such a focused signal aligns closely with what one might expect from an intentional broadcast designed to pierce interstellar distances. Furthermore, the frequency at about 1,420 megahertz coincides with the hydrogen line, the emission frequency of neutral hydrogen atoms, a universal cosmic marker. Scientists speculate this frequency would be an ideal channel for interstellar communication, a sort of cosmic hailing frequency understood by any technologically advanced civilization aware of the universe's fundamental building blocks. Many hypotheses have been proposed to explain the WOW signal, weaving a tapestry of scientific and speculative ideas. Some suggest it could have been a signal from interstellar civilizations using deliberate broadcasts, while others argue for terrestrial interference, such as reflected signals from Earth-based transmissions bouncing off space debris. However, no theory has yet been conclusively proven. The absence of any repeated detection complicates efforts to confirm the signal's nature, leaving the mystery tantalizingly open. Despite this, the possibility that the WOW signal represents a genuine message from an alien intelligence continues to captivate scientists and the public alike, fueling dreams of cosmic neighbors. Skeptics often caution that without repeatability, extraordinary claims cannot be substantiated. They propose that Earth-based sources, including reflections or rare atmospheric phenomena, could mimic such signals. Yet the WOW signal's unique properties defy easy classification and demanding continued vigilance and inquiry. The search for extraterrestrial intelligence persists, driven by humanity's insatiable desire to connect beyond our planetary confines. It is a story of hope, patience, and unyielding curiosity, of scanning the infinite night with instruments tuned not just to the heavens, but to the possibility of conversation across the stars. Every flash of light, every brief pulse in the vast darkness carries the promise that somewhere out there, another mind may be reaching back, waiting for us to answer. But this remains speculative, shrouded in an aura of tantalizing mystery that continues to baffle scientists and ignite imaginations alike. The Big Ear Telescope, a pioneering instrument in the search for extraterrestrial intelligence, was ingeniously engineered to scan the heavens in two perpendicular directions simultaneously. Yet, the enigmatic signal known as the WOW signal was detected only in one channel, leaving the other completely silent. This asymmetric reception deepens the mystery. If the signal had originated from terrestrial sources or nearby Earth satellites, logic dictates it would have manifested in both channels. Instead, only a singular detection hints at an origin beyond our familiar environment. The signal's duration and shape also defy conventional explanation. Satellite transmissions, carefully studied and cataloged, do not mimic the WOW signal's peculiar characteristics, making it increasingly difficult to dismiss this cosmic whisper as mere interference or human-made noise. The signal's elusive nature emphasizes the profound challenges inherent in the search for extraterrestrial intelligence. It is a persistent reminder not only of the immense vastness and complexity of the cosmos, but also of the technological and methodological limits that constrain humanity's reach into the unknown. Decades have passed since that fateful detection, yet the WOW signal remains a beacon of intrigue, inspiring astronomers, researchers, and amateur skywatchers worldwide. The hope lingers that someday, somewhere, a signal of similar or greater significance may arrive, one that could provide the definitive evidence that intelligent life exists beyond Earth's fragile sphere. Meanwhile, within our own solar system, the quest for life takes a more tangible form. The potential for life on the moons of Jupiter and Saturn has captivated astrobiologists and planetary scientists alike, owing to the unique and tantalizing environments these distant worlds harbor beneath their frozen exteriors. Europa, Jupiter's ice-encased moon, emerges as a prime candidate in the search for life. Its surface is a labyrinth of gleaming ice etched with dark fissures and ridges, hinting at the dynamic processes beneath. Beneath this frozen shell lies a vast subsurface ocean, kept liquid not by sunlight but by the relentless tidal forces exerted by Jupiter's immense gravity and the gravitational interplay with neighboring moons. The Galileo spacecraft's observations lend weight to this theory, having detected a magnetic field consistent with a salty, conductive ocean beneath the ice. This ocean, in direct contact with a rocky mantle below, presents the tantalizing possibility of chemical interactions akin to those that fuel life on Earth. On Earth, hydrothermal vents found along the ocean floor harbor rich ecosystems that thrive in the absence of sunlight, relying instead on chemosynthesis, an energy process converting chemicals into life-sustaining energy. If such vents exist on Europa's seafloor, they could offer the critical conditions necessary to support microbial life, a biological spark flickering in the dark depths. Saturn's moon Enceladus presents an equally fascinating tableau. Smaller than Europa, it nevertheless holds secrets of its own. The Cassini spacecraft's daring flybys unveiled spectacular geysers erupting from Enceladus's south polar region. These plumes, rich in water vapor, molecular hydrogen, and organic compounds, offer compelling evidence for a hidden ocean beneath the icy shell. The detection of molecular hydrogen, in particular, signals ongoing hydrothermal activity where water interacts with rock on the ocean floor, an environment that on Earth serves as a cradle for life. This chemical energy source elevates Enceladus as a prime candidate in the search for extraterrestrial microbes. Titan, another of Saturn's enigmatic moons, beckons with a completely different environment that challenges our Earth-centric notions of habitability. Cloaked in a dense, nitrogen-rich atmosphere, Titan boasts liquid hydrocarbon lakes, vast seas of methane and ethane sprawling across its surface. This alien chemistry poses a provocative question. Could life, utterly unlike our own, evolve using hydrocarbons as solvents instead of water? Scientists speculate that Titan's unique chemical milieu could foster complex organic molecules and even prebiotic chemical reactions, precursors that might one day lead to life forms adapted to these strange cold lakes. Beyond these, Ganymede and Callisto, two of Jupiter's larger moons, harbor signs of subsurface oceans beneath their thick ice shells, adding to the growing roster of potential abodes for life in our cosmic neighborhood. Though less explored, their vast hidden oceans widen the scope of astrobiological interest, expanding the boundaries of where life might take root. The existence of extremophiles on Earth, organisms that thrive in boiling acidic springs under crushing subterranean pressure or within the frozen wastelands of Antarctica, bolsters the possibility that life could adapt to the harsh conditions found on these distant moons. Life's tenacity and versatility on Earth illuminate the potential for existence in even the most alien of environments. The exploration of these moons demands cutting-edge technology and international collaboration. Missions like NASA's Europa Clipper are poised to perform detailed reconnaissance of Europa's ice shell and hidden ocean, while the European Space Agency's JUICE mission plans to study Ganymede and other Jovian moons extensively. Instruments capable of analyzing surface compositions, studying erupting plumes, and potentially drilling through thick ice to sample subsurface oceans represent the next frontier in this grand search. Confirming extraterrestrial life would be nothing short of revolutionary, reshaping biology, chemistry, and humanity's understanding of its place in the cosmos. It carries implications not only for science, but for philosophy, spirituality, and the collective human narrative. Yet the challenge is daunting. The vast distances separating humanity from these celestial bodies are staggering. Even within our solar system, journeys to Mars, Europa, or Enceladus require years of travel and immense resources. Beyond that, interstellar distances multiply the difficulty exponentially. The nearest star system, Alpha Centauri, lies over 4 light-years away, an almost insurmountable gulf with current propulsion technologies. Detecting life remotely compounds the difficulty. Scientists must rely on indirect biosignatures, subtle chemical markers, anomalous atmospheric gases, or complex organic molecules that hint at biological processes. For example, mysterious methane spikes on Mars detected by rovers like Curiosity remain enigmatic, possibly signs of microbial activity, but far from conclusive proof. In sum, the search for life beyond Earth unfolds as an epic journey, an unfolding saga marked by tantalizing hints and formidable obstacles. Each discovery, each signal, and every icy plume brings us closer to answering one of humanity's most profound questions. Are we alone in the universe? Until that answer arrives, the quest continues, fueled by curiosity, hope, and the indomitable human spirit reaching ever outward into the star-studded void. But inconclusive as such evidence might be, methane detected on other worlds could stem from geological processes instead of biological activity, blurring the lines between signs of life and purely abiotic phenomena. Similarly, when telescopes like the forthcoming James Webb Space Telescope peer into the atmospheres of distant exoplanets, spotting molecules like oxygen, methane, or water vapor may suggest the tantalizing possibility of life. Yet, distinguishing whether these molecules arise from living organisms or non-biological sources remains one of the greatest scientific challenges. The very environments we seek to explore impose formidable barriers. Crushing pressures, searing radiation, and bitter cold demand spacecraft and instruments that are not only incredibly resilient, but capable of conducting sophisticated analyses remotely with minimal margin for error. Rovers and landers sent to these alien worlds must endure these extremes while collecting and analyzing samples, often in places so hostile that even drilling through thick ice to reach hidden oceans beneath the surface, as on moons like Europa and Enceladus, is beyond our current technological reach. The inability to access these subsurface habitats where life might thrive represents a significant limitation. Equally critical is contamination control. Ensuring that any signs of life discovered beyond Earth are truly extraterrestrial and not hitchhikers from our own planet requires meticulous sterilization protocols. Conversely, returning samples from other worlds to Earth must be approached with the utmost caution, safeguarding our biosphere against unknown and potentially dangerous microorganisms. Beyond technical hurdles, the scientific process demands rigorous standards. Any claim of detecting extraterrestrial life undergoes exhaustive peer review, reproducibility testing, and independent verification. The stakes could not be higher. Confirming life beyond Earth would rewrite the fundamentals of biology and astronomy alike. Therefore, potential biosignatures must be corroborated by multiple lines of evidence and observed consistently by different research teams before they gain acceptance. The quest to detect intelligent extraterrestrial civilizations presents its own labyrinth of challenges. Projects like SETI painstakingly scan the cosmos for radio signals or other communications, but separating genuine alien transmissions from human-made interference is an intricate task. The legendary WOW signal of 1977, a fleeting anomaly that never repeated, exemplifies the tantalizing but elusive nature of such searches, fueling ongoing debates and inquiries. Philosophically and scientifically, the definition of life itself complicates the search. Traditional Earth-based criteria may not apply to organisms with fundamentally different biochemistries or life processes. Scientists are forced to expand their horizons, considering the possibility of life as we don't yet know it, ensuring that their search does not overlook forms that defy earthly norms. Confirming extraterrestrial life thus requires overcoming immense interstellar distances, pushing the boundaries of technology, managing contamination with extreme vigilance, securing reproducible scientific evidence, deciphering potential intelligent signals, and broadening our understanding of life's myriad possible forms. Despite these formidable obstacles, this grand endeavor drives innovation and interdisciplinary collaboration. It pushes science to new frontiers and expands our understanding of the universe. The discovery of extraterrestrial life would revolutionize how humanity perceives life on Earth, influencing diverse fields such as biology, philosophy, astronomy, and theology. From a biological standpoint, finding life beyond Earth would provide invaluable insights into the diversity and adaptability of living systems. It would shatter Earth-centric paradigms, revealing new biochemical pathways and life processes. Perhaps silicon-based life forms or entirely novel molecular structures never before imagined. This could prompt a fundamental rethinking of life's prerequisites and unveil evolutionary mechanisms shaped by alien environments. Imagine life evolving under the fierce radiation of a red dwarf star, or amidst the frigid methane lakes of Titan. Such discoveries would broaden evolutionary theory, showcasing how life adapts to extreme and varied conditions. Philosophically, the confirmation of extraterrestrial life challenges human exceptionalism and places Earth within a vast, teeming cosmos. The Copernican principle, which dethrones Earth from the center of the universe, gains new force, suggesting that life is not a rare anomaly, but a widespread cosmic phenomenon. This shift would inspire profound reflection on humanity's ethical responsibilities toward other life forms and its role within a potentially interconnected cosmic ecosystem. Theologically, these revelations could prompt reinterpretations of religious doctrines concerning creation and the uniqueness of human life. Various faiths might integrate these discoveries in different ways, possibly enriching spiritual perspectives to embrace a universe filled with life. Scientifically, the discovery would highlight the importance of interdisciplinary research, merging astronomy, biology, chemistry, and environmental science to craft new tools and methodologies capable of detecting and understanding alien life forms with unfamiliar anatomies and biochemistries. The resulting technological advances could ripple across multiple scientific domains. On a societal level, the discovery of extraterrestrial life might foster a renewed sense of unity and purpose, encouraging global collaboration in scientific and exploratory ventures. It could spark a surge of curiosity and inspiration, rivaling the excitement generated by the Apollo missions, but on a cosmic scale. Economically, it might stimulate investment in space exploration, biotechnology, and related industries, driving technological innovation and opening new markets. The pursuit of understanding and possibly communicating with extraterrestrial life could become a major engine of growth and creativity. In essence, the discovery of extraterrestrial life would transform our worldview, reshaping scientific paradigms, philosophical thought, theological beliefs, and societal values. It would affirm life as a fundamental cosmic phenomenon and compel humanity to reconsider its place in the universe and its relationship with other life forms. This profound revelation could unite humanity under a shared cosmic identity, inspiring new forms of cooperation and enlightenment. As humanity advances, the question remains, what other discoveries await us? Will we uncover undeniable evidence of life beyond Earth, or are we alone in the vast cosmic ocean? The pursuit continues, fueled by curiosity, determination, and the enduring human spirit. What do you think? Could extraterrestrial life be out there, waiting to be found? Would its discovery change everything? Let us know your thoughts in the comments below, and subscribe to our channel Starflux for more explorations into the mysteries of the universe. Thanks for watching.